is this one.
So it's that one there, I think, right? So I open this one.
Open this one. Yeah.
Yeah, it just opens straight up like the presentation.
Oh, okay.
It's just on the other screen, so you might not get the. Yeah, it looks like you lose the.
You lose the notes.
Yeah.
Oh, I don't like that.
Yeah, we'll fine. We'll close it down.
Okay,
Yeah.
because I need to use my notes.
Yeah.
You're
I knew there was a
familiar with
problem.
that, yeah. You're not using the notes.
No.
Okay.
I might have.
Yeah.
Yeah. I'll probably leave it the way it is though, because it's easier to have, so that way I can have the time.
Okay.
Yeah, got it.
You're gonna try your run some programs.
Time.
Yeah.
There we go. Yeah. 34, but like,
Okay.
so like, if we look at this slide,
Because you have the animation. Okay.
so there's like 20 slides that are,
Okay.
a lot of them will be quick, where it's like, I explain the concept in these three and then I go like, this is what we need to do, this is where we're going to build it,
Okay.
and then I go through this fairly quickly, being like, these are the problems,
Okay.
cycle design, reactive cooling. This is what the layout should be, this is where I should be quite results, but everything
What
quite
do you
pretty
have
slow.
in the group?
No, this is the guys who are actually making it, so
Okay. So that's the.
that's what it's going to look like eventually. And it's like, some stuff has arrived, we have our analyzers, courtesy of, some of it is courtesy of Hydro, so have a chat with them outside if you need high quality gas analysis. And some of the skids have started arriving, we've got our compressors arrived. Here you can see the room as it's laid out now with our PSA, compressors and control systems arrived, the analyzers sit over here, the like important big bits that are here yet will sit in these two boxes at the bottom.
It's supposed to start on next year, right?
Well, no, it's supposed to have started in June.
June this year, right?
Yeah.
But
Yeah.
reality.
Yeah, I don't know
Next
exactly.
year. Okay.
Yeah, there we go.
Okay. Well,
There is it.
it's,
Yeah. If you open your one. I'm so sorry there's not one ticket. Yeah. You gave your pointer.
Yeah, I give.
His first name, but apparently that's more exciting. So yeah, so I might walk around with the mouse in my hand and click things. Do you want to restart the presentation for the series one? So like when we came in. This was running, so I'd rather leave it like we found it. Yeah. And then I do want to sit by the door today, unfortunately.
actually your web page, but Masoudi,
Yeah.
built on it.
If you just use the website.
Oh, okay, I can use it.
So not everything, but just like
Okay.
just
Oh,
things
okay.
is fine.
Mhm. Sure, okay, thank you.
Thank you.
No problem.
From the IACC, yes, so, so this is the agenda, this is just the conference room. Yes, this is the board room. So if you go to it was confusing for me to and there's
I
two
wasn't
pages.
aware there's
I
another
know.
one.
I was very confused and I was like, I cannot understand. Okay, there's two pages. Just understand which one.
Thanks. Thanks.
Yes. What's happening?
All right.
Yeah, that's good.
Don't feel confused if you see me walking behind you.
Super project.
I think we'll give like another 5 minutes.
Yeah.
to write.
走了。走了。
走
谢谢。
坐，
来在这吧。
这有别人吗？
没有，我自个儿跟一排。
我今天早上做个正义圆梦，到底做
过来了。
对，就10几分钟，我那个酒店。
可以可以。
I think a few people did. I'm presenting today, so I'll avoid it. And I need
现在是太早了，所以大家都还没来。
哦，9点还是那个啥？其实9点半刚刚好。
对 session 时间是不是太长了？应该都压缩一点儿。
是吧？
挺
这会
上次开完那个 CST， 然后吴老师就说，他说感觉这个会他整的时间太长。
哦，这个对，其实短一点，其实大家听到最后都累了。
就是 brief introduction 自己做啥，然后交流一下。
是，讲细节谁愿意听呢？真是，真的要是感兴趣，看文章了。这个哥们儿是线上的。
你同事也没来。
有点意思。
我不知道他几点到。
昨天都没拍个照是吧？Group
这
photo
些对没有。我昨天我还找那个 program 看有没有 group photo session， 我发现没有。
他们都没。算了，不吐槽了。
所以这个 organizer 是那个上的。
是什么？
上的。麦克上的。
不知道是谁。这次这个很尴尬，就是他们三个人吧参与，然后主要应该在 Brunel， 但是后续在 Brunel 那个 London， 但是又后续在萨里，然后就导致了这个事儿吧。
上的是萨里的。
哪个？
上的。就是麦克，就是红衣。
哦，就是他。
红衣。
哦，对，他是这边
这边是萨里，左边那是红衣。
对。
好像之前我听吴老师说，他说就是应该是 chair 把这些放到co-chair上，
对，
然后他不应该统一。
对。
所以他是 chair， 他是co-chair的应该是。
就是这个事儿，他们分工没有明确。
吴老师是啥？
因为吴老师我们弄的 IACC 嘛，这个是 IACC 旗下的这个会。这个事儿就是跟吴老师也说，3个和尚就没水喝。
都指着别人。
对，都想让别人。其实还有意大利，就是也是 mute 的，没事，他听不懂。那哥们儿人都没来。
确定一下啊，确定。线上直播。
尴尬了 ，YouTube 还直播呢。
这边没有摄像头是吧？
没有，只有他在 Teams 那边在共享屏幕嘛。如果他那个电脑开着摄像头就有。
但没有，那个就是个显示器吧。
他们那边电脑登录的那个 Teams， 然后再共享那个现在我们看到的屏幕。
我知道，我是说他那个显示器应该没有对人的那个摄像头。
这个不好说，因为它是个教室吧。因为有些教室就是按照360度的，我不知道这个屋有没有。我感觉那个像是，因为如果他跟人走，有些教室就装的那种。应该是3家，意大利的 Brunel 还有萨里。
这个是个啥？
就是咱们 IACC 不是注册 charity 嘛，然后就是他这个都是
在线上。
对，主要的人都来吧。
就是WeChat 上那些。
对，咱们WeChat那个群里边的，按理说都应该参加。
然后我们线下就在这个屋。是这样吗？
在哪个屋？对这个问题，
还是就都是在线上？
这个尴尬，这应该单独给咱弄个屋嘛，因为等下还有其他人都在里，是不是？他们可能来在这儿喝咖啡啥的。
不是啊 ，annual meeting 就告诉是 annual meeting 嘛，如果不相关就上外边待着去。这个教室就……
我最怕说这种话了，得罪人。算了，还是得给他改。
小教室啥的。这边线下
不知道现在有几个人来，问一下。
对啊。
尚静老师，咱俩仨。
咱仨就在外边那个就小桌那种也可以，其实不过比较吵。
算了，咱还用他这屋吧。因为他们这屋等一下也没事嘛，是不是？
对啊，他这块就是这个 session 嘛，然后上面开就太对啊，从
哎呦，那我估计下午都没人了吧？中间这么久，是不是从12:50？这是2小时，是不是？
上镜我不知道他能不能等到这里的。他说他下午有 visit， 他可能走比较早，估计中午就差不多了。
行吧。
就咱俩。
哦，就咱俩。
也不用别人。
那吴老师让我 share 个啥呢 ？share 真是他在线上就 share 呗。那他就在线上 share 呗。我勒个去！
他原来一开始他问我，他说我会不会来这个，我说会。他说到时候也水也会来，我们就大家都见一下，弄一个那个 IACC 的 annual meeting。
是，他就这个就是规定，他这个 charity 的这个要求，咱1年得有这么一个会，还得汇报一下财务啥的。那这可好，要本来想着尽量咱们这些人都在，但是最后发现得吴老师自己都有出事。
微信群里的
也就20来个人吧。
我知道，就是咱俩和上镜3人，没别的。
应该也是。一共29个人啊，乔元婷在，还有乔元婷也在。
啊，元婷。那个圆圆什么的，就那几个学生。
圆圆应该不在吧？吴老师应该就拉了老师进来。
袁婷也是挺social的。
啊。
是吧？
还可以。
我第一次见的梅梅，发现这次发现，上周感觉没有。
哦，那线下是咱，加上上午是咱4个，好的。
当时你一开摄像头，我往这一坐，
挺好。说起来咱这
黑白双煞。你是真白，皮肤我说。
我不爱出门儿。
我已经早就放弃。我在郑州开会，那帮人去我 booth 就展台去问我，都是问我哪国人，他们都不问我们一期，全都说是东南亚，还有上来直接说英语。我在中国，都很尴尬。
其实我现在都分不弄清，说我是什么日本人的、韩国人的，啥都有。
对，你比较像。
yes。我不敢开，我一开有 echo。
Okay, great.
Welcome back, everybody. See slightly less people here this morning. That probably means that.
So I'm very happy to welcome Shubhi as our second plenary speaker. So Shubhi Mukherjee is the Chief Scientific Officer at Ceres Power, and he's also a visiting professor at Imperial College. And he's had a lot of experience in clean energy technology, and Ceres is pretty much one of the leading solid oxide electrolyzer companies in the world, I would say. And I'm very excited to hear about all the progress that you guys have been making over the last few years. Dr. Mukherjee has over 25 years of experience in clean energy technology, and has worked previously at BP Chemicals and at Delphi Corporation. He gained his PhD at Yale and a postdoc at Harvard, and he's published in the papers. Welcome, Shubhi. Thank you very much for.
Thank you very much, Michael, for the introduction.
Michael, sorry, would you mind just to share your screen?
Yes.
Now it's only the camera view.
Michael is doing that. Can you guys hear me properly? All right, thank you, Michael. Again, good morning, everybody. So I'll be telling you a little bit about our journey at Ceres. We were a spin-off from Imperial College, and now we've grown over the last 21 years to develop a technology for both clean energy, and you'll see the importance of carbon capture in that, which I think is of interest to you, but also green hydrogen. So Michael kind of went through it. So I think about 12 years back, I joined Ceres. We were a small company with only 50 people. Now I've grown to be about 500 people, and we're growing fast. And we're a fast-growing clean energy technology company. And we have a very unique technology. It's a metal-supported solid oxide cell. And as you'll see, it can be used for both fuel cells. So you take fuels and you convert it into electrons to make them green, as well as you can take steam and you can convert it into green hydrogen. So we're using it for both of them. We spun out of Imperial College in 2001. It all started from a small EPSRC project by our founder. So all of you are doing work in the lab in the universities, even though little things can turn out to be quite a big thing over the years. So I generally bring, it's a small coupon-sized thing that actually first showed that you could do this. And the initial grant, I think, was for $200K or something like that. So we have now, as I said, over 500 employees, a lot of patents, and we have a very unique business model. We license our technology and our know-how to big companies all around the world to go faster into the market. And I'll show some of our customers who are taking this into products all the way. We work with them, we transfer our manufacturing, all our core know-how, and then just have them take it all the way. There's a company called ARM which does it for semiconductor industry, and we kind of say we're like ARM in the energy space. I think I don't need to tell you the need for these kind of technologies for green power as well as green hydrogen. I mean, this just shows the kind of by 2050, if we need to meet net zero targets, that's the kind of amount of growth we need in green hydrogen, over 7.5 times. And it needs to happen quite fast. And it's a huge industry, it's a huge market. And even if you take what we use today, for example, things like making ammonia and other industrial processes which absolutely need hydrogen, even converting them to carbon-free hydrogen or green hydrogen would be an enormous task. So I think there's a huge need for it, there's a market pull for it, and obviously our technology, but all of the other technologies are needed to make this thing happen on time. And the basic of solid oxide fuel cell, the beauty of it is it can be used, the same materials can be used for making electrons from fuels, but if you can run it in reverse by putting steam in and putting electrons in and make hydrogen. So that's the beauty of it, the same technology, the same material sets and manufacturing platforms, we can use it for both applications. So, as I said, at Ceres, we're kind of working on two different things. So one is Ceres Power, which basically is trying, and this is something we've been doing for a long time now, is basically using our technology for making carbon-free power. So I think we can use fuels like biofuels, natural gas, hydrogen, to make electrons, basically. And we can do it very, very efficiently. So that used to be a big part of our business. And now in the last few years, we have pivoted to making green hydrogen by running the same technology in reverse and scaling it up. And basically that's. And so what you see here is the key to our technology, which is a metal support on which we put ceramic layers. And that is basically the electrochemical device that does all of this, and I'll talk about it in a bit. And then you put multiples of this, which is kind of like a battery, we call it a stack, and multiples of these stacks basically add to more power, or in the case of hydrogen, making more hydrogen. So it's highly efficient in the case of Fuel cells, our efficiencies are 60% net, and even the rest of it is heat, which you can use. And it's very, very cost efficient because of the metal supported technology. Most of our, is about 80% ferritic steel, so it's really, really low cost compared to other technologies. And that's one of the big benefits of this. Also, we run, amongst solid oxide, we run at a slightly lower temperature than high temperature solid oxide, and that has some benefits because you can then use it without using nickel-based alloys, which again is a very big cost factor, and it's very scalable. I'll show you all of those. So, for the longest period of time, using our technology, these stacks, we were basically making this for the application in the fuel cell market. So that's commercial power, distributed generation, and a big, big thing that's kind of the market now is the shipping. So maritime is kind of really woken up to how they have to decarbonize, and that's a huge market for fuel cells. And quite an interesting amount of debate as to what kind of fuel is going to be used. I think all of the fuels are going to be used, but it would include things like methane, e-methanol, and ammonia. So people are talking, and depending on where these ships are going to go, they have different fuel choices, and so they want a compatibility. But it's a huge market for fuel cells that's coming up. The other additional very useful thing for this conference is that these can be combined with carbon capture, and that can be a very big thing. And today, with all of the incentives that's there in the US and even in Europe, we've done some numbers I'll show you. It starts becoming a very good commercial proposition to do that. So that's on the power side. And on the hydrogen side, with the same technology, with the same devices, you can put renewable energy in. And some of the big applications is green steel. So you go to decarbonize steel, and that's, again, a very, very big challenge, and we have to work with all of the steel companies to do that. Ammonia, the Haber-Bosch process requires hydrogen in huge numbers, and that requires green hydrogen. And of course, future fuels for making SAF, like sustainable aviation fuel, which is a big UK and global need, but also e-methanol, e-methane, and all of those things. So there's a huge market, and we are kind of working on this technology and production to cater to all of these things. So I think we talked about a little bit about some of the benefits of our technology. So like I said, there's a 300 micron ferritic steel on which we put our different layers. One of the key technology differentiations that we have is as an electrolyte, we use gadolinium-doped cerium. And all of our materials are very, very low cost. As you can see, ceria is very low cost and quite abundant actually. And compared to some of our other technologies like proton-exchange membranes, which uses iridium for electrolysis, none of those are an issue with our technology. As I said, it's highly efficient in the fuel cell mode. It's fuel flexible, so you can use natural gas, and that's a very good fuel for us. But you can also reform other fuels, biofuels, ammonia, and then feed it in. So we are kind of fuel flexible, which is a very big benefit. And of course, if you combine it with carbon capture, like I said, that's a very big benefit also. All of the materials we use are available widely, and we can manufacture at scale and quality. I'll show you a little bit of what some of our customers are doing. Very cost efficient and can be used for a wide range of applications. And what our customers like is that you can use it in natural gas today, and as we transition to a hydrogen economy, you can use the same device. So they call it a no regrets technology. And obviously, the fact that you can operate the same thing in the fuel cell mode or in the hydrogen mode allows for the big factories to be made, which can make these devices for both of those applications. So all of those are big benefits for our technology. And the SOEC, which is the electrolyzer for green hydrogen, the biggest benefit is efficiency. And so if you can combine it with heat, solid oxide electrolyzers have 20 or 25% more efficiency than other electrolyzer technologies like PEM or alkaline. And that's a huge advantage, especially for the things I talked about, like if you're making steel or if you're making ammonia. All of these processes have heat, and so if you can use it in a synergistic way, you can get that huge benefit of efficiency. And efficiency is very important in electrolysis because what it really means is, so the cost of, levelized cost of hydrogen in electrolysis is 70% actually the cost of the renewable electricity. So if your efficiency is higher, you can use 30% less electrons, which is a huge benefit in overall cost. So therefore, wherever you can, SOECs will have an advantage over these other technologies for electrolysis to make green hydrogen. A little bit about the details of our technology. So we start off with a ferritic steel, as I said. We laser drill it to make the porosity so that the fuel can go in the electrode side. We have multiple layers of ceramic then, very thin layers. Obviously, like all electrochemical devices, we have a fuel electrode, which is a Syrian nickel cermet. We screen printed. Then we have the electrolyte. This is kind of our main innovation. We can put a gadolinium doped ceria and densify it at temperatures at 1000 degrees C or lower. We co-fire that whole unit, and then we put the electron blocking layer, which is again a very, very thin layer, which you need for a gadolinium doped ceria type electrolyte, because otherwise you'll have electronic leakage. And then we have our air electrodes, which we put down by screen printing, and we have a barrier layer of another ceria layer in between. This is something we've perfected over the last 20 years, not only the materials, but the manufacturing. And this, we kind of say, is like our Coca-Cola recipe. We guard it with our life. We license it to all our customers. We make sure they can do it, but we don't give it to anybody else. So that's kind of what is the core to our technology. And year upon year, we make improvements on our technology, a little bit like your iPhones, if you may, because that's what our customers want. The licensing customers want continuous improvement. And so we have to improve power, we have to improve life, we have to improve robustness, and lower the cost. And that's where we also work with universities to get to the next generation of our technology, and that's what we license to all of our customers all around the world. And similarly, just like the cell, the improvements over the stack, you can see the size has grown, but not only the size of the repeating unit has grown from in the early days 78.5 square centimeter to now 234 square centimeter. The overall power is roughly 100 layers, now it's like 300 layers, so high volume, high current density, lower cost, and continues to grow. So a lot of development in that area also, which our customers license from us, and then also manufacture in high volumes. And like I said, we are fuel flexible, so we can not only use hydrogen, but also we are very, very efficient in using natural gas, a mixture of hydrogen and natural gas, biogas, methanol, ammonia, which in marine is becoming a very big fuel, and LOHC, which is also kind of becoming quite important. We are more tolerant than some of the other fuel cells to some of these contaminants, and that is a big point because, for example, in places like China, there's a lot of need for using this because there's some contamination in the fuel, for example, like hydrogen. So they like to use solid oxide more than other fuels. And as I said, we have lots of customers. So this same technology in the fuel cell mode, we have licensed to some very big companies all around the globe. Doosan is a very big fuel cell company in South Korea. They have licensed our technology. They're doing it for marine, and that's kind of the unit, the hundreds of kilowatt unit that they are making. They also have a factory in Korea, a 50 megawatt factory, and they're ramping up to 170 megawatt. It's all automated, works very, very well. Bosch, we all know, has licensed our technology and are manufacturing it in Germany. And so they are making this 10 kilowatt, very highly efficient, 60% efficient units, which are ganging up together to make hundreds of kilowatt. Weichai in China, they're the leading manufacturer of diesel engines. They have licensed our technology and they are manufacturing it for multiple applications. This shows their unit for stationary applications. And then similarly for electrolyzers in SOEC for green hydrogen, we're licensing it to different customers. So Delta is a customer in Taiwan who have licensed for both SOFC and SOEC. we recently announced Denso, who are a big company in Japan, one of the largest tier 1 automotive supplier companies, very good engineering, manufacturing. So that was a big announcement by us. They have licensed our technology for manufacturing. And then we're doing some work with Bosch and Linde and Shell. And I'll show you a 1 megawatt unit that's in the Shell in India, demonstrating for 1 megawatt scaling up. So there's a lot of licensing and working with customers all around the world with this technology. And that's our business model to grow faster and put these things in the market. And this shows some of the ramp-ups that are happening. So the 10 to 60 kilowatt now growing with Doosan at 600 kilowatt, in Bosch to hundreds of kilowatt, and in Weichai to megawatt. So, I mean, that's what we do. We have a very mature stack design. We do still and stack manufacturing, and then big demonstrations. The 1 megawatt is the largest we've done to demonstrate our technology. Now, a little bit about in SOFC, the carbon capture population. So, because of the high efficiency, obviously our technology has low carbon footprint with things like natural gas. But obviously, if you can include it with carbon capture, then it starts becoming a very attractive proposition. And one of the benefits of this technology is you can separate the air and with nitrogen and oxygen, so that starts becoming quite an enabling thing for some of the carbon capture technologies like amine type of technologies. And the concentration that you get at the exhaust of a solid oxide is quite rich in carbon dioxide. So that again is quite a big benefit to use some of the carbon capture technologies. So as you see, in our technology, we are somewhere around the 50% concentrated carbon dioxide. That can be a very good enabler for carbon capture. And this shows a little bit the levelized cost of electricity for a base case, kind of in the US. And if you look at it, if you use carbon capture technology, obviously it's slightly more in cost, but then with some of the incentives that are being given with the IRA, it actually is a very good commercial proposition. So even in Europe, there are some incentives. So these starts to become then very attractive to do that. So for your community, I think that's a very good news that these kind of things can be brought into the market. So that was a little bit solid oxide fuel cell. With all of the experience we have in fuel cell, we are also doing it now for electrolyzers, and that is starting to happen, like I showed. So I mean, we have now over 2 million accumulated hours of our applications, and that is quite attractive for our customers who want to take it for the maturity of the technology. And some of the things that people are really interested in is what is the steady state operation? So now we have over 35,000 hours steady state. Customers want 40 to 60,000 hours, and so obviously we're getting close to that, and we can get to that. Thermal cycling, so on-off cycling is quite a big thing in our technology, and we have a lot of experience in the field of doing this very successfully. And then something that's called emergency stop. So if you have to suddenly stop a technology, you want to make sure that you are robust to e-stops, emergency stops. Load cycling, which is again a very important one. And then the other one is that for transportation and handling, there are no special requirements. So all of these are very important for our customers, and we have shown that those are all there in our technology. And what our customers want is 60,000 hours, and we're running these different things, but we do a lot of lifetime projection. And one of the things that we can do is slowly increase our temperature over life and be able to make the same amount of hydrogen at the same efficiency, at an absolutely world-class efficiency over that window. So that makes it a very attractive proposition for making green hydrogen over the 50,000 hours. And obviously the same robust thermal cycling that we've seen in our fuel cells, we demonstrated in our electrolyzer, and the emergency stop that I talked to you, which is quite important because you need to be able to be robust with these things. And one of the things that in solid oxide fuel cell that you do is there's expansion and contraction of the nickel as you do more of these things. So we are very, very robust with that. And then the other big challenge is the scale up. So you have to scale it up to 100 of megawatts to gigawatts to have any electrolyzers propagation that can work. So we are doing a lot of work. So 1 megawatt unit, like I said, is right now at the Shell facility that we're testing. And they consist of 8 stacks of 100 kilowatts, which are all ganged together to do and demonstrate this. And we've tested them for about roughly 9,500 test hours with very good efficiency. And one of the good things we're seeing is the performance are very, very repeatable in all of this. So we are kind of doing this and putting it together and seeing a lot of consistency, which is very beneficial. And so what is it that we need in the platform? So we have all the required characteristics for SOEC. So one is running at a thermoneutral voltage. That's the highest system efficiency you can get, and we are able to get that. High steam utilization, we are able to run them of over 75% steam utilization. Low airflow, that reduces the parasitics and enables life, so we are able to do that. And high pressure, so about 30 bar, and we are able to do that at system level. And we are initially going to show stacks at about 2 to 3 bar, and then at a system level at 30 bar. And this shows kind of the efficiency breakdown, and we can, even with some of the efficiency losses that we'll get for some of these heaters and power conversion and compression, are at a below 40 kilowatt hour per kilogram. It is absolutely world class at 30 bar pressure for an electrolyzer. And we've now designed what we call a stack array module, which is about 24 stacks in a pressurized container, optimized for all of these different things. And so our customers can take that design and make it and put multiples of these for a green hydrogen plant. And we've taken this on to enable our customers to go to the market faster, because we understand this technology better, and that's why we think that's something in our licensing model we can. And basically, you go from a stack to a stack array model, then multiple of those, that then goes into a huge green hydrogen plant that you have to make. And this is quite a kind of a new thing. You have to work with multiple types of people. So some of our licensees obviously are making cells and stacks for us, but we also have to work with engineering and procurement companies to make the kind of a print for basically a plan to actually make that happen. And hopefully that gives you an idea of kind of how this technology has developed from a little bit of a coupon all the way to now all of these plants at very high volume. So with that, we'll show you a little bit of a video of how a future plant with the series technology would look like and what it would do, so you get an idea of that.
is a leader in clean energy technology, enabling the world's most progressive companies to decarbonise at the scale and pace needed to achieve net zero. Ceres have leveraged Atkins Realis' global expertise and capabilities in hydrogen across the full value chain to identify opportunities to use Ceres' technology in industrial applications. Together, the two companies will develop an electrolyzer module and commercially scalable green hydrogen plant design based on the highly efficient Ceres steel cell electrolyzer technology. Let's take a look at how the plant building block is differentiated from low-temperature electrolyser plant designs. At scale, the technology decarbonises industrial sectors, utilising building blocks of 100 megawatts of modules with scaled balance of plant. The plant will produce green hydrogen at a rate of 26 kilotons per annum at 30 bar. Ceres steel cell electrolyser is the latest generation of SOEC technology, which provides the advantage of operating at lower temperatures. This differentiating feature means that Ceres' proprietary technology uses 30% less electricity compared to alkaline electrolysis when coupled with heat from industries such as fertilizer, chemicals and steel. Not only does this save on renewable power costs, but it also saves significant plant capital costs by reducing the substation size. Ceres' electrolyser module, which, due to the lower operating temperature of the technology compared to other SOEC technologies, removes the need for expensive materials and design complexity. Each 8.6 megawatt DC electrolyser module produces over 6 tons per day of hydrogen, with a footprint of only 120 square meters. Designed for optimum performance, the balance of plant is centralized and optimized to recover heat from the hydrogen purification and compression to warm up the feed water, increasing overall energy efficiency and significantly reducing the cooling requirement by 19 megawatts. As the electrolyser module is pressurized,
Michael, sorry to interrupt. There's no voice online.
and electrical
There's no audio.
is reduced at
Do you know why?
plant level versus unpressurized electrolyzers. The plant's highest efficiency and lowest capital cost is
Almost finished.
We have enough time to repeat it again, I guess.
Yeah, maybe we can do that during the break.
Mhm.
I'll just repeat it during the break.
achieved by integrating with an industrial facility that produces
不是很多
heat. For example,
但是我们在扣享和 YouTube 都在直播，所以其他的平台还会有很多人。
Ceres and Atkins Analysis 100 megawatts plant design enables a significant reduction in the cost of hydrogen production, providing the optimum solution for heavy industry transitioning to a cleaner energy future. To learn more, go to ceres.tech.
Okay, well, so I think I'll kind of end with just a few summary thoughts. I think you've seen how we're looking at fuel cells and electrolyzers. We are trying to go at pace. I think that's absolutely needed for decarbonization and the need for getting to net zero faster. We have to scale up, we have to be bold, and we're trying to do that. I think one of the things for your community that is important is there's a huge market for combining solid oxide fuel cell with carbon capture, and we are actually looking for partners in carbon capture industry. So if you know somebody who has a very exciting carbon capture technology, please let them know, and we'd love to work with them or to know more about the technology. Because then you can use some of the fuels like natural gas that does exist today as infrastructure and do carbon capture, and again get very carbon-free electrons. So with that, big thank you, and I'm happy to take questions.
Any questions?
Thank you very much for the very interesting talk. Actually, I may have missed that part in the video, but I was wondering if your process, I mean, the plants that you're presenting there, has any kind of heat integration. I understand that it's kind of low temperature SOEL, but not to what degree is low temperature, and is it suitable for heat integration for being more
不
efficient?
是，他在线上应该他读车，他没
We
来。
offer about 600 degrees C, so we can absolutely have heat integration.
我记错了，我以为他一台
If you have, for example, an ammonia plant or a steel plant, yeah, absolutely. So it's very good quality heat. You can absolutely integrate it with all of these things.
Thank you for your talk. Hope your company will be bigger and bigger. In your talk, you did emphasize on the marine industry for the future market, but I saw several concern and several fund in aviation fuel. So how you see the fuel cell for using the aviation or using for the jet fuel
Yeah, so I think, again, very good question. So I think in marine, the thing they're talking about is using fuel cells, but with fuels like ammonia or methanol to basically, as you go into ports, you want to have emissions free for all of these things, right? So those are being mandated. For SAF, which is the Sustainable Aviation Fuel, I think fuel cells, there are some people talking of fuel cells, but it's the technology still needs to be developed a lot for use as a power generator in aviation. But for sustainable aviation fuel to be made, one of the ways of making it is to make green hydrogen with electrolyzers and then combining it with other chemical processes downstream to make it. So that's how I think we will spend a lot of work on. Solid oxide fuel cells in an aircraft, I think is still quite far away. People are working on it, but that's, you need to have gravimetric power densities, which are very, very high. So those are not mature technologies.
Yeah, thanks for the presentation. And just wondering, what do you do when the batteries reach the end of life? Can you recycle the materials? And do you have any supply chain issues with the metals that you use for the technology?
So most of, as I said, most of the technology is steel, and there are some ceramics, and so all of them can be recycled very, very easily. And we are looking at further sustainability things like, can you separate them, and can you use some of the materials back again? And we use things like gadolinium dioxide, which today is used in catalysts, your self-cleaning oven and things like that. So the supply chains are all there, they're all quite well known, and we don't have some of the problems or issues with the supply chain as such.
Thanks for the presentation. I was going to ask, you mentioned the IRA and you mentioned the EU having a lot of favourable subsidies. Are you working much in the UK, say on HyNet, or is your business currently sort of very much focused?
No, we work everywhere, and we are a UK company, that's the UK technology, and we have very good links with the UK government. I think we are trying to see now for SAF, where the UK government is taking a very leading role, how we could do some things to do something in the UK. And so both for the SAF and the carbon capture that I talked about, we would love to have UK partners or funding from Innovate UK, etc., to do some demonstrations in the UK. I think many of our licensees as customers are global, so therefore we always give a global pitch, but anything in the UK.
Thank you. IACC from University of Aberdeen. I have two questions. The first one is, my experience and my knowledge about the business model is very limited. So I'm just wondering, can you just briefly explain to us again, what does the series do for selling? Just talk to technology and licensing with other partners, is it? That's the only thing?
Good question. So we developed the technology, so we all of the things that you saw in that core technology, the stack, even the system design, those are all our designs. So we developed the design, we developed the manufacturability, so we have a manufacturing plant in Redhill, so close to London, where we can make about 2 megawatts of these units. So when our customer, let's say a Bosch or a Doosan, come to us, we give all of that know-how to our customers. The design, the know-how, our engineers work with them, and then they replicate our, for example, even in manufacturing, they replicate our plan over there. And they take our designs. We are the design lead, so they cannot change the design. They have to manufacture things with our designs. And so they do that, they scale up. Obviously all these companies are very good at high volume manufacturing. So they have, either use the supply chains we give them, or they use their own supply chains in their part of the world. And they then ramp up very, very fast. And then they scale and they have sales, they have marketing, they sell it to their customers. They depend on us to work and develop the improvement that is required for the next generation technology, and they pay us for that. And when they start selling the products, we get back the royalties from those products that are sold in the market.
All right, it's much clearer now. Thank you so much. My second and last question is, well, Series was started as a spin-out company of Imperial College London. Would you mind if I could ask, so how much of the PI belongs to the IC at the moment, or is the Series its own 100% of the
Yeah,
IP?
I think none of the founders are part of Series, obviously, for a long time now, but we obviously know them very well, we involve them very well, we respect them immensely. I think one of them, Brian Steele, Professor Brian Steele, passed away some time back. He had, from a health reason. But the other founders are all there. They have professors in there. We recently celebrated our 20th anniversary, and we invited them back, and we had it in Brighton, and then we had 500 people in there. It was quite an emotional moment for them to see all that had happened in there. But no, they're not involved in the day-to-day running or anything like that. But they kind of stay involved, and we invite them from time to time to do that.
Okay, thank you very much.
Right, any other questions on the room? Yeah.
Sorry. What other industry you think that could be the future? I mean, the future market. I mean, apart from the marine industry.
For fuel cells, you mean, or electrolyzers? I mean, for fuel, anywhere you need power today, you need to decarbonize it, right? So distributed generation, all the data centers, power for all the data centers need to be from renewable sources. So it's a huge market for all of these things. The question is, which one do you target first and get in the market? I think marine could be a very important one because it's being mandated by a lot of regulations. So I think the shipping industry is very much looking into it. But distributed generation is a huge market. I mean, every time we are using our cell phones and that's expanding our social networks, we are using electrons coming from somewhere that gives off carbon. And so I think all of this are going to be big market.
Great. I think I've got one quick question.
Yeah.
I found it quite interesting the going up in temperature to keep the kind of efficiency levels.
Yeah.
How do you know how to do that? And, how is the decision made, and what's the kind of ramp up, these kinds of things?
I think that's a very good question. I mean, obviously, we are doing a lot of work on predictability of degradation and looking at it. In our conversation outside, I think that's where all of these things are very, very interesting, because we do it passively right now, but if we can do it in some controls actively, it would be very, very interesting.
Great. And then another thing around that kind of flexibility, you mentioned that it can switch, between fuel cell mode and electrolysis mode.
Yeah.
Do you have any clients that actually want that to happen, or do you find people just wanting one version? And also, if you were to have clients wanting that switchability, how easy is it to actually deliver that?
Yeah, I think again a very good question. So I think we think it's one or the other, which are the first markets. But there's a lot of development and R&D going on in kind of places where you can switch back and forth. And some companies are involved in that. I think the jury is still out whether that will be a cost-effective proposition for a commercial need. But where it will be required is if you have remote areas, for example, where you need electrons, let's say during the day, if you have solar, and then maybe you want to make some fuel or something else during the night, you want to do that. The balance of plant and all of these things have to be worked out so that it's cost effective. And the efficiency, the round trip efficiency, is what people are always looking at for those kind of things. Obviously, it's easier to do one thing at a time if you want to combine them more. But there's a lot of work going on.
I guess if you can do that, you can do like
Yeah,
that's and then the switching is a bit longer term rather than just like daily switch.
Exactly. Yeah, absolutely. So all of those are exactly the same. and especially in academia, a lot of those type of work is going on, which is quite interesting and I think should be done.
Great. I think we've got time for one question if anybody does have an extra question. If not, then let's thank Shubi again. Thank you. Now we've got, I think about 10 minutes.
我得去弄一下线上的还正常时间。
20 minutes? 20 minutes break? Ah, okay. Oh yeah, he's on
not dominant, but
Who are our speakers for the next session? Are you one of the speakers? Okay, great. You can upload just you can use the.
OK， 没问题。
我们视频拷过来再放一遍。
不用，他就把链接放一下就行了。我得出去了，丽莎。哎，我主要得充电器。不，我的意思。
那个下午你说那个其他人的话来得及吗？
来得及。
啊，来得及。
嗯。
我是优价，
我得出去充电啥的。
那你出去充电？
啊，也得那个啥，这个扛不住。聊天人。
我1分钟出。
怎么找个充电的？Good. I just need to charge my laptop somewhere. See. 哦，我得蹲那儿蹲一天，只有这个是吧？
不是那个我们招待那个左右桌子上地板上有个铁片儿，这个铁片一翻翻起来。哦。
然后那个桌子那儿有，那还有灯。
那我这儿那也行，给你们倒咖啡。哇，开了吧 ？Yes.
Have you been taking pictures of the events and stuff like that for the IACC?
I just took a few of these. I was thinking, should we take a group photo?
Maybe it's a good idea. Yeah.
Is it?
because
Maybe
yeah.
during the lunch time, we still have many of us. Otherwise, in the afternoon, is the afternoon after the lunch, we are going to have the general meeting. So that's including the lunch break is going to be 2 hours. I'm thinking some of the people might leave. So lunchtime.
By the way, what is that general meeting? I saw it in the.
Oh, it's the IACC is a registered charity, so we have to organize this kind of general meeting every year with all of the organizing committee.
Okay.
So yeah.
Because I saw it in the schedule and I was like, what is that?
Yeah, we have quite many of the committee members who attend online, and we chair the session with several of us.
Salman, have you been taking pictures of
Yes.
Okay,
yes.
Great. Well, then maybe that's the guy to
Yeah.
talk to. So from the Institute for Sustainability, I want to share some things. I don't know, maybe you can email some pictures.
Yeah.
Just like a or something. Yeah. Maybe also upload
你看我这位置好不好？
Maybe put together a folder and then we all.
Yeah, let's do that. Yes.
第一场或许。
Yes, yeah.
我来，我皮糙肉厚一点。
I mean, yeah, it was 6 p.m. yesterday.
Yeah. Nice, nice, nice. 这个我买的快，一看一会儿就充满了。
快充是吧？
嗯。
那45入也没有很亏钱。
亏啥呀？
因为以后出去也能用。你在上海没发现吗？
发现。
发现那个充电器不行。
在上海哪个充电器？
对，你现在不是在澳洲买的吗？你在上海没发现？
对，我上海就发现了。可是我在机场里就是逛，我就没找着卖充电的，我找了一圈，整个机场我都逛了，他都没有那个卖这个那个啥的，就是充手机的有，但是充电脑的他就没。
还在充吗？
所以上海我就没买着。
哎，这不实在要是吗？去机场买一个。
我懒得出去，我就给博宇看那个 proposal 了。
哎，行。
还行。行吧，这也没人偷吧。
这边这里。
Yeah, that seems like a newish shift. Earlier conversation. But maybe it's just he wants to focus on that for this particular actually, but it's great because that's also the thing that I was trying to get support for they were quite keen at the beginning and just ended up towards the end they were just for one time it's like
based on what I could understand of the you guys do is also, optimizing or democating units, PSA, these sort of things. And also pleasing the lab.
Yes, it's USA. So, and we've since Survey. So we can collect a lot of data, and then if you tell us what you want, we can collect all these data and just pass them to you, either for validation of the models that you have, or if that sort of database could help the machine learning.
We're quite interested in using that for like control purposes, but also like for as we were saying, should be doing this kind of like if you include the performance prediction on materials, looking at how that degrades over time, and controlling that like dynamic behavior so that you don't stress the materials.
I see.
Quite interesting to like have a look at that, because I think that there's a trade-off there, like an optimization problem. You don't want to stress the materials, but you want the throughput, so you like have some sort of balance.
Interestingly enough, with Paulina, studying Masoudi. So she's joined us in January. She's her background control. Then her past 2 months, so she's basically involved in the experimental process of like, so she's looking into the control side. I think there's potential there.
Do you know what sort of doing like model predictive control?
Have a chat with her, because that's beyond me. That's beyond me. But I think what she's really interested in is, well, we had a discussion before, and you mentioned as well, the interdependency of food gas that is dictated by the share of renewables into it. I think that's something that we really want to do. So
and also it's also with machine learning that's kind of has a lot of trouble as well, because you're not I mean like it looks great, but like in reality that's not actually there's no it's very difficult to then put control over that. So those models, like yes, they're fast.
How reliable?
But also the problem is that they're not. They're not that good to run optimizers because the gradient's like super.
Exactly.
These neural nets. So there's a lot of like interesting pattern models.
Makes sense. Old school guy.
Well, I like that too. I mean, we always go first principles and try to find ways you can answer those. Yes, that's what I did for Surrey as well. It was just like just trying to do. Should be great talk.
Thank you. Very, very good. We were actually talking, and since you said that you have a lot of interest in chronic cancer, it is my background. There's a lot of around.
So I think we don't have combustion, so fuel cells. There's no loss of solid. But then there is after burning, catalytic burning, and then the exhaust comes out mostly CO2 and
excellent.
So that's why what are the really leading technologies of you, right?
That's perfect.
Exactly. That's kind of the pitch that we have to do.
Excellent. That's exactly what we are. At the moment, we're trying to establish. So we have a secure project based on this externally funded project by the government, and it is coming to an end at the end of this year. Well, March next year. The plant we're building is this year. So what we're doing is we're decarbonizing. Lovely.
Going here.
So we're basically going from 400
the one in.
Is it open?
I don't think that this is your guys' event. Yeah, this is for
But at the same time,
they see the opportunity.
Literally 2 weeks ago, on the impact of moisture.
So then you don't need to do it so much during
compress the absorption of water, so you can work at the same time. So you can dry it out, but you can sometimes if you have a lot of
yeah, I just need a
let's say direct air capture, dropping out the water there becomes immensely expensive. So clearly you wouldn't do that. The amount of water versus the temperature rate that you need to
Yeah, exactly.
well, in what way you sort of
Because I mean, there's a lot of we did an analysis.
right.
There is a cost.
Absolutely.
So I think
I think that's an area, that's the type of guest you're looking into, that's definitely something we can work on.
Yeah. Question about you mentioned biogas. How does your material respond to the like CO2 concentrations and like H2S and things there? Or I mean, H2S is not that difficult to remove. Most biogas plants, it's like the cheapest on the site.
So I think that's the key thing with biofuels is how you take out the contaminants. The one that is the biggest challenge is silicon training things. But people have get theirs.
I'm also thinking if you've got that CO2 rich stream, the ways to turn that into kind of like syngas. Because I know that some of these catalysis
so that's the thing.
this is what South African
can you take
thinking
CO2? Yeah, but then it's not carbon neutral. Then you are making.
Yeah, it's who's this for? I didn't get one over today. Is that all right? Oh, look. Thank you. Oh, brilliant. I just thank you. And then sorry. Oh, sorry. Would you like me to sorry. That's so sweet.
Last furnace.
I didn't even get one over today. Oh my god. I wasn't looking where I was going, I was plugged in.
You want to find?
Yeah, basically. I'm just going to go and pass them.
I would say I'm so
Yeah, have you tried this one from it's from like the audio shop?
So that's we just first. Eventually, that's going to come through. It's okay. The point is, that's a real country, especially untraditional.
But yeah, because I don't have like the matcha whisk or anything. I can just pour hot water in it. It's ready. You can obviously try it. It's not,
oh, it's in the front?
Yeah. And it's like sweet already, so you don't have to. It's already sweet, so you don't have to add any sugar.
Is that matcha?
There isn't matcha here, but it was really good. I'm so excited for this. And I think they're going to bring that. I know, that's what I thought.
Yeah, that's some hot water.
Oh, thank you.
No,
I might have coffee.
I don't think there's much coffee there.
Yeah.
Yeah.
Oh yeah, thank you. And then pastries. Yeah, like crust. I don't think so. I'm like, okay. Jessica, I'll see you outside. Wait, no, carry away from me. No way. Free. What do you want? Which one do you want?
Excuse me, ladies, do you know which group you're in? No, it's not yours. Sorry. It's not yours.
It's also the other thing that's like coal. It's like 80% coal electricity mix as well. So you've got tons of switching white sources. So coal is the main fuel. So that's all made their money by taking coal instead of giving to liquid fuels. Cars run off from coal. It's so bad. It's so bad. You're chairing the session. Yeah, I know.
Yes, my love.
Thank
Let me move over here. Yeah, I tried to cover it, but unfortunately, because it's a walkthrough, everybody thinks it's theirs and it's yours.
You're right.
I'm not being rude to them, I know.
Yeah.
I came here this morning, I served part of you. I had to go and do something else. That's why I'm trying to be careful with this.
Thank you. Oh, sorry, dear.
Can I help you, my love? Are you with this group here?
Yeah. Thank you.
Okay, that's fine.
Yeah.
Sorry, I have to stay here to charge my laptop.
That's fine, darling, that's fine. I know you're with that group. It's just that there's another group in here and it's nothing to do with them. Nothing.
Okay,
Looks
okay.
as if I don't know what I'm doing. Sorry.
Can I take
Yes,
one?
of course you can. That's why they're covered.
Thank you.
This happens to everyone we do. Can't leave it. As soon as we disappear, there's another group in the building.
Yeah, I see.
Right. with this group here.
Yeah.
That's fine.
How are you?
I'm fine. I've got Let's Theatre G pinching you stuff as well. And there's no... They've got nothing booked. Right, there you go.
Through which we discover this molecular trap-down mechanism. For the applications, then I will discuss our perspective and ongoing developments in this topic. To raise your interest, to seek your suggestions, and possibly to motivate you to work with me together on this interesting topic before we conclude. So molecular separation plays a key role in energy and environmental factors. Important applications are listed here, including carbon capture and hydrogen purification, which are directly related to. So in chemical and process engineering, molecular separation is a critical unit operation, which can account for over 60% of in certain processes. Taking CO2 capture as an example, there are 4 technologies, molecular separation technologies available. They are solvents absorption, cryogenic distillation, membranes, and adsorption. Particularly interested in adsorption technology because such as high energy efficiency, low operating. Okay.
That's why.
Okay. Thank you. So secondly, molecular sieving struggles with separating molecules of similar size, especially when the size difference falls in the range of sub-nanometer or even sub-angstrom. So for example, if we want to separate CO2 and acetylene, they have the same kinetic diameter of 3.3 angstrom. It's impossible for the conventional molecular sieving to work. So if we want to go one step further, we want to do size inverse sieving. For example, when we recover low-grade methane, we would prefer to selectively admit and adsorb larger component methane while rejecting the smaller component nitrogen for the better energy efficiency, because selective adsorbing the minor component in a gas mixture will be much more cost effective. So in order to address these limitations, we need a new mechanism. Okay, and recently we discovered active saving mechanism in a class of chaplet zeolite. We refer that to molecular trap down mechanism. So in this talk, I will focus on discovering this mechanism and showcasing the interesting applications. So here we just want to give you a heads up, the key feature of the molecular trap down mechanism. The pore apertures are blocked by metal cations. And certain molecules which have suitable interaction with the door-keeping cation can induce the temporary and reversible cation movement to open the gate so that to get admitted. And other molecules will be excluded. So in this way, selective gas admission can be achieved based on the ability of the molecule to open the gate rather than on size. So this is an active saving process because the gas molecules actively trigger the host door open for entry. So then I will start the journey of discovering this interesting mechanism. So as we mentioned before, we discovered that in chaplet. Chaplet is a typical small pore zeolite with three-dimensional structure made up of double six-ring prisms linked by tilted four membranes, creating the 8 membrane, 6 membrane, and 4 membranes in its structure. So here only the 8 membrane with a size of around 3.8 angstrom serve as the size to the interior pore structure. And the extra framework cations need to be present and distributed at different positions to counterbalance the negative charge of the framework. So one key characteristic of chaplet is that if we have cations sitting at site S3', which is at the center of the 8 membrane, it will impact the pore accessibility of this material. So we prepared the chaplet with different cation type and density and measured CO2 natural methane adsorption and plotted adsorption isobars. So adsorption isobar describes the gas uptake changing with temperature at a given pressure. So here we have 2 interesting observations. Number 1, at low temperature, the CO2 can be admitted, while nitrogen and methane cannot be admitted. Number 2, all the 3 gases can exhibit the unusual bell-shaped isobars. So a bell-shaped isobar signifies the transition of the pore accessibility from inaccessible to accessible status. So we will show that from the first interesting observation, we identify the molecular trap down mechanism. Then we will later show that the second observation is actually a key feature of the molecular trap down mechanism. So in order to understand such an unusual gas admission behavior, we use cesium from chaplet did in situ synchrotron powder XRD of gas absorption experiments. Then by resolving the XRD patterns, we found that the cesium cation is rightly sitting at the center of the 8 membrane pore aperture, with the site occupancy being 100% throughout the whole temperature range we studied, suggesting a pore blockage. So this actually explains why the nitrogen and methane were excluded at low temperature. But then the temperature, then the question arises, why was CO2 admitted given such complete pore blockage? So we believe for any molecules to pass through, there must be movement, the cation movement, at least partially. So indeed, from literature, we found that the cation migration can occur between the pore aperture site to the supercavity site at high temperatures. Then we wonder, is such cation migration linked to the CO2 admission? So we did DFT calculation to determine the energy barrier for this cation migration process. It determined to be around 500 MeV under vacuum. So actually, the magnitude of this energy barrier is so high that it's impossible to occur in the temperature range we studied for our gas absorption experiments. But indeed, CO2 is admitted. So we were wondering, is it because the presence of CO2 molecule that can facilitate the cation migration process? So accordingly, we made the hypothesis the CO2 can induce a temporary and reversible cation deviation from the center of the pore aperture to get admitted. So in order to examine our hypothesis, we further did the DFT calculations to determine the energy barrier of the cation movement in the presence of gas molecules. So this figure illustrates our proposed CO2 admission process. So in the beginning, with the 3 CO2 molecules on the one side of the sodium cation coordinated 8-membrane pore aperture, the energy barrier for cation movement is substantially reduced to 45 MeV from around 500 MeV. Then with the sodium cation moving towards the CO2 molecules, one of the CO2 molecules will move into the center of the 8-membrane pore aperture and sits at the momentarily opened pore aperture. Then with this CO2 molecule passing through the pore aperture, the sodium cation will come back to block the gate again. So in short, the CO2 molecules pull the door open to get admitted. So we refer this process to molecular trapdoor mechanism. So clearly, the presence of gas molecules plays the key role in reducing the energy barrier for the door open, therefore to enable the gas admission. So the CO2 can significantly reduce the energy barrier, while nitrogen and methane just slightly reduce the energy barrier. So that's the explanation why CO2 can be admitted. So then we found found experimental evidence that aligns with our hypothesis. So firstly, our in situ synchrotron powder XRD of gas absorption experiment results show that the CO2 was indeed admitted, then with the cation occupancy being 100% at the pore aperture. So that suggests the cation movement is a temporary and reversible process instead of a permanent migration process. Because if it's a permanent migration, we should have been able to capture that using the XRD. So secondly, we did sodium AMR in the presence of CO2 and nitrogen. We found that in the presence of CO2, the cation mobility is much higher. That indicates the CO2 has stronger interaction strength with the document cation. We induce the movement. Okay, so here we give a brief summary of the molecular trapdoor effect. The gas admission is via a temporary and reversible cation deviation process induced by the interaction with the gas molecules. And the molecules with stronger interaction strength should have lower threshold admission temperature, therefore enabling the temperature-dependent accessibility. This is the active process where the pore aperture keeping cations dynamically participate in the gas admission and the explosion process. So then we go back to the second interesting observation, that is a bell-shaped isobars. So here we measured absorption of hydrogen, argon, nitrogen, and methane on another typical molecular trapdoor adsorbent, potassium from trapdoor. We found that these 4 gases exhibit different threshold admission temperatures. That indicates the different molecules have different interaction strengths, will have different ability to open the door, reflected by the different admission temperatures. So that actually proves the molecular trapdoor effect is at play. So in order to quantitatively describe such an unusual bell-shaped isobar, we need to come up with a new capacity model, which is also very important and essential for the process design. So here we revisited the gas admission process. We split the gas admission process into 2 parts, 2 concurrent parts, the cation deviation and gas hopping. So accordingly, the energy barrier for a successful gas admission it includes 2 parts. The delta E host accounting for the energy barrier for the door open, and delta E gas accounting for the energy barrier for gas molecules passing through the momentarily empty pore aperture. So here we use iterative DFT calculation to determine the energy barrier for the 4 gases. So we won't go into the detail because of the time constraint. And also, for the model deviation, we won't go into the detail. We just come up with a new model. Actually, it's a modified TOS model. If we remove this part, it reduced to be the classical TOS model. This part only introduce this K parameter that accounts for the temperature-dependent port accessibility. So with this new model, we only introduce two parameters. One is beta, the other is hidden. The other is T0, which is the threshold admission temperature. So beta is the width of the transition temperature range. By applying this new model to our molecular travel zeolites, here you can see the curve represents the model fitting. We achieved a perfect fit. Here we have some interesting findings. Number one, the experimentally determined threshold admission temperature T0 is in linear proportion to the theoretically determined square root of the energy barrier for gas admission. So that actually validates the definition of the T0. So secondly, the T0 is in linear proportion to the apparent pore size. So that indicates we can make use of this feature to make tunable molecular sieves. And thirdly, we also found that beta, the width of the transition temperature range, it somehow correlates the molecular mass. So that indicates maybe we can make use of this to do isotope separation, same size but different mass. We also applied our model to other family of porous materials, including supramolecular hosts and morphs. We achieved good fitting again. So that is very important because it's essential for process design. Okay, then I will go through some interesting applications. So firstly, in order to demonstrate our molecular travel mechanism can work for separation, for saving, not based on size, we examine the CO and the nitrogen separation. So these two molecules have very similar physical chemistry properties. CO is a bit larger than nitrogen. At the same time, CO is a bit stronger than nitrogen because of its dipole moment. So on a conventional non-trapezoidal material, you can see we achieved fairly no selectivity. On a typical molecular trapezoid solvent, we can achieve a CO over nitrogen selectivity up to 7. Okay, so this is the first time we show size inverse saving can be achieved. And we also use our molecular trapezoid solvent for nitrogen and methane separation. This is one of the most important and most challenging application in separation science. So sometimes we favor methane selectivity, sometimes we favor the opposite, depending on the minor component in the mixture. So here we show one adsorbent can achieve invertible selectivity between these two gases. So basically, the TC of the two gases can divide the whole temperature range into 3 regions. In region 1, which is below the 2 TCs, both molecules cannot be admitted, they are blocked. Okay, so we achieve no selectivity, actually negligible uptake for both gases. Then in region 2, that is between the 2 TCs, we can achieve a nitrogen over methane selectivity based on the molecular trap-down effect. Then in region 3, where the temperature is above the 2 TC, both molecules can be sort of freely admitted. We can achieve a methane over nitrogen selectivity based on the conventional equilibrium-based separation. This is the first time we show one single adsorbent can achieve invertible selectivity. We also demonstrate that for the same size saving between H2 and D2. If you still remember, the different gases with different mass will have different beta. That is the width of the transition temperature range. As long as we can find a difference in their transition temperature range, we can find a window at which one molecule can be admitted while the other is excluded. And of course, we use that for CO2 capture from nitrogen and methane. We achieved the record high selectivity of CO2 over methane at 10 bar. And to prove our molecular travel down mechanism is not compromised by gas mixtures, we did a binary breakthrough between CO2 and methane. You can see the high selectivity is well maintained, consistent with that calculated from single component isotops. Then we went one step further. We run a simple PSA, a 2-byte PSA at 20 bar and 20 degrees C. We can achieve remarkable separation performance with methane product purity of 100% and recovery of over 90%. That proves our molecular travel solvent is useful in real applications. And we also tried that for gas storage. If you still remember, so under our molecular travel mechanism, if each gas molecule has a threshold admission temperature, so maybe we can use that to do gas storage. So we can load the gases above its threshold admission temperature and then lock it inside below its threshold admission temperature. So we did that for hydrogen, and because of time, I won't go into the detail. So here we use a working temperature, a threshold temperature of 170 K with a dosing pressure of 70 to 250 bar. We can achieve up to 78% of hydrogen storage. Although it's not satisfactory, at least affords a different idea to design materials for gas storage. Then initially, because of safety concern, we were not able to demonstrate that gas storage using hydrogen, so we used nitrogen instead. I will skip that. Then later, we demonstrate that using methane. Okay, then I will briefly touch on some perspective and ongoing developments. So until now, did you notice any limitations of the molecular travel solvents? Any idea? Yes. Okay. I think most of you didn't realize that. That means maybe I made a good story. So actually, there are some limitations. One is the kinetics. The other is the uptake. You can imagine for our molecular travel mechanism to work, we need numerous cations to block the pore aperture. So it would be difficult for the gas get in and get out of the pore, so the kinetics won't be high. And also, because of the large amount of cations, the gas uptake is limited. So how can we address these limitations? So the first idea is to make the temperature regulate the membrane. So in this way, we can just use significantly reduce the number of cation blocked pore apertures to do the separation, so that it can potentially increase the kinetics. This is an ongoing project. It's not easy. So finally, we managed to make the membranes based on our molecular travel solvents. Then the second idea is to make the cold shell zeolite particles in order to increase both the kinetics and uptake. The idea is simple. We want to use a non-trapped material as a core to provide high capacity, and use molecular trapped material used as a shell to provide the high selectivity. So this idea is simple, but we didn't we have not made it yet. So hopefully we can find someone to make it for us. And in order to prove our molecular travel mechanism can be broadly applicable to other zeolites, so we challenge the established belief that zeolite LTA, which is maybe probably the most famous molecular sieves. So we challenge that. We believe the gas adsorption in LTA zeolites is where the molecular travel effect. So we managed to demonstrate that CO2 can be admitted in the 3A zeolite, which is the potassium form A zeolite, with the potassium cation formally blocking all the 8 membrane pore apertures. So we also observed the adsorption configuration of the adsorbed CO2. So we demonstrate that zeolite LTA actually follows the molecular trap-down mechanism for gas admission and absorption. And also we further show that we can fine-tune the adsorption kinetics and the threshold admission temperature by changing the cation type and the density. And recently we demonstrated the hydrogen methane separation using 3A zeolite based on the molecular trap-down effect. And since we have proved that the molecular trap-down effect can be applicable broadly to different zeolites, so this is another project. We want to use molecular trap-down zeolites with similar cages but different cage connectivity. We want to study how the cage connectivity can impact the adsorption kinetics. And another idea to increase the kinetics is to make the molecular trap-down in the channel type zeolites. So in this way, instead of using numerous dot-keeping cation at each pore aperture, essentially, in principle, we just need one cation, one dot-keeping cation per channel in the channel type zeolites. This is an ongoing project. And of course, we want to extend the molecular trap-down mechanism into morphs, which can potentially give us unlimited possibilities. So we started this idea on Z-morph, a zeolite-like morph, which shares similar structures with zeolite. That is, it has negatively charged framework and positively charged cations. So initially we were not able to synthesize the material, so we did a simulation study. We found that we can use 3 cesium cations to together block 1 pore aperture and induce different gas admission behavior. And only recently we very luckily found a collaborator who made this material for us successfully. Now they are installing the dot-keeping cations based on our prediction. And we also demonstrate the molecular trap-down effect in other 2 cationic morphs. So they have a cationic framework and with ions as the dot-keeping as dot keepers. So we demonstrate that in one case type cationic morph, one channel type cationic morph. And the last idea is to use electric field to induce the cation movement. So we believe by using an electric field instead of temperature, it can probably give us faster cycle of gas absorption and storage operations. This is an ongoing project. So using our dedicated in situ electric field setup for gas absorption, we have observed the change in gas uptake in our rigid trap-down zeolites, and also in some flexible zeolites, as well as in a lot of interesting morphs I got from my collaborators. Okay, now I can conclude. So we discover active saving mechanism for gas separation termed molecular trap-down mechanism, where gas molecules are discriminated by interaction strength rather than size. And we also derive a model to describe this temperature-dependent admission behavior. So we achieve a series of applications by the active molecular trap-down mechanism, which are not possible by the conventional molecular saving. And we believe that high potential to expand the molecular trap-down mechanism into other porous materials, especially morphs. And we can also use other stimuli such as electric field to regulate the molecular trap-down behavior. So finally, I would like to acknowledge my postdocs, my students, and my key collaborators, and also the funding agencies. I'm happy to take any questions. Thank you very much.
We have a couple of minutes, very quick questions. That's time.
Yes.
Really fascinating.
Thank you.
I have a question here.
Yeah, sure.
So I'm curious about one of my questions. So you're regulating the endless
Mm. Yes.
What if you have gas molecules that have similar actions with the gate to be? For example, if you have like ethylene and something like that, what would be your separate?
Yeah. Good question. So basically, for a given material, we rely on their different ability to open the door. Now, how to define the different ability? So basically, we look at the polarizability, the dipole moment, and the quadrupole moment of the gas molecules. And recently, we also found that sometimes for two molecules, for example, CO2 and acetylene, they have same size, similar magnitude of quadrupole moment, and similar polarizability, but they can still exhibit very different ability to open the gate. Why? Because their quadrupole moment is in opposite direction. So I think that I would call that different handles we can use to induce the different ability to open the gate. Yeah. So if they have a quite similar property, maybe we can change it to a different door keepers and a different host porous materials to further maybe to magnify their difference in the ability to open the gate. Thank you.
We're past time, so any other questions, please Dr. Shane during break time, I will say.
Thank you.
Again. Right. So the next speaker is Christopher Lulu from University of Manchester, and I'll leave it to you now.
Hey, so I'm going to give a quick chat about the Recycle project that we're running at the University of Manchester. It's a Department of Energy and Security and Net Zero funded project, and we've got a selection of partners that are working on it as well, from across the UK and a little bit in France as well. This project is all about building a small pilot scale but very large pilot scale for a university system to produce hydrogen with carbon capture from natural gas. I'll have a quick chat about what the concept is, what we're trying to do, and then hopefully show you some layouts of what we've built so far. Unfortunately, it's running a little bit behind schedule, as all government projects do. But yeah, we'll see how it goes. Cool, so the basic of it is it's all about a chemical looping process that can run at high pressures in adiabatic packed reactors. So we have 3 reactors that go through 3 different stages, and they're all slightly out of phase with each other, as Vlad discussed yesterday. So first of all, we oxidize our metal to metal oxide. This is really exothermic and produces loads of heat. We then reduce that metal using off-gas or low-value fuels. This stage can be exothermic or endothermic, but it's almost heat neutral for most reducing metal. Whether it's exothermic or endothermic depends heavily on like what metals you're using, what the gas phases are. But in terms of overall heat balance, the bed will remain in the hot state it was at the end of the oxidation, but will become catalytically active. And that's when the reforming comes in. So we can then use that heat that we've stored in the bed with our reduced metal oxide, with our reduced metal, to then carry out a reforming, turning our methane into a syngas of hydrogen and CO. And this is very endothermic, and then that cools down the bed, ready for the oxidation step to then reheat it up. And we loop through these 3 stages to get a chemical looping system. In particular, this project is looking mainly at using nickel for our pilot plant scale, because nickel works really well as a reforming catalyst and is a good oxygen carrier for carrying out the oxidation and reduction as well. We're doing this in packed beds because that means we can operate at high pressures. In fact, the system we've designed to build at the University of Manchester operates at about 30 bar, and the simulation and design work we're doing for the next stages of the project operate at even higher pressures. And by operating at these high pressures, we get to produce high pressure hydrogen without having to put hydrogen through compressors. We can just compress methane, which is much easier.
and doesn't involve as much slip. In terms of how the overall site would work, the technology can work for a variety of different sections, can use a variety of different feedstocks. Currently in this project, we're using natural gas because it's cheap, abundant, and easy to get funding to use. But other projects that we've run at the University of Manchester have used bio-waste and other reducing gas projects. And then the syngas that's produced, we could use for many different things, but we're looking particularly at attaching a water gas shift and PSA system to produce pure hydrogen for power or for decarbonising industrial heating. Oh yeah. So in terms of what we're aiming to do with this project, we're building a 20 kilowatt hydrogen plant, aiming to produce 99.5% pure hydrogen out the back end, and operating that in a pseudo steady state, so operating it more similarly to how a reactor system would. And as well as that, we're going to be producing a high purity CO2 in a separate stream, which we could use for sequestration. We could sequester or use somewhere else in plant, but because we're running it at the university, all of these gases just go up the flue, and we just need to prove that we've produced them for the next stage of the project. So like I said, we're building this at the University of Manchester. We're in fact building it at the top building there on the right-hand side of the screen. This is a combined teaching and research institute, which has made a lot of extra funds for us in terms of what we can do for safety, how we can build a hydrogen demonstration plant inside a room where next door undergrad students are doing some simple water-based chemistry to complete their undergraduate degrees. In fact, we're building it in the building to the right. You can sort of see two pictures of what the almost empty room looks like when we took it over, and that's the sort of size we're going to build this whole plant in it. We believe this is the first fully integrated chemical looping plant in the world to produce both high purity hydrogen and high purity CO2 at the same time, and it's the largest packed bed chemical looping plant in the UK.
It's okay, you can go inside. There's a back door as well. If you turn
in terms
right,
of what we're actually designing and building, we'll have a quick look through the process flow diagram just to get you a feel for how large a plant we're doing and all the steps we're making in it.
Okay.
So we take natural gas from the main supply, so we're just piping that straight out of the natural gas that will go to most of your homes. We're removing the sulfide stuff that's in there to make it smell funny, so we don't have to deal with the sulfur in the reactor. We compress it, we mix it with demineralized water, and it then goes to our chemical looping section, where it will enter one of the 3 reactors at different times. The syngas that's then produced is then cooled down quite aggressively, and then we have a second heater after that to control the temperature, so we can then set it through a water gas shift reactor to increase our hydrogen yield, and then through a PSA unit to produce our hydrogen. Unfortunately, that hydrogen needs to be vented because there's nothing we can really use it for in the university. But the tail gas from our PSA, which is still reasonably hydrogen rich and very CO rich, we then feed back into our chemical looping plant. So we use that as the reducing gas on site. We can also use methane, CO, or hydrogen, or any other number of gases from bottles to make it up and for startup, so that we can get the system going without having to lift ourselves up by our own shoelaces. That gas feed is then reacts with the nickel oxide in the bed to form a mixture of CO2 and steam, and there shouldn't be anything else in that gas phase. We then cool that down so we condense out all the water, and then we can send our CO2 to vent, and we measure the purity of that CO2 to ensure we hit the requirements needed for what the government thinks it wants for all its pipelines and sequestration for the later projects. The final bit is after we finish doing the reduction, or before we do the oxidation, we need to get rid of all the flammable gas out of our mixture before we start mixing air with it, because we shouldn't be mixing our air with our hydrogen or CO at any point, because we don't want the university to explode. So we purge out the reactors, and that purge also goes to vent. And then we also have an ambient air that we take in from the top of the building, which is then pressurized and used for the oxidation, which goes down through the same coolers as the nitrogen vent does. On top of that, all of our coolers produce steam at about 200 odd degrees C, which we then cool back down again using a more normal cooling water system. And then we have some deionized water that we condense out that we then either recycle or send to vent. This system is then built on a number of rigs, a number of skids that are in the room, so that we can modularize it to make it easier to move it around and get it into and out of the room and building. In terms of the design problems we've been facing, they sort of go into 2 sections: designing how our system's going to cycle through, and dealing with all of this suitable cooling to make sure nothing scary happens. So I'll go into a little bit more detail of those. So in terms of the cycle design, because we have 3 reactors, initially one of the reactors will be in reforming. We then need to purge out our reforming gas mixture so that there's no hydrogen left in the reactor, or no CO or no methane, before we can start our oxidation, so we don't have air oxidation going on at the time. We then purge out our oxygen to make sure we don't have anything on before the reduction. And then our second and third reactors then go through similar stages. The important thing to notice here is reduction reforming gases are always flowing somewhere. They're always going to one of our 3 reactors. So we need to make sure we put the right interlocks on so we can turn the gases on at the right time and off at the right time so we can redirect them to where they need to go. Which means that because we're always flowing gases, if we redirect our flows to the wrong places, we need to be able to measure and control that, and we need to make sure we can change things at the right times. The other side of that is that when you change when you're changing where gases are coming from and where they are going at the same time, we have some problems. So we need to work out when we turn a gas on, how long it's going to take for that new gas to reach the end of the reactor so we can then change where it's going at that point, rather than changing it immediately and then feeding the wrong gases to the wrong flue. The counter to this is that the purge and the oxidations do not run continuously. So we have pressure heads stopping flows, which adds different sorts of complexities. So managing both of those together was a lot of fun, and we think we've got that well planned, but we'll see how it goes when we finally get it up and running and working. The other side was reactor cooling. So our reaction product gas is rich in CO and CO2, and if we cool it down to below 600 degrees C as it leaves, it can start reacting with our metal pipeworks if we're using stainless steel, causing metal dusting, which causes holes in our reactor system, which leads to leaks, which is bad because we don't want our hydrogen CO leaking into the room next to where all our undergrads are. So we need to make sure we cool that system down to 200 degrees C with expensive metal pipeworks. So the aim is, can we make this distance here between our reactor, our cooler, and our furnace as short as possible so that we can avoid how much expensive material we need to build. We've got a 3D layout of where the room is. I think I'm probably going to go through this quite quickly. Essentially, we've got a selection of different things in different rooms. It's all quite compact. Lots of tight pipeworks and other things going on inside this room, which is about 10 meters by 10 meters. There's lots of fun things in there. The layout works. I was hoping to be able to show you some results, but while some deliveries have arrived, like our control system and some of our compressors have arrived, most of the room is in fact still empty. So hopefully our chemical looping reactors will be arriving in the next couple of weeks, and then we can start connecting everything up and realizing all of the other mistakes we've made that I will talk about in the next time I come to this conference. So we should be able to achieve pseudo steady state. We've had to specially design a load of coolers, and we are still slightly behind schedule as expected from a government project. But so just to acknowledge our funders in the Department of Energy Security and Net Zero and all of the partners that have been involved in the project. There's a lot more details online about different bits that are going on if you want to have a look at that website. But cool, thank you. Yeah.
Actually, 2 questions around the rate and the recycling process. The first question is around safety. So, how you can, let's say, certify this process is going to run smoothly during the scale-up? I mean, imagine if a purge stage does not operate, or there is a malfunction in purging stage. How you guarantee that the process is not going to go out? So the second question is how you manage the cycle time in order to reach the steady state. So I imagine all these cycles are not run on the same time frame. So one of the processes may be shorter than the other. So are you using a kind of surge time to run a steady state or continuous process?
In terms of safety, for the scale we're working at currently, we have gas analysis at the back end of every single reactor. So we can measure how much of each different gas is turning out in each different place. That's part of our analysis system. And in terms of at larger scales, that's why we're building the pilot plant to show how it will work and to make sure we can successfully model and simulate how this sort of work works. So yesterday, Vlad talked a little bit. So he also works on this project and he's looking at simulating this whole plant and working out those sorts of things so we can ensure it does operate safely. And then the second question, which was about cycle times. So cycle times are kept consistent. That is one of the design parameters, is the oxidation time, the time for reduction. The time for reforming and reduction are kept the same, and the oxidation plus purges is kept to a set amount of time, and we change flow rates to ensure that we have the right amount of time for each system. It gets more complicated at larger plant sizes. So our size, we only have 3 reactors. The bit of the project that is about taking it forward to the next stage and simulating larger plants that would actually operate profitably is looking at changing the number of reactors as well as the flow rates to ensure that we don't have too fast gas velocities. So I think currently for attaching it to a glass, for replacing a glass manufacturer's current methane heating with hydrogen, we use one reactor going through oxidation, 2 reactors going through reduction, and I think 4 going through reforming. So that's the other variable that we can change. It's just that in the pilot hall space we have, building 3 reactors at all was quite a engineering feat in terms of getting everything close enough together. Cheers, thank you.
So our next speaker is Santiago Zapata from University of Manchester.
Okay, hello everyone. My name is Santiago. Today I am presenting some results of the C4U project that we are working on Manchester. It's advanced carbon capture for steel industries integrated in CCUS clusters. I'm dealing now with the CASO technology, which is a calcium-assisted steel mill-up gas hydrogen production technology. For steel production, you may know that there are mainly 2 processing routes. The first one is the blast furnace, basic oxygen furnace route, and the electric arc furnace. And the blast furnace route is particularly carbon intensive because it relies on coal as both as fuel and reducing agent. And on the other hand, the electric arc furnace route is less carbon intensive, but it is limited by the scrap availability and also some quality requirements of steel. In this presentation, I am focusing on the BF route because it accounts for around 70% of global steel production. And in particular, blast furnace gas is it's generated when hot air reacts with coke in the blast furnace, and its composition includes around 20 to 30% of CO, 20 to 25% of carbon dioxide, and the rest hydrogen and nitrogen. Currently, it's used as fuel in the steel plants, but it has a very low heating value, and is produced in large quantities. So it has a major role in the overall emissions profile of steel plants. The steel production is very energy intensive with high CO2 emissions. It accounts for around 8% of global CO2 emissions, and its demands will increase in the future. Therefore, there is a need to invest in clean hydrogen generation to support the transition, and also to retrofit assets with CCUS technology. Because there is a target to reach net zero emissions by 2050. Therefore, I am presenting now this technology that we are working in the project, the CASO technology, which purpose is to transport this blast furnace gas into a hydrogen-rich gas with a higher energy content, and also to generate high temperature heat. the CASO process consists on 3 stages: the CASO reaction, the oxidation, and the reduction. In the first stage, the CASO reaction, it involves the production of a rich hydrogen gas through the water gas sieve reaction of the carbon monoxide contained in the feed. This reaction is performed with high temperature reactor beds packed with calcium oxide and copper-based materials. And the copper-based materials act as catalysts in the water gas sieve reaction. We have a continuous removal of the CO2 from the gas phase shift, which pushes the equilibrium towards a higher production of hydrogen. Okay. The second stage is the oxidation, where the copper-based solid is converted to copper oxide with air at high temperature and high pressure and moderate temperatures, and we obtain nitrogen in the reactor outlet. And finally, in the reduction, involves 2 reactions: the endothermic reaction of calcium carbonate, and also the exothermic reduction of copper oxide to solid copper using a gaseous fuel. So in this process, we use a fraction of the blast furnace gas for the oxidation of the copper oxide. And it's very important that this reduction process is thermally balanced. So the same, the energy released by the oxidation is used by for the calcination reaction. And as a result, we obtain a CO2-rich stream that can be used to produce any other product or to okay. Well, in practice, the process occurs using sequentially operated pack-baked reactors. The solid remains in the bed and a system of switching valves is used, similar to the pressure swing absorption. So here we have the CASO reaction first. This reaction is exothermic, so we need a heat removal stage. For that, we use a closed system of nitrogen. And from that nitrogen, we can generate high temperature heat. Well, we have the oxidation, where the nitrogen is obtained, and this is the nitrogen that is used to cool down the reactors. The reduction, important to note, with this CASO process, the CO2-rich stream has around 54% of purity, so we need a further purification process. And finally, we add another heat removal stage. Therefore, as the purity of the CO2 is not high, we improve the process with this CASO enhanced unit. The main difference is that we include a calcination step instead of the first removal, where we use a steam, and as a result, we produce a CO2-rich stream with a purity of around 99%. So this is the main difference of these 2 processes. The rest of reactors are the same. Yeah? So how do we model this complex process? First, we started with a 1D heterogeneous reactor model, which takes into account mass transfer in gas and solid phases, energy balance across the system, and also reaction kinetics. This model was experimentally validated with the rig we have in the university. And this model allows us to predict the molar composition of the product gases at the outlet of the reactors, and also the maximum temperature achieved in each stage. And we use this data as input for the process simulation in Aspen Plus. Here we have the PFD of the CASO process, showing the 3 reaction stages: CASO, oxidation, reduction, and the 2 heat removal stages. As I said, we use around 1/3 of the blast furnace gas for the reduction stage, and also we need a further purification step for the CO2 that is released in the process. For this study, I consider partial condensation. On the other hand, in the CASO enhanced, we use all the blast furnace gas for the CASO reaction, so we produce more hydrogen, and also the CO2 stream is around 99% pure, so we don't need any further purification. I use several process performance indicators to evaluate these 2 technologies and compare to a benchmark with amines, MDA, CO2 specific emissions, CO2 capture rate, and the specific primary energy consumption for CO2 avoided, or SPECA. Results This table presents the comparison of the two CASO technologies with the benchmark. And initially, we can see that the thermal energy output in the hydrogen stream increases from 77 to 161 megawatts, because we use more blast furnace gas for the reaction. And also, the CASO process, it actually releases energy because the process is overall exothermic. On the other hand, in the CASO enhanced, we need to use a furnace for the calcination reaction, so we need around 57 megawatts, but it's much lower than in the benchmark, the MDA, which uses around 143 megawatts of thermal energy. The CO2 flow rate with the CASO enhanced is the highest, and also it has the highest purity, 99.4%. And it shows very competitive indicators in terms of CO2 specific emissions and SPECA, actually SPECA much lower than the benchmark MDA.
Can I bother you for a sec?
These process performance indicators depend on the utilities that we
so
consider for
basically,
the energy consumption of the plant.
Are you a member of IACC?
Yes.
Okay, so you know we are a registered charity from North Island, so that's a part of the organizing things and also the law. So we have the organization of the meeting with all of the members. So we want to
with the different cases, for example, case one we use hydrogen,
how we are going to manage the charity and what is the strategy and also financial parts of this charity.
This hydrogen is the one that comes
be very generic, so Professor Chunkery is going to briefly introduce the IACC to everyone here, and also we have the committee members who are going to attend online as well, and also I will spend a couple of minutes to just sharing all the financial, all the transactions happening last 2 years about IACC. That's it.
Higher CO2 capture than the benchmark, all the scenarios.
Yeah, we chair this session.
Actually, the CO2 capture rate increases between 1 and 29% respect to the benchmark.
So there is nothing that we need to prepare here on this end.
And this table shows a comparison.
We can keep everyone here in case some of them will be interested to join in IACC as well.
Scenarios.
Well, I hope so. There's enough people.
That's why I'm here.
Okay, yes. So, and we are not doing a break in between.
We are using renewables, so we don't have any indirect emissions.
So that's
we achieve lower SPECA than in the benchmark when we
could have
use
a short
hydrogen,
break,
reducing the process for heat and power consumption. The other scenarios increase SPECA between 8 and 5.
Yeah, we could have 10 minutes of a break.
Yeah, because for me the big question is with the
in conclusions, we were successful developing a model to capture the dynamic nature of the CASO process.
Oh, you mean for all of these talks?
We modeled this in Aspen
Yeah,
Plus.
you're well doing the lunch,
Stationary
you're well
process
doing the
that
lunch.
Chris explained before. Also, we demonstrated that all the CASO systems exhibit higher CO2 capture than the benchmark. In particular, the CASO enhanced show a competitive performance with lower CO2 specific emissions and SPECA than the benchmark. And very important, the scenario analysis demonstrated that these performance indicators are very sensitive to the modeling assumptions and the utility mix. So it's very important to consider direct emissions and indirect, from the process and also for the energy source. Future work, of course, integrates OPEX and CAPEX in the analysis. Actually, the presentation, the title of this presentation was Techno-Economic Analysis, but it was not allowed to include any economic results by the project partners. Hopefully, in the next meeting, I could include some results. Also, the results are very sensitive depending on the energy prices. Very sensitive. I am not including any result. And now we are working on a detailed process design, simulation optimization, and life cycle assessment of the most relevant scenario. I have to thank the funding received for this project. It's from the European Union Horizon 2020 research, and also to the project partners. Thank you very much for your attention, and any question you have, very happy to answer.
And we have online questions.
Yes, of course. But we have another person in the audience who's asking the question now, unfortunately. Yeah, sure. So the person who was asking the question online, please go on.
Yeah, right. This is Tomas and Jose here from Sevilla University. Hey guys, so congratulations, Santiago. Very beautiful presentation. I have two questions actually. One is you said that the hydrogen boiler seems to be a way forward for this process. The reference case is natural gas boiler, right? I couldn't pick it up.
好的好的
Yes.
这几天照顾不周了啊
Good,
下次有机会
good,
我再
fine.
好好交代
And the second question goes to the initial concept of the project. You are doing a combination, a hybrid calcium looping water gas shift, where your temperatures, to me, for the carbonate formation and the water gas shift doesn't match very well because you wanted to use a water gas shift catalyst based on copper, but this reactor is running at 700 plus, right? So maybe you could consider a different kind of high temperature water gas shift catalyst. Have you considered that? I mean, copper is a low temperature shift catalyst, basically.
Yeah, if I got your question, is in terms of the operating temperature, or operating conditions of the calcination reaction, or in general?
Yeah, calcination reaction and water gas shift are happening at 700, right? More or less.
Well, actually, in the Caso reaction happens at 750 degrees Celsius, and the calcination around 833 degrees
Right.
Celsius.
So the Caso reaction is a hybrid process, you said, with calcium carbonate formation plus water gas shift. It's not a question, it's a puntualization, right? So you are using a low temperature shift catalyst for your model, copper. I would say that perhaps you should consider a high temperature catalyst like iron or something like that. Just a puntualization. I don't know if you have considered that.
Well, that's a very good point. We haven't considered yet that, but it's we could evaluate the use of a higher temperature catalyst.
Yeah.
Yeah, thank you very much for that.
I appreciate some modeling work, but I'm an experimentalist. I'm sorry for that, but in practical terms, I don't think the copper will work at 700. Really.
Okay. Okay.
Cheers. Thank you. Congrats.
Thank you. Wait. No, actually, the main industrial partner is ArcelorMittal. Yeah, so it's one of the leading. Okay, can you repeat the name? Okay. Okay, yeah, thanks. Yeah, now we are looking to find industrial partners to demonstrate this technology. Okay, thank you.
Maybe just one last quick question myself. What sort of equation of state did you use for reactors?
You mean this? Okay, so basically with this reactor model, I'm a modeler, so I didn't work in this reactor. You have the reference there. So what we did is to build a model in MATLAB, considering this mass transfer, energy balance across the system, reaction kinetics, and we can find the conversion, and also the maximum temperatures. So what we do in Aspen is to use stoichiometric reactors. Yeah, the stoichiometric reactors, we set the conversion to the one that gives us the model, and also we set the composition of the outlet streams and the temperature. So we work in a closed loop. We use the results of the reactor to feed the simulation, and then we go again to the reactor model, and we make sure that both results are in agreement. Yeah, of course, this has been experimentally validated before. Yeah.
Right. So one last time.
Thank you. Thank you.
Our final speaker. Thank you. So our last speaker for this session is Yuan Zhou from Queen's University, Belfast.
Okay, thank you so much.
My name is Yuan Zhu. I'm from Queen's University, Belfast. I'm super honored to have this great opportunity to do this presentation and share our research. Personally, I finished my PhD study 2 months ago, and I'm doing a postdoc work at Queen's. And for today's presentation, the title is Integrated Biomass Gasification with Carbon Dioxide Capture and Utilization, and we call it IGCCU technology. And I would like to give 3 sections for this presentation. I would like to start with the conventional CCU technology and then the ICCU technology in our research group. And the final part is my PhD work focusing on the IGCCU technology. The first part is the CCU technology, which is carbon dioxide capture and utilization. And I know some research may call it carbon capture. I do think that's still some debate and discussion about this topic, but anyway, it's quite important about the carbon capture technology. There are some reasons for this. First, they can help to remove the carbon dioxide from different kind of carbon dioxide sources. And it can help to reduce the carbon dioxide emission. Most importantly, I do believe that this technology can help to reduce the global climate change issues. And as you may know, that there are quite a few CCU technology, carbon capture technologies. And I do think that one of the most important is the memory separation technology and liquid or solid solvents for the carbon dioxide capture. And the next part for the CCU technology is the carbon dioxide utilization. And it can be also called the carbon dioxide conversion. We know that the captured carbon dioxide can be converted to many high-value products. For example, it can be employed in our daily life, like can be used in the food industry. But from a academic perspective, I would like to say the captured carbon dioxide can be used to generate valuable chemicals like carbon monoxide or some hydrocarbons. And for the conventional CCU process, it can be included into several steps. First, the carbon dioxide can be captured from the point source or directly from the atmosphere. And then the compressed carbon dioxide can be transferred by different ways, like the pipelines or the shape from the point of the capture to the point of utilization. The last step is that the captured carbon dioxide can be used as a resource or feedstock to create chemicals and fuel products. We do know that the CCU technology have a lot of advantages, like I mentioned before, recycle carbon dioxide, it can be enhanced the economic profits. But the conventional CCU technology still face some challenges, like some of the CCU technology are still very far from the real world market. Like it's always at a very high cost because the carbon dioxide and the solvent transportation is quite expensive. And I do know that I want to mention that the CCU technology do not deliver a 100% negative carbon dioxide emission because the solvent regeneration process always connected to the carbon dioxide releasing. The next part is the advanced ICCU technology, which means the integrated carbon dioxide capture and utilization. And for this technology, we can check this figure here. We can see that when we introduce the carbon dioxide containing fuel gas into the system, the diaphragm can be used to capture the carbon dioxide. And then when we switch the carrier gas from the flue gas to the green hydrogen, we can see that the captured carbon dioxide can be converted directly. And this advanced ICCU technology show great advantage, like all the reaction can be conducted in one single reactor. and the reaction temperature is always the same. So it can help to emulate the energy requirement, and it can help to address the transportation issues of the traditional CCU technology. Next part, I would like to say that the most popular ICCU process can be classified to three categories, like the ICCU RWGS technology, ICCU DIM, and then ICCU methanation. And for like recently, there are some researchers employ very advanced and fancy technology like the plasma to activate the ICCU. And I do think that are a lot of reaction parameters for the ICCU technology. Okay, this is one of the most important publication in our research group. You can see that we use calcium oxide alone material for high purity syngas production using the ICCU RWGS reaction. And we can see that we achieve very good carbon dioxide conversion rate and carbon monoxide selectivity. And more importantly, from the result of the Aspen Plus simulation, the cost of the producing carbon monoxide is like 292 US dollar per ton for the improved ICCU process. It's quite cheaper than the reference scenario. Okay, this part is the most important part for my presentation because it's my main content of my PhD work. It's called IGCCU technology. I would like to give you more details about this technology. You know, like we are facing two most important global issues like the energy consumption and climate change. Like we can see that from the right figure, the carbon dioxide concentration is increasing year by year, and in the government panel report, the global temperature is 1.5 degrees C higher than the pre-industrial level. So I do think that we should pay more attention to the renewable energy to solve the problems here. So for the renewable energy resources, we can see that biomass energy almost account for like half of the total renewable resources. And biomass gasification technology is quite important to turn or convert the biomass to the valuable energy or products. And we can check the figure here, the red figure here, the development of the biomass gasification technology. We can see that at present, over 2.4 billion people are rely on the biomass. And we can see that biomass can be classified to many categories. And for our project, for our research, we mainly pay attention on the carbon products. And the carbon products can be there are three main carbon products, like the biochar and the carbon monoxide and the carbon dioxide. We know that the biochar can be directly used to capture carbon dioxide after some modification, and the carbon monoxide is the main content in the syngas, and the most unfavorable product is carbon dioxide. And for some research, they proposed the sorption enhanced gasification technology for capture the carbon dioxide during the biomass gasification. But there are still some challenges, like there are still some carbon dioxide is sitting in the gas products, and the captured carbon dioxide conversion process is still facing very significant challenge. And I do think that the overall carbon dioxide emission during the whole process is quite important. in my PhD work, I propose a IACC technology to address the carbon dioxide emission during the traditional biomass gasification process. And the first research is achieving zero carbon dioxide emission from the integrated biomass gasification with carbon dioxide capture and utilization. We can see that from the conventional biomass gasification process, we can see that we use steam gas biomass gasification process. We can see that the carbon dioxide can be produced, but in our novel IACC technology, we employed the ICCU technology to couple in the biomass gasification technology. We can see that in the first step, during the biomass gasification, the produced carbon dioxide can be captured by the carbon dioxide, and then we switch the carrier gas from the carrier gas nitrogen to hydrogen. The captured carbon dioxide can be directly converted to carbon monoxide. So from the novel IACC technology, we can see that no carbon dioxide released from the system.
Which event?
And then we can check some very interesting, excellent results here. We can
Perhaps.
see that for the conventional
No, we only have two sponsors.
with the
That's
for the
all.
benchmark,
Yes, only
we
the
can see the
event.
carbon dioxide emission achieved 0.95 unit. And in our IACC technology, you see no carbon dioxide emission. And for the hydrogenation step, is also the carbon dioxide conversion step, and we can see that we achieved 0.95 carbon monoxide production. And we also found that this technology is quite stable. Like after 5 cycles, we can still achieve zero carbon dioxide emission during the whole process. And we can think that the carbon dioxide conversion is quite stable at almost 100, but the carbon monoxide selectivity is decreased from 98% to 88%. So the second work is ultra low carbon dioxide emission for biomass gasification using air and nearly 100% carbon dioxide capture and conversion. In this work, we further update the IACC technology. We use more cost-effective possible oxide-based material. It's with the marble powder and the gasification air, and in this work we achieved more excellent carbon dioxide conversion and carbon monoxide selectivity rate. And we do more precise condition in this work. We found that optimal parameters for the IACC technology is that the marble feed mass is 6 grams and the temperature for the hydrogenation is 550 degrees. And if you want to check more details about the IACC technology, you can check the publication here. And for the conclusion, I would like to say that the IACC technology increases the carbon dioxide capture and the carbon dioxide utilization by employing the simple and cost-effective diaphragms as the both solvent and catalyst in one single reactor under the same conditionals, and it's achieved very huge advantages over the CCU technology. And for the IACC technology, it takes the advantage of the ICCU to address the significant carbon dioxide emission associated with the traditional biomass gasification and to achieve the production of high-quality thin gas with zero carbon dioxide emission throughout all the process. And at the end, I would like to acknowledge the great supervision from my supervisor, Professor Wu, and the kind help from all the members of our research group and the founders here. And that's all for my presentation. Thank you.
So we have maybe 1 minute for a quick speaker question. Any questions?
I know that biomass gasification usually has quite a lot of issues with tar formation. I was just wondering be considered if that tar formation?
Tar information.
Like tar, like solid carbon.
Solid carbon. Yeah.
Yeah, it can be quite a big issue in gasification technologies. How did you deal with that?
Okay. I could cause the time limit. I did show my experiment setup. You know, in our project, the biomass is all the burned in the two furnace reactors, and the biomass is heated in the up furnace in a container. So the carbon products can be, residue can be made here, and the gas production can be goes through here to react with the marble. So the marble can not affected by the carbon residues.
Right, thank you very much once again. So let us all meet in 15 minutes. So next, the keynote speaker is going to be in 15 minutes, let's say 10 to 12. So please help yourself outside. And Kadir, if you're online, our online presenter, could you please just stay on the line so we can set you up proper before your talk? Thank you.
Yeah. No, I haven't read the email. Okay, if
you could message to me on Teams. Yeah, that's probably easiest.
Having this thing, I can load it in.
I can. Just drop it to me on Teams.
Yeah, I'm trying to find Kadir. Hi, Kadir. If you're online, can you please unmute yourself?
打针。
什么打针？
哦，没事，就晚点。
晚就很正常，这趟航班正常嘛。
看人尽量做。
晚了拍下来，又不就回不去了。没事。
The appropriate sessions, yeah. Okay, thank
主要
you.
是直播这个东西有问题了，我这电脑就我的 OneDrive 就总是 crash，连 Word 都打不开。
内存爆了吧？
没有，我的内存很多，还有600多个 GB 呢。
不，那个占用内存不是那个
Good， 不是固态硬盘，
不是固态硬盘，就是那个 RAM 处理内存。 运行内存。
Let me know if it doesn't work. I can send it in another way.
No, it's absolutely fine. I just need to open. I can open.
就是比如说你手机这儿有一个这个，就是这个你可能8G 这个视频清晰度比较高，就起爆了，很有可能。然后网站不跨时。
Sorry. Somebody called it.
我的 OneDrive
你看 OBS 不用吗？这电脑我
Sorry, somebody? Yes, it's here. The person who's presenting from Manchester right now.
几号电脑也有吗？
She is
你
online.
自己装上去了。
She's not
对，我
responding
装上去。
to.
我那天修相机，然后看能不能把一个相机的显示器连到电脑上，没搞了半天，然后没搞上。这个东西居然给我通过了。
Thanks for presenting online. Would you grab something?
No, thank you.
哪个老师？
上镜了。
哦，上镜了上，他做了好多 in situ 是吧？
啊，不是，他做好多那个模拟，然后他那个就是他通过热力学的方法把那个做一个什么分子门一样的东西，然后选择进来一些分子能通过，可能就一个特定的温度区间，这个分子能通过。
尚老师做的蛮好的。就这个 memory 吗？
啊，对，有，哎，那应该不应该，你36G 怎么可能快？
是吧？这个是固态硬盘，这个 HD。
对，哦，怪不得我靠，你电脑这么好，那不愧是3000多，那应该不会被占。你这多少分辨率？
应该是 OneDrive 有问题，就是我的 OneDrive 出问题了，可能。All right, ready for the talk?
Are you going to chair the last session? Do you think
Yes.
there's a chance I could swap with Leila?
Yeah, if you want to swap, yeah, that's fine. I don't mind. Have you spoke with Leila?
No, I don't know who is.
Ah, okay.
I don't know who is She was. It's at my train time. All right.
Do you? Can you hear us?
Just right here.
Yeah, we are in the same lesson.
Yes, unfortunately I cannot put your session because I have to leave recording and my bus at 4. Yes, so I have to leave here before it's too close for my...
Or maybe swap with the second speaker.
Yeah, maybe they
I think he or she probably is here. You can swap with it. But I don't know who is
I have to leave earlier because of the bus. My bus is also leaving here. I wanted to see your talk because it's relevant to me.
You have to run?
I have to run. So
It's okay, we have a recording. I'm doing the recording for everything.
From yesterday, actually, some very good talks that I missed because. Alright, I will try to find personally.
Yeah, maybe.
Sorry, I
Speak with Salman. Do you know who is guy? Because the Paula is going to catch the train. She wants to swipe the top. Yes, we know everything. Thank you. Thank you.
Can you be able to speak up?
yes. Good morning.
Okay, thank you very much. I'm going to try to make it a bit louder here inside, but yeah, we can see your screen, so all is good there. Thank you.
Okay, and I will increase my volume here.
Oh, yeah, that's much better. Thank you. Fantastic.
Like Manchester is just kind of
你吃点东西，喝点啥？
没有，我吃太多了。哎，你可以尝尝那个咖啡兑橙汁。
不行，橙汁儿我喝不了。
哦，那没事。
我感觉我都10几年没喝过橙汁了。
可以。This.
Connect online for the presentation.
他那个班长好像搬过了，你知道吗？
哦，对，早上搬的嘛。
啊，对，昨天早上搬。
嗯。
相当于大概3点多就结束，反正我们也不着急。
哦，肯定要拖延一点的，就是讲着讲着就多了。
讲到4点。
咱就早哎。
我们今天浪去12点了，后面是12点。
Can you please stop sharing your screen?
啥东西是开始了 ？Lunch 已经开始了，咱不是老晚了吗？
那个人说他接到了星期六12点。
哦，那是不是他们学校估计就安排错了？没事，反正跟着他们想吃就给他们吃呗。你们先吃，你们这么辛苦。 他估计定的时候安排错了，知道吗？
我们先把油炸的下去。你们要我帮忙的？
那不用，没事，你吃你的。
我没事，我找你抽根烟。
啊，我是想去来着，但是我看这会儿人太多，
怕被拿掉。
应该也没人拿吧？
谁拿？不是在排的。
By using different document types, I can fine-tune the threshold. For example, when you have that will correspond to higher. So the reason and you can calculate at lower temperature.
Yeah, I used to do it.
Yeah. And usually we like to So if you have water, obviously it will be changed because in the brand, the calculation maybe not really kind of so in zero line for gas separation, we always have green line gas mixture.
Yeah, it's pretty bad. You can imagine if two molecules have quite similar reaction structure. One is larger than the other. So the larger one will interact catably to a larger extent. So that is possible to manage. So you will see a difference in the understanding and difference in structure. I think it's like just but if you use dry ice even CO2 can be blocked. And also in the early lecture I showed that carbon high, very high gas
separate those technologies and being produced elsewhere, and that's where the money goes, and that that's UK PLC down. It's interesting to understand why that's generally all of the material we're using from their contribution to the project.
Until now, we have not found suitable capital resources that can but actually, in our recent work, we found that we have easy when we find actually use like silver lining.
So you haven't done the contract?
Yeah, we can sometimes. Usually we use that based on the freezer. So most of the time we use silver to have stronger binding ability to
I don't know if it's exercise. I was a photo. The professor's like, oh, I had a meeting with those guys. Well, I think it's more of some of the like this stuff. Okay. It's like going on. All of them pushing to get this stuff here as fast as possible.
So at least for me, like everything is so far away.
We're trying to remember who's taken it from her team, but there's so many teams in Desmond. I think the thought also was that the first little project was a base project and then changed after one, which was a lot of fun.
你是到时候开会，我们走人现场，你应该清楚。好好，
下次见。
再见，拜拜拜，保重啊。
你也是。拜
拜。
Can you try to pull it?
Hello?
This one.
Okay.
Should be.
Okay.
Yeah.
Just use this one, right? The keyboard.
Hello. So welcome everyone back to our now nearly afternoon session. And we are going to start today with our keynote speaker, Lisa Sun from Surface Measurement Systems, who will tell us about the impacts of humidity in the CO2 adsorption process and insights into and challenges into materials.
Yep.
Thank you, Lisa.
Yeah, thank you for the introduction. I'm Lisa Sun from Surface Measurement System. I really work as an instrumentation scientist. And today I will do something about the influence of the relative humidity on the CO2 capture on the porous materials. Here's about the climate change, the global warming and technologies, as well as the instrument in our company for the carbon capture. And I will also use some case study to show how to evaluate the materials. So first of all, for our company. Our company is called Surface Measurement System, and it was founded in 1990 by Professor Darrell Williams from Imperial College. And in 1991, we have the first water suction gravel in the world. And after more than 30 years, we have a series of different instruments, including the gravimetric method, like the DVS systems, as well as the IGC and the breakthrough analyzers for the gas absorption, separation, as well as the sample categorizations. And globally, we have different branches, like in UK, US, India, Germany, in China, as well as some categorization laboratories in India and UK. And back to our today's topic on the CCS, carbon capture and storage. So nowadays it is very popular, and more people are developing the novel materials and technologies to for the carbon capture. And they want to capture the CO2 either directly from the air or the emission from the industry and for further transport or further storage. And by doing this, they want to mitigate the climate change, meet the climate targets, and finally to achieve a better life. Typically, the sources for carbon dioxide capture includes two sources. One is a direct air capture, and the another one is from the industries, the emissions. And the challenges of applications including the low CO2 concentration. For example, in the air, concentration is around 400 ppm, and for the post-combustion, it is 3 to 50%. And another challenge is the presence of water. So when we talk about the capture CO2, we want to selectively absorb CO2 from the gas mixture. Besides CO2 uptake on the material, we also need to consider the absorption of other components in the gas mixture. For example, mixture, the most competitive component. For some material, it can even destroy the structure, for example, the mold material. So it is very and the absorption, other technologies, absorption, well, high selectivity, the low cost, the higher flexibility, and environmental friendly. More and more people are choosing. And it's the pathway, typical pathway, how you develop the material and finally you use it for the carbon capture. And first, you develop based on several criteria. For example, the CO2 activity, it directly relates to how much sample you use to amount of CO2 molecules. The CO2 capture, we want to reuse the solvents for many times, and that relates to the regeneration. So I would like to mention for the selectivity and regeneration, it should be a trade-off, because if activity, that means a higher affinity towards the CO2 molecules, and it's a little higher energy, like the ultra low pressure or temperature for the regeneration. So the stability, like the stability or the hydrostability, it's very important as well. Like the kinetics, that is very important, like Professor Jin Shang mentioned, that is a very key factor for the gas separation. And in this presentation, I will mainly you develop your materials. We'll need to conduct some experiment to evaluate the performance, like measuring the isotherm as well as to measure the breakthrough curves or the absorption kinetics. And I will show instrument in this part. And here for the capture a lot of, including zeolite, graphene, etc. So for different materials, they have some material have the high capacity, on the other hand may do not have the high stability for the stage. And here is the instrument, like the DVS system, as I mentioned, that is a gravimetric method. And the mechanism is we use the balance to measure the gas uptake for the during the absorption process. And they also have the breakthrough analyzer for the solid material as well as for the gas production. And maybe I spent a little bit time to introduce the brief introduction of the DVS system. So we use the balance and we put the sample here inside and we purge the gas inside. After that, if it's the gas uptake, you can straightforward to see the. It is a very straightforward way to record the kinetics simultaneously, and it is much easier compared with the volumetric method. And here is some data. Like I mentioned, when you change the gas concentration, you directly have the gas uptake like this. And this one, if you plot the final uptake of each step, you can have the isotherm on that. So you have structures or the absorption or desorption behaviors. And this system, we have two systems. One is the vacuum system. This one, we use the vacuum pump to change the gas concentration. Want to go to the details. And the another one is the flow system. We use the carrier gas to change the gas concentrations to make the gas mixtures. And by using this one, it can be very easy the gas concentration of CO2 as well as the relative humidity temperature. And the incubator temperature is well controlled. So for the measurement, it is very stable and you can get very good, very accurate. And for this one, we also have the options. You can put some hyphenations like the Raman and NIR or camera here. And by doing this, you can start absorption as insane, and it's very good to mechanism. And here the picture we capture from the camera. And the next product is the BTA breakthrough analyzer. It is very simple. So you just put the sample in the column and purge the gas, and afterwards you use the sensor to the gas concentration. And by using this one, I would say this one is more related to the realistic stage. So after you screen the materials like the isotherms, CO2 uptake or selectivity, you will for the real-world applications. And by using this way, you can evaluate the separation performance of the material. Take up how much water was absorbed in the material. And here is the schematic of this system. So using this one, you can generate very uniform mixture for the experiment. And after we have the two column options, you can load the two columns simultaneously to save your time. And afterwards, we have a series of detectors. And if your application is on the capture or VOC capture, our instrument is smart enough because you do not need to connect the exhauster to the mass spec for further determination. Use some case studies. It's 39 zeolites.
不知道，反正这趟航班我下个地方老晚。
So for this one, I believe all of you are very familiar with this. People want to capture the CO2 from the flue gas, and the condition of this application is CO2 concentration is 3 to 50% and very high relative.
然后硬生生没给我落在伦敦，也给我停法国去了。他兜了一圈都兜回来了，然后又兜到法国的那个机场停在那。
But it's still not be
没有，你然后在那个机场你得等，我都不知道我都睡了好几轮了，然后再倒回来。
And I will show you the data. First with the isotherms at different temperature, 25 and 40 degrees using the DBS vacuum. And find out the CO2 uptake. It's quite high on this material, and especially within this range we are interested in. And here is the kinetics of the absorption process, and by recording the data, you can have very straightforward feeling.
像这种的话，我感觉是要赔张机票。
And they measure the water.
对，因为没有过夜，
These two
就是如果你
temperatures
下飞机
define
过
that
夜，
the
他
water
可能会说
capacity is quite
或者
high,
耽误了
and
一
it
天，
is
还要赔你工时啊，或者是住的。
看原因，有可能他是说什么？
对，然后
也 also collaborating,
或者是航空管制，这
they
种的话
also measure
都不管。
water isotherm and reported are very consistent, and that
睡一觉，我说该落地了，咋一看这咋出法国去了？
So that we conduct the co-suction of
你到了那
CO2.
个手机是不是？
So
然后它不停在那
experiment,
里。
we use 5% of RH, the background, and we increase the CO2 concentration here. And here is the curve. You can see that actually at the beginning, that zero CO2 concentration, only 5% of RH, it already reached to this high level.
没打扰。
Towards when we increase the CO2 concentration, there is
对，今天这不咱试的那个YouTube 直
That
播，
means
这次试一试，然后接下来的话，咱们会
should
尽量
release to the
多
water,
去
and
说
that to the hydrophilic
镜子还是不反正啊，英国好
feature
多
of
地
the
方用的是
material
镜
with
子，
the
然后
presence
就
of
习惯镜子就
CO2,
懒得登。
well,
想着
negligible
YouTube 的
CO2.
话，可能是不是好多人更方便一点？
Ethics during the exercise, and in each
挺好的，我一直想要
you can
当个
also
YouTuber，
have there
现
is
在
a
终
little
于
bit
吴老
change
师
here,
让我梦想
and
成
by
真了。
你真的假的？给你
this
搞个皮
data, you
套
can。have some sense. Maybe there are something like replacement
对
or，whatever
我那个你
reaction
看
is
这不上道
happening.
了吗？
我给你搞个皮套。
Through this
我
data,
就
you
一直想弄
can
来着，一
but
直没
if
想
you
好，总要有
combine
个
with
契
some
机
easy
是
to
真的？那
measurement,
你直播
you
讲啥
will
呀？讲学术内
对
容。
YouTuber 不一定要直播
Copy
，YouTuber 可
like
以做很多视频，
competitive
然后你后续上传嘛。
OK。
And after that, we use breath analyzer to evaluate the separate performance. We first measure the CO2 absorption under the dry condition, that is 15% of CO2, and we compare with the ISO that is
是吧？按
consistent.
那不知道是正不
That
是
means the high accuracy of the BTA.
不是。
Afterwards,
那咱可以。
of water uptake at different relative humidities, and we conducted the consumption of CO2 and water. And from this data, you can find that water there is negligible CO2 uptake, and hence here that means for this material, it is highly hydrophilic and it with water during the absorption. And here is the capacity of comparing the dry and wet conditions, and you can
哦，她是个女的。
it is
安娜嘛。
the regeneration. So we increase the temperature from ambient to 200 degrees C. And during this process, you find that the CO2 and water are dissolved from the material. And from this data, you can, well, if you calculate the desorption capacity, you can compare with the absorption capacity and to see absorption. And another information is the temperature of these peaks. So if the molecules dissolve at low temperature, that means a weak direction. But dissolve at the high temperature, that can tell you something like maybe they have the different size with different strength.
他是他老师第一个学生。
the material is very stable, and the suction on this material is very good. The conditions or under the heating.
这个行业就是基本上和材料什么的就一样，这个卷这样子资历，当时找教职应该是很难的。
One of the challenge of the BT measurement is when we do some measurement, if the of one of component is small, to get capacity of this component. You can find the data here. For water, the standard deviation is very small, but for CO2 it is not. There are some reasons. For example, when you conducting the BT experiments, you need to subtract the blank, and another one you need to create the area here. So if the area here is very small, it is very hard to get accurate integration. And so you do this measurement, you can use the same condition and use the DVS system to do the measurement. Doing this, you will have the overall uptake of CO2 and water. And water, you read here, accurately guys. And this is very important to calculate the structure. This condition is the CO2 concentration is 400 ppm, the temperature is ambient, and salinity. So from the isotherm, we find that the CO2 capacity at around 400 ppm, well, that is satisfactory, around 0. millimole per gram. On this material, we find that with the presence of water, no CO2. And this is with the results. So as a conclusion of this material, it is CO2 capacity under the dry condition, as well as very stable. But if you want to directly use it in the real world application like the DAC or PCC post-combustion, a good candidate. And of our collaborator, what they want to do, they want to build 2 columns, and one they put this water. For another column, they continue use this material to capture CO2, and by doing this,
这感觉不像是个英国妹子。
the next MOF material, and this is the material from our collaborator, the normal MOF. This type of material, they have we first the CO2 isotherm at 25 and 40 degrees, and you find that for the CO2 capacity, it is quite high among the material, above 4 millimole per gram, and the kinetics very good,
也是非常好
possible under the ambient condition. Dry. It's the cyclic test, and you can find that the cyclic test there is almost decrease in the capacity. The kinetics, no matter the disruption kinetics, it can reach to equilibrium less than 5 minutes. It is very good. But after we introduce water in between the cyclic test, for example, from 25 to 40 to 50 to 75 to 90, and gradually with some changes. For example, here it is start to become non-reversible. It cannot be fully steps, and finally, when the relative humidity reaches to like 75% or 90%, the structure destroyed. So the conclusion of this material is very good performance in terms of the capacity or the kinetics or the test, but when it's water, it is stable enough. And the third material, that is resin. So this material now is very popular to be used in the DAC direct air capture applications because it has amino groups, and with the presence of water, it can enhance the. And here we first measure the CO2 and water isotherms, and we find that it is different compared to Cetinex or the MOFs because it is not reversible. You can find here. And that means if you do the disruption under the ambient condition, it cannot fully regenerate the
哎，
material.
不过今天曼城来好多人。
Further energy like heating for the regeneration, and that is again relates to the affinity of material to the molecules. And here, it's at different temperature. And we also calculate the heat absorption using the isotherm we measured, and we find that the heat absorption is quite high. And after that, we introduce the water during the CO2 suction. We want to see the water, it can enhance or not. And the data over there shows that with the presence of water, the capacity enhanced. After we do the desuction, we first, I want to find proper temperature for regeneration. So I just set the temperature ambient to 100 degrees. And I found that around that something, it can be fully regenerated. And I use that temperature. Afterwards, we use the FTIR to check the peaks. And from the peaks, we find that it seems after the regeneration, all the CO2 related peaks disappears, and maybe it is fully regenerated. And after we repeat the assumption for the regenerated sample, and here is a comparison, you can find that the capacity decreases. And this, at the beginning, I think maybe it is only due to it lost some assumption sites during the size. And afterwards, I compared this assumption curve with the assumption curve. The water also decreases. So the conclusion of this material, after we do the regeneration, both CO2 and water assumption site, it have affinity lost. So here is the conclusion of these three different materials. The impact of water are different. It's, well, I should say not that negligible, because the structure is good, but for most material, the structure can be destroyed by the humidity. But for levitate, the resin, with the presence of water, it can enhance the CO2 absorption. And like the regeneration or the stability, another concern of this material. Okay, so finally, I will introduce our life solution. If you want some tools, knowledge, or support for the carbon capture package, contact us. And here are the package, including different instruments. If you want, it is a very good solution. Like the contract test, if you want to categorize your sample or do some measurement, feel free to contact us. Very much.
Thank you very much for your presentation. We now have time.
这是不是问题？早上的时候还是 Michael 还问我来着，然后我跟他说最好今天中午开个叫，再不开就没人了。
Carbon.
我反正提了，这不是我的，又不是我的，我已经
Yeah, so maybe your question related to the stability, right?
看 Michael 不是那个老师，不是 Michael Brunel 的 Michael 是萨里。
Yeah, exactly.
Michael
Yeah.
其实应该昨天人多，今天就没几个人了，看着人都走了。
对，
一会儿学生们也走。
Some of the conditions of the output streams to
我们
be
看到
sure
别人我们才
the
能学
components
习。
support the CO2 absorption. For example, for some of the processes, the flue gases that we now have
对，第一天做的最
or
好的。
even pressurized.
We only have the ambient pressure. And for temperature, we have the local preheater. For example, the DVS system, it can go up to 300 degrees C. And for the BTA, breakthrough analyzer, it can go up to like 450 or 500 degrees C. You can do the measurement at high temperature. But high pressure, no. On the other hand, I would like to mention, if you want to evaluate some high pressure process, because the CO2 partial pressure is not the high pressure. If you convert, I mean the absolute pressure of CO2. For example, if you want to do a suction of 5, finally the pressure of CO2 is 75 bar, is something like that. And in that case, we can also do the measurement for this process. Yeah.
One of my own.
Yeah, it's okay.
In your presentation, you said that the 0.5 millimole per gram, despite being more acceptable or DAC conditions. And my question is, so how do you define that being satisfactory for DAC?
Well, we just compare with the literature. They badly use some material like this, but that is the dry condition, not the realistic. Under realistic, nothing. Yeah.
We thank you very much.
Thank you.
Round of applause.
Thank you.
So our next presenter is joining us online. And hopefully, Gadir, can you unmute yourself?
Yes.
You give me a moment on this end to pair everything so that the participants would be able to see. So fantastic. So yes, our next presenter is Gadir Al-Hamar from the University of Manchester. Welcome, Gadir. The floor is yours.
Hi, my name is Gadir, and I am a student at the University of Manchester, and I am glad today to present my work, chemical looping assist propylene or propene production. First of all, propylene is a valuable intermediate chemical compound which has a broad industrial application, like shown in Figure 1. This material is mainly produced as a byproduct in steam cracker or fluid catalytic cracking of naphtha. And because of recently shifting from naphtha to natural gas, then the amount of propylene produced has been decreases. This motivated to find another or propose another on-purpose process, such as propane dehydrogenation. This process, like all other process, has a company with a lot of carbon dioxide emission, which already has amount of about 33 billion tons on 2021. Now we will go to explain propane dehydrogenation process. This process is on-purpose process. That means it is going to produce a compound, mainly one compound, rather than produce a mixture of compound. There is two kinds of this process: the propane catalytic dehydrogenation process and the oxidative propane dehydrogenation process. The first one, it is an endothermic process which needs for a heat supply, as shown in equation 1, while the second process occurs in the presence of oxygen, and it is an exothermic process. Because of the simplicity of the propane catalytic dehydrogenation process and the economic benefit rising from the difference in price between propane and propene, then has been commercialized. But it also has some disadvantage. So the main disadvantage for propane catalytic dehydrogenation, it is endothermic process which need to be occur at high temperature. This high temperature will lead to increase the rate of coke formation as well as side reaction, and also will emitted amount of carbon dioxide. While for the oxidative propane dehydrogenation, the main disadvantage is the presence of oxygen, which make the reaction difficult to be managed, as well as the oxygen could be burned the olefin produced from this process. That motivated us to find another way in order to produce propane, and so we will go a little further chemical looping composition, and we will say the main advantage of integrated chemical looping with the propane dehydrogenation process. For the chemical grouping composition, it is autothermal process, and it could be considered as carbon dioxide capture process. In this process, the main reaction, which is the composition reaction, will be divided into reactor, and we were going to use solid oxygen carrier in order to transfer the oxygen required from the air reactor to the fuel reactor. So the process mainly will divide the reaction into two steps. The first of all, we have the oxygen carrier, which will be oxidized in air reactor, and all the product stream from the air reactor will be depleted here, only nitrogen. Then the solid oxygen carrier will be transferred heat as well as oxygen, as shown in figure 3 in the line red and the red line. This way, this will make the heat required for the reduction process, and the fuel reactor will make the oxygen available for the reaction in the fuel reactor, as well as the heat required for that reaction. And the main product from this process or this fuel, it will be only CO2 with water, which can be easily separated from each other and by using a simple flash buzzer rather than use the amine scrubbing process, which need a large amount of energy. So this is the main advantage of using chemical lubricant composition to end the process in order to reduce the amount of carbon dioxide emission. So in order to have a very good performance in this process, we need to know some of the important characterization for the oxygen carrier. So it should have a high element carrying capacity, high reduction, oxidation rate, should have a very good selectivity toward water or carbon dioxide, mean complete composition, good recyclability, good stability, high melting temperature in order to have a good stability and recyclability for long cycle, like 30 cycles. And also we need it to be resistant to toxics and contamination. Figure 4, which is modified Ellingham diagram, it is divided the oxygen carrier solid into mainly 4 sections. All the oxygen carrier above the line, reaction line 1, will be suitable, have very good oxidizing properties, and will be suitable for chemical lubricant composition process, complete composition, while all oxygen carrier above between the line 1 and 2 will be suitable for partial oxidation reaction with a noticeable amount of water. Between reaction line 2 and 3, all the oxygen carrier will be suitable for reducing syngas, and finally all the oxygen carrier under line 3, reaction line 3 and 4 will be just inert material and could be used as a support for other active site loading on it. What we have been doing in our work is make a simulation of the commercial oleflex process using SPN Plus for the propan dehydrogenation, catalytic propan dehydrogenation process. And first of all, we have fresh propane, which sent to deep utilizer in order to get rid of the butane available in the stream. After that, it has been mixed in heat exchanger 1 in order with the product stream in order to take the advantage of the heat available in the system. After mixing with after heat exchange with the product stream, it will be mixed with hydrogen, sent to furnace F01 in order to increase the temperature of the stream to 650 Celsius, which is the reaction temperature, and sent to reactor 1, which operates at 1.5 atom. After that, it is followed by a series of reactor, and the final product from reactor 4 will be, as I mentioned before, exchange heat with the feed, and it is more cold and heat exchanger 2 in order to send to separation flash 1. And this flash, the water will be separated from the other gas and sent to compressor, which is C01, in order to increase the pressure of that stream, which is the gas stream, up to 20 atom. After that, the stream will be sent to dryer D01, in order to get the to get rid of the moisture available in that stream. After the compression section, then we will go to the cryogenic section. In the cryogenic section, which is first of all, the temperature will be decreases to minus 30 Celsius, sent to flash vessel 2, in order to separation natural gas hydrogen in the upstream from ethane, ethene, propane, propene in the downstream, and the temperature of the top stream from vessel 2 further decreases to minus 95 in order to increase the recovery of propylene and propane to 99.4, 99.1 respectively. Finally, we will, after the... No, not that. After that, we will normalize the temperature in heat exchanger 5, set to pressure swing absorption unit in order to separation hydrogen from the other gases. And while the downstream from heat exchanger 6, the temperature of that stream will be first decreases because separation ethane, ethene, propane, propylene will always need high temperature, high pressure, low temperature. That's why we have been set the heat exchanger 6 to about minus 30 with the pressure about 18 atoms, sent to the de-ethanizer, which is T02, and after that the bottom stream, which is propane propene, sent to the de-propanizer, which is T03, in order to separate the propane from propene. This is the commercial one, while the other process, which is chemical lubricant composition integrated with the propane dehydrogenation, almost have the same section. First of all, the debutanizer, and the second section, which is the downstream separation, while the main difference is the reaction section, or called the upstream section. As it is appear that first of all, fresh propane will be sent to the debutanizer, and then the product stream will be exchanged heat with the feed, and then it will be mixed with the red line. The red line represented the solid oxygen carrier that first of all it will not be on the system, then it will be recycled. So first of all, we will mix propane with the solid catalysis, sent to the heat exchanger in order to increase the temperature. After that, it will be sent to the propane dehydrogenation reaction section, and the product will be sent to cyclone. The cyclone will separate the product, which go to the downstream separation from the solid. In the air reactor, the solid will be regenerated because it will be already reduced in the reduced form, and it will be oxidized with air in order to get the oxidized form. After the oxidized form, the nitrogen will be separated from the solid, and the solid will be sent to the fuel reactor in order to then be reduced by natural gas. And after that, all what we have is the water and carbon dioxide, which will be easily separated from in the last flash vessel, and the cyclone will recycle the oxygen carrier, which has a high temperature, and after the first cycle, the first heat exchanger before the reaction will has a heat duty of 0. So in this way, we have been reduce the amount consumed in the process. For our result, S1 Plus results, mainly we have this approximately the same production rate, because we want to make a comparison. So for the production, it is mainly the same, but the output for the chemical lubricant propane dehydrogenation of the hydrogen, which could be by sale as byproduct, the purity approximately the same, and it was high for the propylene 99.91, and for the hydrogen 99.99. The same conversion for the two processes was 35.4.5. Approximately the same selectivity. The main difference between the two processes is the energy consumption in the propane dehydrogenation was 5.7 gigajoules per ton propylene produced, while for the chemical looping propane dehydrogenation was 3.4 gigajoule per ton of propylene produced. But while for the carbon dioxide emission in the first one, which is the commercial one, 2.78 ton of CO2 produced per each ton of propylene, while it was about 0.753 ton for the CO2 per ton of propylene. Finally, we have our conclusion. The main advantage of coupling or integrated chemical looping composition with the propane dehydrogenation is first of all avoid carbon dioxide contamination with nitrogen. So we will no longer need to use the amine scrubbing, which is known that it is need a large amount of energy. Then cut off the amount of energy required for polypropylene production because the solid carrier will transfer heat for the required for the endothermic reaction from the redox. Is the upstream energy consumption was 5.7 gigaton per gigajoule per ton propylene, whereas it is only was 3.4 gigajoule ton per propylene. And finally, the amount of carbon dioxide has been emitted reduced about by 72.5%, which is the main advantage of our work. Thank you so much for your listening today. Thanks.
可以呀、赶明儿我给你凑一凑。我这个人就是主观能动性不行，就其实我对很多事情都很感兴趣，但是我就是自己就不想去尝试。我们那儿就是好多高尔夫球场，对，明年还可以安排高尔夫。对，明年可以安排高尔夫。就是我老想着我去高尔夫，是不是？那都是那个高尔夫球场，然后又便宜，是不是？
production and not to pit them against you, but what do you think is the low-hanging fruit of engineering in this case? Which technology would lend with the metal looping? Propylene or hydrogen production?
Sorry, could you just repeat the question?
So if we have a look at the two big, let's say, separate branches, in one case we are producing hydrogen, right? Most of the colleagues in Manchester are doing, versus your approach to using propylene.
Okay.
What would you think would be
对，就可能计划
easier
安
to
排
deploy?
好要去哪儿都感受一下。我不行，我做攻略也不行。
就王田特别喜欢记账，欣然特别喜欢做攻略。
然后我另外俩学生，那可以啊。不是不是，会计是吴老师的学生就在听。
If I understand it well,
挺好的，挺好的，各有所长。
It is
我就喜欢跟着别人溜。
to do is to find a way
对，我是啥都行。
to produce either
对，我也
propylene
啥
or
都不挑，我就跟着溜。
commercially with a little amount of carbon dioxide and a little amount of energy consumption. And I am sorry, really sorry if I didn't answer your question.
No, it's be fine. Very much. So a round of applause for our online speaker.
我感觉回阿伯丁我们都得穿袄了。哎，天恒，你要走？衣服了吗？没，我这不是。
啥温度？
反正最近都不用，没外套都不咋穿。是吗？你就晚上可能穿一会儿。就是现在春暖花开的时候。
为啥我那个风衣能走冬天穿到秋天，再穿到？
我棉袄我就能穿半年。我阿伯丁老省钱了，我说不用买衣服，就一个袄穿，一直穿完事儿。
在香港是全夏装，然后一来
全是就是秋冬装，
全秋冬。
我们有个同事去年
，Hello from me too.
今年1月份入职的，他就是香港过来的。
Kind of talk to the ones that
这同事可逗，一中国男孩是吧？然后他老家是东北那个袁鑫老师，Triple E 的。然后他来，因为他来之前就是联系过我们，所以就是也算是半个认识吧。所以来之后我们就出去吃饭，但是因为不是正是那嗖的冷啊。然后我们一块吃饭，有一天就是他主要是没有厚衣服，就是他是这种不是。 他是老家东北，但是从在北京住了蛮多年，大学在北京，但是后来新加坡那边做活后，是吧？然后就在那个香港，就是去阿伯丁纪念香港日子，对，他是从香港直接飞阿伯丁的。我也觉得，然后他穿了一个就是我感觉我是秋天才会穿的，特别特别薄的那种厚的外套。就不是袄那种。我那天晚上出去，我感觉冷的就是整个人都是抖。
Kind of have a look at where this CO2 comes from. It's nearly impossible at the moment. So we're thinking what we managed to do something with this CO2. And there are a lot of things that you can do with it, and there are many industries that you can use it. And so in my group, we do try to make different things from CO2. This could be carbon, this could be methane, this could be methanol. But today I'm just about there is one reason.
我之前在香港待的时候，就过年回家就穿一条。
And this, I think we heard about this yesterday, where we said that traditional fisher, we know about it, right? And so we could kind of utilize our infrastructure to do the same for CO2. Of course, there's a lot more problems coming to that. With CO2 instead of CO, but researchers have been trying to look at what kind of would be possible to use this. And they have come up to an understanding that there are two systems that are the most hot, let's say, or the most promising. And this is the copper zinc system and the nickel gallium system. One is more tricky because you basically need to have the nickel 5 gallium 3 phase, while others are a bit inactive. But overall, this one. So we have thought about probably a solution could be the solution to this. You see what I did there, right? And so probably some about this all the time, but the catalyst that we usually use in many catalytic applications are impregnated catalysts.
其实就是有的时候那个音调不太一样。
对我们那个你们老家跟河南话区别就是我们做过油画都会往上提一下。
In extrusion, we dope active phase inside the oxide support in solid solution, and then we push it to the surface in the form of metallic.
不要跟别人吵架，我说我没吵架，那一说的话，本来我嗓门可能也就大了点儿。
But the traditional ones sit kind of relaxed on the surface supports, while the exhaust are kind of confined because they.
这样。
And that
那感觉没什么东北口音。
对他们说没有，但我觉得很奇怪，我觉得我有东北口音。
Or that's how they look.
你还说我有东北口音？
They look quite impressive just because you have a huge control over the size, the population, and the homogeneity. And because, like I said, they are half embedded. A lot of people say 1/3, but depends on what kind of metal. And they're also crystallographically aligned. That they are like locked in there, they don't go anywhere. And
得现在我学生好几个，
除了我都是东北。
Exchange properties, and we have seen how amazingly
我
they
必
work.
须得保持我
With
河南的口音，
applications,
必须让人
they
认出来
are
我是河
regenerative
南
and they're
人。
agglomeration resistant, as I said, so catalytic application.
我要是说方言就那个啥，但是普通话的话我也不知道。
说方言的问题。
We do change the carbon
可能
deposition
太久了，就是那个啥，我跟着我妹，然后顺着
If you
我就
consider
说
that,
那个啥
it means that probably they're sulfur resistant as well because it is a very similar
你
mechanism.
口音不算重，其实辽宁我觉得口音重。
We thought we would apply
我也听不上人家的口音。
to hydrogenation. And so we made a copper zinc system. There was a prof's guide. If you want, I will tell you the details on the design of that. But basically, we put copper and zinc inside the guide. We made the single phase material, and this is the microstructure of the material. Quite
bulky for a catalyst, porous for a perovskite, I would say. And this is after exsolution. This is the microstructure. It's exactly the same after reduction, pretty much. And then this, you can see, this is the XRD of like phase hooking, which is copper phase here. And I know that this is not really amazing. You can see all these tiny nanoparticles, copper nanoparticles coming on the surface of material. And the average size is, I would say, 2 to 6 nanometers.
这个对，这个是标志性的区别。那你们说二化音呢？
It's a bit about, let's say, 5%. How much we doped in? 0.5%. And of course, does it do anything? Yes, it does. It does produce atmospheric. This is a tiny amount, but like I said, we put a tiny amount just to screen, tiny amount of copper on the surface. But then activation energy. Not anything else that has supported in the literature. And this is after testing, so you can see microstructure is packed and the nanostructure, and again you can see all the small particles being still exactly the same as when the sample was fresh. I would say, okay, surely an impregnated sample would do the same. With same perovskite with a copper zinc, and you can see the bit more to the edges and the same with the copper. The activation area is much high, and this is the same sample after the same exact amount of use. You can see how, as compared to what I showed you before, you can see how burn zinc have agglomerated at specific places in the sample.
我们那边也要婆婆，
How do you do it? That's something we wanted to know.
到时候你婆婆得给你包大红包，已经提早改口，就得是个大红包。
我不是对我说这个，比如说这个是我婆婆，然后但是就见面确实也会很麻烦。
哦，那见面，
和丈母娘这。
Just XPS cannot differentiate between those two, but it can differentiate between 2+. So copper will seem to be the same. We can see this from the Ozempics. And I will not explaining this in detail, but just want to say that this bond here, 1500, that zinc oxide does have an influence in this conversion. It's not just copper that's doing all the work. And briefly, I will mention the nickel gallium is a bit more premature, I would say, our work. So this is how the gallium system works, and you can see this is an SCM picture as compared to the TM that I showed you before, because nickel has bigger particles. So we are in this an SCM as compared to the copper that. And so of experiments here, the A side, the ion effect, the nickel gallium, because of solvent how, right? And we see that we have a different, we can control again the size and the population.
就纯姐，只有这个词吗？
我弟跟我妹叫我老姐，整天都把我叫老了，我都恨死了。
我姐叫我老弟。
To my eyes,
对，老弟咋叫都是对吧？都是小的。我前几个月在家的时候，给我弟读高中，他不是那个住校嘛，然后送东西去了，那不是上这课送的是吧？大门口我就给他递，我就走了，只怕别人不知道多大岁数。再见，老姐，回去小心点儿，老大声了，我的去，那可老了。对。 我不说，人家还以为我是谁，是不是？一说那真老，真是一点情商没有，不知道将来咋找媳妇。
The nickel 5 gallium 3 activities that I talked about before was present in all samples, but in the low field, sorry, in the high field dissolved samples, we also saw gallium oxide. That has been referred to as but it looks something like this is metallic and this is
一个是堂姐，一个表姐。
好像是吧，不是。然后比如说我舅喊我妈就会喊子儿，就是
阿子儿。Who hosts projects together and sees a senior lecturer in this school as well. Pain from Imperial always support me and my group and all the XPS amazing work is.
就是现在是这个 logo 是吧？
And Eleonora in Polytechnic.
这不是那个
who also works a lot on this area, and we've done quite a lot of work together. Of course, the founders, because as you know, without them we cannot do much. And I want to.
这 logo 我也能设计，不
My
用
group
花那么多钱，
they
给我
are
个
always
300-500
take pictures
可以
with
就
me,
行。
but also
还要
without
设计
them they are not. We wouldn't have anything here, and there's one person here who's
对，这一般人不敢啊，是吧？
the work system as well. And thank you for your attention.
之前吧还算是个 logo。
Thank you very much for the presentation. Any questions?
哦，这不挺好看的吗？这个一个英国大不列颠国旗加一个那啥。
Yes.
哎，这不挺好看的吗？
这个
with this.
啊，那这也不大行。
这本来就是它只是个名字的 logo 嘛，这个本身都会有，这个都在保存。这好歹，哎，算了，不说了。
我觉得曼城还挺好看的。
咱不跟帝国理工抗争，人家帝国理工化工排第一，咱不跟他争。
What the CO2 you mean?
这个化工好。
The CO2 was not in ppm level.
说的好，那我就是他得不到的女人。
Yeah, so we haven't done industrial conditions just yet because this we've done higher pressures. Not 50 bar, but like 10, 20 bar, and they don't seem to deactivate. Of course, there is still a lot to be said about like water poisoning, you know, and lower CO2 kinetics, but this is something to look in the future. What I can say is that these materials don't die. So hopefully, something that.
没有，我们北爱跟英格兰有水。 北爱跟英格兰有水啊！
它就那边就一个大岛，上面是北爱，底下是爱。你有签证的话随便过，你没签证的话就
偷偷过。
高速公路这个被抓了以后，
就是他带。
不知道啊，我咋开过了
？Theoretically, because again, this is quite a new method.
前面回国还是回？
There's a lot still to be done, but theoretically, you can exhaust from many oxide matrix. Any metal that you want. So it's about the process, it's not about this particular thing. We've absorbed, like, for example, yeah. Right, it's something very commonly used. And the difference is that instead of just putting the nickel on top and spin it and then calcine it, we just spin everything together and then calcine them. So it's the same cost, I would say. It's just a reduction. You would have to do a reduction in your catalyst either way. So it's more about the material design that would lead you to make this possible more in terms of making that.
但是去年还是哪一年？去年好像因为个什么事儿，然后他们就突然开始严格了，结果爱尔兰的警察局的负责人说，我们去年1年查到的偷渡人数比之前10年加起来的都多。原因其实
因为之前10年没查过，
直接不查。
搞笑的。
爱尔兰是用欧元吗？
我拿的是欧盟的。
哦。
之前。英国不是脱欧吗？英国在脱欧之前，北爱尔兰之前闹过独立，闹独立之后，北爱
是就北爱要独立，还是要跟爱尔兰合并啊？北爱自己要独立。
先不说合并的事儿，至少他要脱离英国。
啊，那苏格兰也干这事儿。
对，后来北爱、欧洲还有英国，搞了个协议，就是北爱暂时留在英国，还算英国，但是它。也是欧盟的一部分，所以说就是北爱尔兰之间的一个边境线
啊，可以。
然后等到英国脱欧了之后，你说那你脱欧了，那我们怎么算？
对呀，那你们怎么算？
后来那个协议就等于就修订了一下，北爱算是个特殊，你既在英国就在欧盟。
OK，好吧。
然后我们现在
退税是
退税国家来分是
不能退税。
但是其他一些像边境，
那你们去
退税怎么操作的？
都是通用。
退税在机场退的。
在给什么？给一个英格兰的地址，不然的话你给北爱尔兰被征签。
写我地址。
因为我们拿着都是英国的
必须退。
退税。买啥东西能退税？就
啥都能退，它有个最低额，几十镑、几十欧就行吧。
就你在机场买多少钱的东西就。
机场退不了，你比如说你再去德国，在德国商场买个什么东西，然后你问他要张退税单，然后他就给你，你在机场的时候把那个单子。
找谁呀？找谁？机场的什么人退税？
机场有个专门，然后管这个，要给你戳个章啥的，还要看一下你的东西，他就。
那比如说我这次回去的时候，我走那个赫拉姆斯特丹，我买了瓶香水，假设。
但你在机场买的已经是免税的香水了。
哦，怪不得。
你申法签的话，
哎，那您是比如说我在阿伯丁买了个香水，然后在阿伯丁机场可以退税。
你在阿伯丁买，在机场你不能，你住在英国你就不能退英国的税，就好像你是中国人，你在中国买的东西，你离开中国你也不能退税。
哦。
是说你比如说你去德国买了个东西，你因为不是德国居民，你只是游客，你不需要交他的这个税 VAT， 所以他把这个 VAT 退给你。
哦，20%的样子是吧？我觉得。
每个国家不一样，有一些是10%，有一些是20%。
那我们来英格兰才能给退。
如果你在德国买个东西回到英国，你是可以退的。
就找谁退呢？找德国人还是找英国人退？
是德国退，你在德国买，你的钱交给德国了，所以说是德国要退给你。那
我不是已经回来了？我就在德国的机场找他退。
对，你要在买东西的时候跟他要退税单，然后。
那吃饭什么的也能退吗？
不能。
啊，只有消费这种。
就有 VAT 的东西，然后消耗品，你在人家德国已经把这个东西吃了就不行。他是说，因为你不是他的居民，你就没有理由要交他这个税。
懂了，就是我比如说在德国买了一个，就随便，比如买了个手机，然后就是2个 VAT。
可以，
哦，这样就在去德国那个机场吃饭。
有一些大的商场可以在商场顶楼就可以办理退税，直接退现金，但是需要一些大的综合性的商场。你只要去哪儿的时候，你小红书里查攻略就行。
那不太适合我，我可能没那么高消费。我搞点吃的。
啊，吃。
然后我上次办美签被 check， 就本来像我这1年。本来像我这种是最简单的，就是公司 sponsor 所有费用，而且我们还有分公司在那边，人家一般全给10年，我他给我check 了，我要给1年。
我都没去过美国，老害怕了。
我上次去波士顿那边，感觉
还行。我怕我走道上，然后是吧？谁那个精神不正常，拿个枪隔着马路给我一枪那个啥？我想我人生如此之。
那边好像还比较安全，
还行。
纽约什么我上次去。
就德克萨斯都比较的野蛮哈。
左西边那些是。我下个月去圣地亚哥，好像就是西边。
小心点，小心点。
就参加那个 IACC 那个会。什么化工？
赶紧吃点东西，趁还有。
我对这些一点
不感兴趣是吧？
感兴趣早上。感兴趣还能等他们出来。
咱就先下手为强。你喝啥？我给你倒吧。那行。那你们公司，你可以不回答，就是不可以不是，我不问工资，我对这个不感兴趣。就是你们公司的 IP 那个大老板，这叫什么？威廉是吧？他占多少？
他什么？
就是你们公司的 IP， 他占多少？
我不懂，就是你刚刚问的那个，我都不懂，就是这些，你给我讲讲。
啊，其实我也不懂啊，就是因为它这个是学校 spin out company， 也就是 IP 不可能是100%属于老师的，甚至都不可能100%属于学校的，对不对？所以这个问题的话，他在 spin out 的时候，他当时要开这个 spin out， 然后当 William 应该是跟学校都是签好的。
多少给学校多少啊？
盈利都是后话，就是这个 IP 到底是谁占多少百分比，然后才牵扯到后边你要如果盈利该怎么分，对不对？前面 IP 的话，这个东西就是明面上面好。
就是那个，就是像这些技术什么 development 这种。
对，就是这个技术本身不属于老师，也不单单属于学校，就学校不可能单独给他卖了，不跟 William 讲 ，William 也不可能单独把这个卖了，然后不跟学校讲，所以他们之间是协商好，然后这个 spin out 才就这个合同必须签好，然后才可以这个 spin out 才能开起来。再加上你们公司做的这么好了之后，是吧？这个肯定还有一些变动。
他俩之间还有没有啥联系？就对学校的公司。
但是当然 William 已经退休了，是吗？
还没有退休。
还没有退。
对。
就学校肯定是占。今天早上那个人他没有回答我问题，他都不回答，是吧？
啊，我是不懂这些，你问这些我当时完全不知道。
我不知道，好，因为我也想着弄这个 spin out， 但是就很麻烦嘛。
我香港就也整老多 startup， 但我觉得那些老师就全都是在这个捞钱，就是因为就写一个 wrong 的 application， 然后就可能一开始是比如说10万，然后下一次可能就100万的这种，就是港币那种。
是，因为公司大家都是想要挣钱。
然后就全都是。就啥没有，我觉得，然后就在淘气，就根本不是像这种。
你这个理解非常深刻，这个也是嘛。我问他到底是卖啥？你们公司好歹是卖仪器的，人家公司是卖的啥嘛？但肯定人家技术是过关的嘛，是吧？
那个early career。他们会 handle 稿子吗？
我老师是想分给他们一些吧。
他们是 review 还是？
他们可以 review， 然后
还是他们找 reviewer， 他们应该
对他们找
reviewer 是吗？
不，他们是 reviewer。
对，他们是 reviewer。
就包括现在所有的 associate 那个 editor， 也不是所有人都会是 handle submission， 吴老师在控制着。
对，我就有一个朋友问我，我忘了，因为我后边就是我会找别人再找 reviewer， 但是我忘了这个 early
啊，ECR 应该现在吴老师还没有那个啥，那这个吴老师肯定要找比较信得过的人，然后比较容易沟通到的，就是联系就立马能找着的，是不是？有的时候要一个个讨论的。ECR 的话，一方面都是资历比较浅的，然后可能有一些就是认识的，隔了好几道人，就有的时候突然想起来的事就找不着，是不是？差不多，没有按几分钟嘛，还行。
挺好呀。
Paula, are you going to swap with the second speaker?
Yeah, with Farsaner. Yeah.
Okay.
So just move me here and then Farsaner.
All right. Okay. Have some lunch.
可以吃点那个炸虾。
赶紧吃。已经这个点儿，今儿得吃好几，今儿没有，生气了，说不定有别的，看看。
对，今天有那个春节里面的虾，
看看，
那虾还挺嫩的。
一点都不感兴趣。
这把萨里的风也赶住了，这个门我再也不想听，我就要给它拆了。
再换点头。
不用，一会儿我就进去了。
哎，
我已经做一上午了，不在乎，再做一个点儿。
啥时候开始来？哦，1点。
估计还按点了啊。
那虾没有了。
我不用，谢谢。你吃，我白天不咋吃东西。
平时也是吗？
我就晚上吃的比较多。白天不咋饿，这一吃就困。
你有90度吗？
我会变一下吗
？90度一点。
我感觉贼瘦。
哎，还是你瘦。
我感觉我肉一点都不少，就是骨架比较小，但是肉真的一点。
你看非常紧实，我都不锻炼，我都不动。
但我看你就感觉不瘦那种。
也不瘦，我肉都你看都裹起来。
我也是肚子。
没了是吗？
不是还有。
昨天这个信号不好，没有加上。
可能那个吃饭的地儿确实是。
我有备注吗？
不好意思，我那个啥。我才发现
奇怪的。
没接受是吗？
不好意思啊，之前也有这种情况。
写备注吧。
朱元。对。昨天我还看这个名，我说朱元。
就差一个档。
你这个想的。
当时并不知道是谁，就看那个。今年还有啥
计划待定的还有，我就怕10月，我估计还得飞趟悉尼，给我吓坏。7月底那边还有个会，我是答应了，但看情况吧。
再飞一趟，也不累死。
完。
11月底还。
你们不是指望着我那个啥的吗？
没有。
我不是在努力。
辛苦。11月底。
对。
哪个老师？哪个会？
还是黄老师要办一个非常大的会，还有 ACB 的主编。
我靠！
我就听着这个，当然 ACB 的主编是其中大佬之一。我心里想，我就要抓着你，我就问你凭啥不给？凭啥？
可以，那你去之前把第2篇也写完，给你投出去。
我就跟他杠。当然，那个就黄老师办的会，就是请的大佬也比较多，就是，但是我一听 ACB， 这不是最近在跟他杠呢，是不是？
他后来回邮件了吗？
他就是不回，所以我硬投的。其实这种情况下，再投上10有8九就退回来直接拒了。
啊。
因为我们是被拒稿了，然后我现在拒稿没有重新邀请，我就又投上去。其实说白了，我就在白费时间。
啊，没事儿。
但他如果再拒，我就还给他写信。我生气啊，因为他不符合常规操作。
对呀。
一个审稿人凭什么拒我？
狗屎。
你要么早点别送审，是不是？
那审稿人而且那英语水平那么稀烂。
那审稿人英语水平不行，那很正常。
我觉得学术水平也未必好，我说
这很正常。但是他提的一些意见，我们还是很中肯，确实是我们是有问题的，被他剪出来了嘛。这点我们只是就是提问题不怕，就是我们能回答他的问题就行了。
Okay.
每个人都会提问题，提问题不怕。如果不提问题的话，那个审稿人就是如果他不提问题 ，editor 都不会要他的意见的。所以不提也是有问题的，人家很中肯，花时间其实也是看了的我们的那个 manuscript， 提了很中肯的意见，这是没有问题。就他们意见我们很容易就 address， 并不是说我们是有一些完全解释不了或者是完全的错误上的信息嘛，对不对？再加上一个审稿人就拒这件事情，那你不符合常规操作。
去他妈的，没事。我反正看到这个，我第一时间不是说沮丧什么，而是就很生气，然后觉得得。
那你以后气的多了，你只要有 review 回来都气，每一次都气。
没事，我不是说那种。
不是我的意思是那个啥，就是这样。当然我现在我跟你讲的时候是这样的，就是但是我看着我也生气。但是你要知道，每个人都是这样。你想有些老师几百篇文章，每一次看到 review 意见都生气。因为这个东西都是大家做学术嘛，你看我做的不爽，我看你做的不爽，一样的。
行了。
别人看你不爽，这也是我看别人做的，我也不爽。
OK。我没想到这个香蕉这么甜，
看起来还
贼甜。昨天我就觉得不好吃，结果吃了就贼甜。
是吧？感觉还没熟嘞，是不是？
甜。
但我个人观点，这是正常，就是因为你自己看不到自己的缺点，才会对自己满意嘛，所以要同行评议，是不是？让别人挑出来你的毛病，确实人家也挑出来一些毛病，对不对？你看我们现在是不是这个更有自信了？
对。
我接受任何批评，但是不接受人身攻击。
攻击啥？
就有些人是无脑人身攻击。是不是？那就是另外那个啥，就有一些审稿人直接说什么英语不好，要找那个专业的 proofreading 公司那个啥，这种我觉得就是你先看你自己英语啥水平，这就是一看就是无聊，就是没有意义的那个审稿意见嘛，对不对？还有就直接说 novelty 不够，讲出来 novelty 哪不够，就好像我说我有 novelty， 我要讲出来我哪有 novelty， 那你讲我 novelty 不够，那你也要讲出来哪 novelty 不够，上来直接拒稿的理由是不是英语不好 novelty 不够，啪，然后那个啥
novelty 不够太多
是不是
惯用词汇
啊？这看自己懒得花时间审，不愿意审稿别接受邀请呗。那像我不愿意审稿，现在发邀请我都不审。不祸害人家，
不是。
我得去透气。
啊，走啊。
45啊，早着嘞，你在吃。
吃完饭到就一直到那个。
估计有10分钟 break。我看一下时间，估计有10分钟 break。就吴老师，就咱那个meeting general meeting， 然后应该40分钟差不多就结束了，能休息一下，不然连着的话，估计大家也坐不住。
主要是吴老师讲，你和吴老师讲，然后我们是在那个。
对，我刚刚那个我问吴老师，全部都进去，
全进去一起开这个。
对，那说不定有一些人感兴趣，想加入。
Good luck。
Thank you， 我去透气。
很多人要写没有什么好的 solution， 之前他们会建议你跟那些cost group 我们或者是便宜点样品，便宜点 cost group， 便宜点样品，便宜点 cost group。 但是我是觉得这项目都不难，但是我是觉得这项目都不难搞，就后面只要是有很多的样本，都会让大家给它变成pilot。你如果测 breakthrough 的时候，一般就是在测这个分类的项目，已经到这一步，那就是 application， 就 real world application。那 real world application 没有一个应用本学，所以这个时候我觉得也建议大家往这个 pilot 上转，也对这个实际有用的，我觉得。不然你即使你这个分数能做出来是很不错的，但是它其实是跟 pilots 它是不一样的，因为 pilots 的大小跟你这个柱子什么类型什么的，这其实对这个填充都有一定的影响。我的意思是，即使用粉末测出来这个分数，它也不可能代表真实情况下用 pilots 做这个系统分离的效果。你那个材料怕水吗？我是之前在 Newcastle 他们就有一个就是做那个 pilot 的机器，然后他们怎么做呢？就要么是加一点 solution organic solution， 就类似于 binder， 要么就是水跟这个粉末给它混合完了之后，就放到那个仪器里面，它就给你成型出来。它成的之后它也不会散。如果只是水的话，其实我觉得都不大，因为它也没有加其他的 binder， 那你做 solution 的时候，它其实所有成分都是来自于这个样品。如果加上 binder 就是另外一个事情，因为 binder 它很多就是不跟重量啊，就会影响这个它的还有分离的效果。
Yeah, well, so that happens more often. Sorry, less often.
But yeah, there's one thing that maybe you can help with. I don't know Funke.
Maybe
have you seen him? Do you know him?
I don't know. Maybe
when you do experiments, you tell the scientists like, vale con samples, and then all the vegetables. And then you start, sometimes they degrade or they start having secondary reactions as the time passes. So sometimes what you have like the same that by the time you utilize it, you grade it, they have changed. So those are very, you know, you can see that those things are the same.
they still really all they're doing is injecting material in that.
It's quite interesting that maybe this robot approach is expanding into so many different sectors. Well, we're talking about experiments. When you think about day-to-day lives, actually already happening, like self-service, the supermarkets, space. I think there will be quite a few disasters before.
我说还你这个嘞，谢谢。
我下午要提前走，正想问你。
啊，可以，应该能坚持，应该能坚持到下午。谢谢谢谢。你是不是瘦了？我感觉比我上次见你瘦了。
没有，
没有。
我这段时间还回国了，然后是胖了15到30斤，我感觉。但是我回来以后就迅速瘦。
你这看不出来，你
个子高，我藏肉，腿贼胖，你好天天吃说腿胖。
哎呦，都说藏肉。
还是你瘦呢，你还减肥。
我就控糖。然后赶明儿去阿伯丁玩一玩。
对，跟我的那个合同够那么长时间的吗？我现在合同补到明年的5月，合同看的是学合同还是？
在这之前也可以去嘛，是不是？让吴老师给你送回去。
我还没去过。
可以啊，去逛一逛啊，挺好的，挺好的。那你下午就一路顺风，好吧？好，谢谢啊，拜拜。
啊，是。那个 QUB 的几个学生好像就下里实验室参观一下，我就跟他们一块去转一下。
哦，行，可以，没问题。
这边应该不忙。
不忙。
你回头把这个没有插电，
电应该够。可以，应该能坚持。
那我去他们实验室交流学习。
好，你去看一下啊。
没人啊，住院了。上厕所啊？上厕所上这么长时间，掉里边了。回答纸话，现在对话影响。估计就是1.4度。我的投手估计2点。2点半，半个小时就搁这儿。
也是，想补张照片儿，就是放我们那个 background， 然后
行，
然后你在这边帮我。
可以啊。
对，
你的哪个
presentation 打出来，补一下。
没问题。
有我们，刚才我那个在哪里？
这个吧？
不是，哎，我考哪儿去了？
就是行不行？
不是，那我拿 U 盘再考一下，或者我根本就可能直接在我的那个里面。
Yes, Ali Nabali. Yeah. Do you want me to send that email to introduce you as well? Yeah, sure.
Yeah. 说要发个 post， 然后。
你找这个，那个是我的电脑，不好意思，
没事。我看哪块儿，这个吧，是不是？哎，那个哦，对。然后，
好嘞。
对，就往前一点，就。对，你就随便看。Sorry, feel free.
谢谢，客气。
谢谢，看着就是有点白菜。
这本来就是该摆拍的时候嘛。看行不行？不行，咱可以再拍。
去实验室的人有点多呀，好像把刚吃午饭的人全拐走。
谁？没事，拐走就拐走。谁安排的？
不知道，好像是萨利本地的一个老师。
哦，那为啥在这个点安排的？
对呀，
安排什么？
他们去那个 laboratory。
他们是不是觉得这个跟他没关系啊？这个按钮。
不对呀，但是萨利管事的老师不是这个。No, if it is a laboratory right
yes,
now.
Right now.
Angie,
Yeah, do you want to go?
No. It's okay. We're going to start in 10 minutes, is it?
Yes, that's what
I'm thinking the journal meeting is open to everyone.
I think so, but I don't know.
Oh, I
how
thought
many
it's
people need
open.
to be there.
Oh,
I
okay.
have no idea what the general meeting is about.
Well,
Tuesday is the
you'll
one
find
put
out.
it in.
Yeah, we want to make it open in the
Okay.
case we can attract more of the members to join in the IACC.
Okay. Yeah, because it wasn't clear what it was, and I didn't want to put the tour too late. How long do you think the meeting will take?
30 minutes.
How long did we? I don't have the schedule. Okay, he scheduled it for a full hour, so maybe when they get back we can.
And you said
Yeah, we can.
half an hour is enough.
Yeah, so they'll be back in half an hour.
Okay. Okay, sure. Thank you.
人给我拐走了，这是啥情况呢？他不是1点45就开始不？
他们是几点？那个 tour？
他说要半个小时。
那不正好完事儿了吗？这个会，咱一共40分钟。
那咱是按点开始不？咱还按点开始？
对，按点开始，因为线上还有
对呀，
其他人。
线上国内都老晚了，是不是？
嗯。
哦，那就不管。行吧。
哎。
嘿。
对，这个看起来是正常在，像是正常在讲。
没事儿。
我一摆拍就贼僵硬。
我也是。
你平时会健身吗？
我偶尔就是周末去健身房，但是都是去那种特别不累的。我特别喜欢一节课就是 stretch。咱俩不是一个级别，你这不是特别累就蹬自行车。
那不是能坐着吗？
那老累了，我就不行，我得那种就不会喘的，对，就不能喘的。
瑜伽。
啊，对，差不多这种。咱俩真是，我都觉得蹬自行车去健身房那最累的了。
这侧身这个驼背
还行。
但是我找不见他们。
啊？你不是跟着一群人吗？咋丢啊？
没有，他们要走的时候跑来跟你说这事儿，
然后就不见了。
哦，不见了。
哦。那你问一下那个圆圆啥的。
在问的路上。
我估计他们大概率是觉得不相关。谁组织的 lab tour？
萨里的这个管事的老师，可能确实他们不清楚，连他俩老师都不清楚到底是干啥的。 就可能安排点别的活动。是我们也在积累经验吧，这种线上线下，有时候沟通之间可能还是有一点问题。但这个东西嘛，都是在慢慢变好，总有第一次。而 YouTube 直播昨天上午都没直播成，没赶过来。
你平时感觉压力大不？教职这种？
我觉得还挺好，跟国内的老师比，我感觉我都幸福了。我感觉我的人生也就这样了，我的梦想的职业也就这样。那干啥都有点压力，你不能说完全没压力，是吧？但是吧，你说要是真压力那么大的话，也没那么大压力，就看个人选择。国内那会儿我干不了。
关键你知道，我觉得就心很累，而且就那些什么党政什么，就是都是这些，要么就是形式主义。
那种搞不了，人际关系太复杂了。
mute 了吧？
我的是mute，这个没有共享。所有人都是 mute， 所以这个 Teams 也在 mute， 我也在 mute。
哎，这不是那个萨里的 organizer 吗？
对，
他组织的 lab tour。他还在这。不是 visit 他的。
不知道 visit 谁的，但人家也不用在嘛，行。肯定博士。博后带着啥？也是刚才有学生进来跟我讲，他们要去逛一下，可能临时决定的吧。
刚才上一个 session 结束，应该在这说一下，欢迎大家。但是也没想到这帮人会走。
对。
Hi, Yesui, can you hear me?
Yes, I can hear you.
Okay. And is that your personal computer or the conference
I'm
computer?
using my personal one.
Okay. I'm not sure how many participants in the conference room. Do we need to connect to the main projector, or I think just your computer will be fine?
Well, I'm connecting with the main projector, so all of the attendees in the room can see all the slides.
Okay.
But we don't have too many of us at the moment because they are having one of the laboratory at the moment.
That's fine. As long as it can be connected to the projector. I can't. Is that connected or not?
It's connected. Can you see
Oh, I see. That's good. Yeah, I can see it now. I can see that now. Maybe we wait for 2 minutes, couple of minutes, then we can start. Yeah.
Yes, sure. Michael, we probably need to start in time because we have several of the committee members who will attend online as well. We have the link. We have a separate Teams link. No. But anyway, you are going to see all the slides which the professor is going to share his slides with us. Thanks.
Yes, can you see my slide? Yeah.
Yes, I can see it now.
Okay. Okay, I think we shall start. Yeah.
Yeah, we can do it.
Just maybe start to record the session. Okay. Hello, everyone. My name is Chunfei Wu. I'm from Queen's University, Belfast. I'm also the chair of IACC. IACC is the International Association for Carbon Capture. The official website is IACCR.org. So we couldn't have the IACC.org because that has been registered by someone else. So we have IACCR for research, so IACCR.org. So it's our first annual meeting. So it's some general introduction of IACC. IACC is a registered charity in Northern Ireland. The registration number is here. We started about 2 years ago, but we formally get registered last year, I think around summertime. And IACC have very close relationship with CCST, which is Carbon Capture Science and Technology, and ICME journal published by Elsevier. So IACC, the core members of IACC are mainly editors of CCST, but IACC is a separate group. So we have our independent management team, and also the key thing is have our own finance account, so we can independently manage the activities. So the key purpose, I think, our aim is to promote carbon capture research and technology. So research and also commercialization. We try to be a good platform, a useful platform to promote collaborations, among our members, or we have new members. So basically between the academics and also, collaboration between the academics and the industries. So I think that's very important. Here is because this is a charity group, the key purpose is we want to make some personal contribution to this, to the world, because most of us as professional researchers or employees in this field. And so we just try to contribute to the healthy development of the world in terms of carbon removal, carbon capture. Of course, that is expanded to very broad topics like bioenergy and hydrogen and CO2 utilization and CO2 storage, etc. But the main thing is focused around carbon capture. So we do one of the benefits is for the participants or members of IACC so it provides some kind of career development opportunities, especially for early careers. So we need this platform to build our network, to know more people, or even to know some of the cutting edge research through like conference, event, workshops, and also just build some. Also that sometimes in terms of the promotion or finding new jobs or etc. That also should be helpful. And we also want to promote the knowledge exchange, in a broad area, so disseminate the results of carbon capture. So we generate a lot of results, research results, from engineering, development. So we try to promote and the knowledge exchange among the members and non-members. And so it's a charity group. So basically, all of us are. Work in this group, we don't get any payment. Of course, there are some volunteers. They have some kind of time-based payment to them for very small number of volunteers. So one of the key activities for IACC is a membership. So we provide free membership. So it's all free. And we have 4 categories. The first one is distinguished fellow, which are really world-known academics, leading academics in that specific area. We only have 10 distinguished fellows. So we aim to have about 1 or 2 each year. So this is invited only or recommended by someone. So we also have fellows of IACC, which are normally professors in the carbon capture or related area, also should be well known in their specific research area. So currently we have 37 fellows. We are open to increase 5 to 10 fellows each year. So if you think you are eligible or you want to recommend someone, just get in touch. So for senior member and members, it's all open. So you can use this QR code, or you can find it on the website. So to apply for senior member of IACC or member of IACC, we will send you the confirmation and also the certificates. So both are free. For senior member, we expect you to be an academic. That means lecturer or about position at the university, or kind of senior employer in a company. For members, so normally they are PhD students, postdoctors, or junior member in a company. So both all these categories are free. So for senior members, we also add your names and to the list at the website, the IACC website, so you can find your names at the website. And for members, we send you the certificate. It is noted that for the senior members, we ask you because we try to develop an expert database. I'm going to mention that later. So we ask senior members to be whether or not they are agreed to be included in our database, expert database. So the other key activity of IACC is the training. So I think this is something we are proud of, or we want to focus on, because it provides direct impact. Also this is what I think we can do, or we are comfortable to do, to provide training. So we will invite what leading researchers to give presentations to, and for example, we did one on 7th December 2023. So we have four presentations about CO2 capture using liquid-based solvent, solid-based adsorbent, membrane. So these key research areas and direct air capture. So these 4 key areas. I think these training materials presentations are also available. What we are doing next, I'm going to mention that later, is we try to expand this to a 4 course about carbon capture in the future. So conference events also are the key activities of IACC. So we had one last year, December, at Queen's University of Belfast. So this is the main building of the Belfast. We have, I think, around 15 to 20 participants joined in person, and 5 to 10 presentations online. And the participants, that's also open to everyone online. And so that's a hybrid event, joint event actually with CSCST, which is Chinese Society in Chemical Science and Technology in the UK. We have the sub-conference. So IACC, instead of have an annual big conference, we have more small conferences in the specific areas. So this one, I organize it, it's online. So we have a specific topic about integrated CO2 capture utilization. So we have the co-organizer from America, Singapore, and Spain. So this is virtual. We have, I think the presentations, most of the presentations are also available online. So we try to make this one, so IACC Integrated CO2 Capture Utilization Conference annual, so that will be online. So we also, Dr. Lei Xin from University of Surrey also organized an online conference in May this year about natural-inspired CO2 capture and conversion. So this is another sub-conference of IACC 2024. We have a plan to have another one focused on membrane-based IACC conference organized in the east by Pakistan and some groups in Pakistan. So that's a plan. So we also actually, what is happening is today, yesterday at the University of Surrey is a hybrid conference. And so that's another sub-conference. This sub-conference will be the main sub-conference of IACC. We will have AGM annual general meeting, and at this hybrid conference. So it's a hybrid conference. We have in-person and online presentations, also the online access. So for this sub-conference, also available on online presentations. And awards, we support a few conference regarding the presidential awards or other awards. But one of the key awards here is the IACC SMS award, which sponsored by Surface Measurement Systems. And so we have these are also available at the website. So this is about 1,000 cash per award, and we have 2 awardees announced recently, and there's a trophy, also certificate related. So I think this will also be annual awards. So we intend to do that. So details will be confirmed later. So for all these awards, we actually have 2 steps evaluation. So first, we send the application document out for peer review, and then we have the reviewers provide the scores. Scores normally is 6, 7, 8, 9, and so we then, based on the scores, we have a panel discussion. Normally we have around 5 to 6 panel members. Then we will rank these awardees rank the applications, then we announce the final decision. So that's mainly the procedure. We also founded the ISPT, IACC Outstanding Awards, and also Future Leader Awards and the Future Star Awards at the IACC2024 conference in Zhengzhou. That's in Zhengzhou this year. So about the finance, I would like to ask Dr. Yeshui Zhang, who is Executive Chair and the Treasurer of IACC, to provide some details regarding the finance. Okay, Yeshui, back to you.
Sure. I'm going to share my screen.
Yeah.
Okay, I guess everyone can see my slides, is it?
Yeah, I can see a slide.
Okay,
yeah.
Great. But Chunfei, you forgot to introduce yourself, but actually it's my bad. I'm chairing this session. I should introduce yourself, but I'm sure that most of the people should know you. So Professor Chunfei, who is the chair of IACC, because we still have several of the attendees here. They might not know you. All right. Chunfei already introduced myself. I'm in charge of all of these financial aspects of the IACC. Basically, I'm a treasurer. So I'm going to cover just several of the different things since we have the IACC business account last year. I have the statement for all of the activities in last year and also the expense claim procedure and how we are going to make the payments in general and also the invoices for any of the payments. Finally, I have the bank account in case any of the new sponsors or if you want to share it with other of the activities. So we do have our IACC business account since last year, start from end of May 2023. Was using my name as a treasurer of IACC, but it's a business account for IACC. It's not personal one. And yeah, I do take all of the transactions. It doesn't matter how big or how small of the transactions. I have all of the records and each of the transaction, I do have the proof of the payment. Everything was in profile, in the file. And all right, it's not the updated a balance of the account because I prepared this slides on 4th of this September. So in total, in last year, we do have the income is 17,000 and okay, everything in right, that's the how much we have spent is around 5,500 and the balance by 4th of September, we have around 11.6 thousand left. And I just updated the balance today. We do because we spent something for this event for these 2 days. For now, we do have around 10K 9,700 balance in the account. I made this summary. So just to give you some idea, I want to make sure it's transparent to all of the committee members and all of the members for the IACC because we are the charity. Of course, this will be made available online for the public as well to make sure everything is transparent. The most of our income is either comes from our sponsor like SMS and also from the registration of the event, for example, the CCST annual conferences and also like this IACC event. And for the expenditures, for now we spend the most of the income for paying the awards and also we do ordering some of the member gifts. That's everything. And also we do spend some of the budget for the maintenance of the website, for example. So the expense claim, we do have the template for any of the claim. For example, our volunteers or even the committee member, we spend order something or the web page of the maintenance. Everyone, even myself, I have to fill in this expense template and also provide the proof of
payment. That's all compulsory thing to get the reimbursement. And of course, in the case in the future, all of our members, if you have spent any of the thing you want to make the claim, you just email me. I will send you the template of this expense form. And also we are using this same of the expense template for our invited speakers. Chunfei just mentioned the training opportunity we provided. So sometimes we offer the payment for the invited, the most prestigious of the speakers. We're also using the same of the template. And normally it takes around 2 to 10 working days. It depends on the transaction. It's for the UK payment, it will be immediately. But some of the international transactions, it might take longer time to receive the payment. Invoice for all of the sponsors did request the invoice. That's just one of the example of this template I normally offer to the sponsors. And also we do use the same of the invoice for all of the attendees or whoever need the proof of the payment for attending for the registration, conference registration payments thing. Last is a bank account. That's the details. I just want to bring it up to make sure everybody is aware. Yes, we do have the proper of this business account to manage all of the income, all of the transactions for IACC. That's everything from my side. It's over to you now, Chunfei.
Thank you. Yes, I think maybe we can open a little bit to questions regarding the finance part.
Yes.
Then I will go to our future plans. So, are there any questions?
No question from from the room. Any questions from the online audience?
No, here. So, but anyway, you can send your feedback or comments to us by email, or the email address. The email address is carboncapture@iaccr.org. It's also available at the website. So I will finish my presentation here with the future plans.
Yeah, I can see your slide now.
Yeah. So IACC plans. We do have a lot to do in the coming year. So as you can see from the IACC website, we need to improve the diversity of the board and the committee members. So if you are interested, I guess the board members normally come from the committee members. So if you are interested in joining the committee, we have a few different committees of IACC. I think we are still at the development stage, so everything is not perfect at the moment. So we try to improve these things. So we have different committees, and even the rules of each committee or the contribution of each committee, we still we gradually try to improve them, improve these. So we want to enhance the involvement of IACC members. So how you would like to contribute to the running of this IACC or any other events or comments? So just let us know. So we try to because it's a charity. Everyone is works for the most of people works, especially committee members works for the I group free. So there's no fees, no payment. So we try. So how we can ensure the passion of the committee members, or ensure the involvement or commitment of the committee members. So we want to have some kind of measures. So for example, this one. So in general, we would like the committee members or the key members of IACC to be involved as much as they can. So we have awards, conference, training, etc. So we would like them to be involved in terms of direct involvement, give presentations, invite others to give the presentation, or promote the IACC, or or basically bring the sponsorships, etc., but anything to contribute to the development of IACC. But we have, as I mentioned, IACC is very close to CCST. CCST is ICME junior. So, but CCST annual conference are not organized by ICME. CCST annual conference are organized by us. So that conference normally is also free to attend. Even we have, it's optional to contribute to the registration fees. So we, as Yasmin mentioned, we have most of the income come from the CCST annual conferences, registration or sponsorships. So we want, for example, CCST has an annual conference normally in July. So we want our key members to attend CCST annual conference. And also IACC annual meeting normally is also around this time. So if we suggest if you fail to attend 3 consecutive times, so we will have a conversation with them to maybe suggest them to step down. So in that case, we'll give them opportunities to other active members. But of course, it's not just straightforward. So we need to discuss with the members to see to evaluate their contributions. So because the contribution can be different forms of contributions. Some members they have the ability to promote, to bring more members, or some or to promote the IACC events or etc. So it's not always about the direct involvement by just attending the meetings, but we do understand that attending the meeting or conference is very important to show their support. And IACC, we're going to have the IACC annual hybrid conference with AGM annual general meeting. So this next year, as I mentioned here, Professor Yongliang Li from Birmingham University had expressed his interest. So we're going to update that later. So 2 or 3 IACC annual sub-conference. So this year we already have 3 IACC sub-conference. So we have the CCST, have the bioinspect CO2 capture. We have this one, hydrogen. We're probably going to have another one related to the membrane. So, but if you are interested to organize a IACC sub-conference, just let us know, because IACC will actually provide a lot of support in terms of the website development, registration, invite speakers, etc. So we will provide a strong support to you. So if you are interested in organizing such a sub-conference. So we will try to develop a database of carbon capture experts, so mainly from fellows and senior members of IACC. So this database, expert database, will be categorized in a website. So we will also provide more information in the near future. We're going to have 1 annual IACC award. So hopefully IACC's SMS award will be annual one. And probably IACC at some point can create its own award. The last one is important because I think that's our main focus in the future, because we think at the moment there's almost no course about carbon capture. So there's no program about carbon capture. So we try to develop an online carbon capture course. I hope it will be free to most of members, to most of the participants, but we will see, because we really want to disseminate the knowledge. So this course could include like CO2 capture using liquid absorption, solid adsorption, membrane separation, cryogenic separation, direct air capture, these key topics. On each topic we include the fundamentals and also design and some kind of assessment. We need to work out how to efficiently assess this, and because we want to ensure the participants actually actively involved in this course. Then at the end we provide IACC certificate. We also try to have the involvement from companies, provide some case studies. So we want to make it really useful one. So as an additional training to your normal studies is for PhD students. So we try, in that case, we get you equipped with these carbon capture skills, for career development, to find jobs, etc. So that's a key plan. So any questions, you can send us an email. I will actually quickly add this email address here. So you can send us this email, send us messages through this email. It's carbon capture at IACC.org. Okay. My personal one is is this one. Okay. Any questions?
Any questions from the audience? I might just move my camera. We have around 16 or 17 people in the room at the moment.
Okay. So I stopped sharing my screen.
Oh yes, Chunfei, do you mind to bring up the QR codes again for the registration of the membership things? Yeah.
Yeah. It's also I'm sharing my screen.
Yeah, I'm thinking
so it's
it
here.
might be worth to bring up the web page actually, so everybody can access everything through our website.
So yeah, I will demonstrate this. The website is www.iacc.org. So that's a website, and we have the about the borders, communities, privacy policy, and conference and event. We can, if you actually are involved in other conference or events, or want us to promote the event, just send the information to us. We can add your conference to the website, and we can also send your conference to our members. So we do have around. So here we have around 325 senior members, 480 members at the moment. So we do have roughly 1,000 members. We have another 2 WeChat groups. I think some of them are already included here, but we do have WeChat groups. There are around 600 or 700 people there. And for members, you can see here membership. You can find out the distinguished fellows. We have 10 distinguished fellows. They are including we have one from Professor Nila Shah from Imperial, and Chris Jones from the Georgia Institute of Technology, also from Australia, other members. And we do have the fellows. We have about 37 fellows here. So so if you think you are eligible or you want to recommend someone to be fellow of IACC or distinguished fellow of IACC, just let us know. In terms of the for senior members, so we do have a list here. So that's around over 300 senior members here. We don't have IACC partners, so a few partners here. It's all free. There's no partnership fees. So if your company or would like to be partnership with IACC, because IACC is very at an early stage, so we just promote each other. There's no direct fees involved as partners. So to join us here, if your membership join us, we have 4 categories here, especially for senior member, and this QR code and the member. So it's very simple. You see, if I start that now, it's very simple form. Just a few questions: your name, your institute, your position, your email. So some list key publications, key research project, personal website, and we want to create a database in the ScienceShare website. So we will ask you or not, you're happy or not to be included. So in this ScienceShare website, so it's still under development. So in the website, we have 5 categories here. So this needs to be changed. So here under the first category, you see IACC. Then under IACC, you have IACC conference recording or IACC expert database. So you can select the regions. So under development, in China, UK, or USA. So UK, then we're based on the research area, have DAC, life cycle assessment, etc. I'm not sure we have anyone from the UK. And search, we have no one from the UK at the moment. I guess there are some, that's USA, if anyone. Yeah, but that's a purpose. We try to categorize the information and put them into a database. And then let me check if I have anyone from China. So, and then this, you can, if you find someone, you can actually, so we have someone it's still under development, so we could actually do some discussion, leave a comment here. So of course you need to register. So a very simple registration process. So that's under development. We do have the recorded videos. I think they are available. So we have science share. This is also we try to do. We have, of course, there's other things like CO2 adsorption. So that's under development. So we have the conference recording. Let me check. So we do have this nature-inspired conference recording. We have some conference recording here. So that's about the membership. So it's a relatively simple process. Okay. Any other questions?
Any more questions from the audience? No? We're open for all kinds of the collaboration. Maybe Series can be one of our industrial partners. There will be no free of charge.
Yeah, it sounds like a good
idea. Okay, I think we expect to finish at past. Yeah, is that correct?
past. Yes.
2. Yes, yeah, so I have 8 minutes. So that's actually not bad.
It's okay. We have the next session will start at 14:40, so we have around 17 minutes. If we have more of the things we want to discuss.
Okay.
Any questions? We still have the chair of IACC here. We can ask any questions for him. Okay.
So anyway, we can get in touch anyway using emails, or we're gonna have more events. IACC event.
All right. If no more questions, shall we stop here, Chunfei?
Thank you, everyone. I'm sorry I can't join them and attend the conference in person. But it was not expected. But okay.
We can all see you.
Okay, thanks. Okay, let's stop this meeting here.
Thank you very much.
Bye, everyone.
Thank you.
Bye.
Well, guys, this is a very general meeting for the IACC because we are proper of the charity. We want to make sure everything is transparent. So, and also make sure all of the committee members are aware of the activities and the strategy of the IACC. That's the purpose, only purpose of this annual general meeting. But if you haven't become the members of the IACC, I would strongly recommend you to do so. Why not? Is it free of charge, and you are going to have the IACC program with the membership certificates, and also you'll be informed for all of the IACC related of the events. We do run. Some of you might miss of the first half of the talk from Professor Chunfei Wu. We do running of the training schools and also events, small scale of the workshops, and large scale of the conferences, all sorts of the things. We do invite the prestigious of speakers to give the training, and in the long term, we are planning to run the part of the training program for the industrial partners, and also make it available to all the industries as well, to make sure we targeting on someone who really want to gain new knowledge relevant to the carbon capture science and the technology. And also, if you have any of the partners, industrial partners who want to become the industrial partner of IACC, please recommend them to do, because it's free of charge. I'm not going to ask you to sponsor how much of the British pounds to IACC. That's no problem. We can easily add the logo to become the industrial partner. It's similar as other types of the membership. It's free of charge. But in the case we want the sponsor, of course myself and also Professor will get in touch, but nothing will be bonding to the memberships, either the normal member, 4 tiers of the member, or industrial partner membership things. So everything is flexible. Any questions for me? Professor Chunfei Wu is the chair of the IACC. I'm the treasurer and also the executive chair of the IACC. So I'm doing all sorts of the things, try to help Professor Wu. So any questions, get in touch to me or Professor Wu. at the end of this session, enjoy the coffee break, and we'll start the last session in around 15 minutes. Thank you.好嘞，
我去开始打包。
行，那有机会咱机会多的去了，行不行？我还得
去伦敦，我把钥匙拼那儿，我等一会儿去找钥匙。
行行，你找。
啊，那我先去收拾一下。
OK， 好，拜拜。
Literally, it's Friday, I think. What's next week? It's very soon. Yeah, so it's not as. Yeah. Theoretically, both physics examiners should have read it by now. We read the actual we read the thesis on the way to it, sort of stuff. So he has got it. So last week we had a practice via. We made lots of notes, asked questions I didn't know the answers to. Or didn't know the answers to, or just in the moment panicked. Which I think is his biggest weakness is that occasionally he just sees up and his brain stops working under pressure. Which is particularly helpful for a bio, I would say. Just automatic stuff like that. Who knows what it is? He's tested a lot of materials at scales that no one's testing those materials at. I mean, some of the stuff he's done is not in his thesis though, but all of his modelling stuff.
我都忘了。
So it's just left out. Which is he's just overworried about it, because that's also why he's not going to Canada. He's just too worried about his thesis. Maybe Adam got, yeah. Oh no, I think Adam got turned down. It's abstract. Yeah. It's like, yeah. It's coming up soon. It might be this Thursday, it might be immediately after before the. Yeah. So I think it's in the morning, so I think it's hoping he'll be able to get to the meeting. I don't think he should come to me anyway, but. So it's not that. Which I think is why he also didn't like going. Well, he's only been paid to do postdoc work. He's self-funded PhD. For the last year, he's been working on various different postdoc funded. The university's laughing because he's being paid research assistant rather than research associate salary for it. So as soon as you pick your hire, you need to go let HR know that you'd like a pay rise. I think it's in the contract. I think the contract might say like if you accepted pre-Fiverr. So I'm pretty sure it's Fiverr because I started before I took my degree certificate. They paid me research associate the whole time. this was after I had my corrections. So I'd had my corrections approved before I started. That was by like 2 weeks. I just admittedly, the Vincenzo was my external examiner, so it was quite easy for him to be like, yes, I know how far he's got through because I was the external examiner.
All good?
Do you want to switch the screen?
Okay, all good. Can you remove this one? Recording has started. Is hiding somewhere. That's a YouTube streaming. Hiding somewhere. I checked, it's not here, but somehow it's appearing while I'm streaming it.
Yeah, so you are streaming.
Yes.
So it's on this PC then, I think.
No. Oh yes, you're right. I got confused, sorry. Yes, you are right. It's from my side. That's why I was confused. You're absolutely right.
So that's okay.
All good, all good. Thank you.
Yeah, so then we're all good. The only thing is to unmute then before we start. Good to go. The microphones should all be fine.
Hope so. I
Yes,
hope.
but if they're not, it's so you can see it here. If I click on it, might have to click and hold or something like that.
All right. Okay. Now it's connecting.
This one.
Excellent. Thank you. Cheers.
And yeah, they told me it's better to put it, instead of having it, it's better to hang it on something.
I think I heard a story that I don't know where they're from, where
I'm going to grab a drink. Do you want a drink?
No, I have just.
one thing based on experimental work or based on like literature reviews and literature review written by a supervisor. It's like, yeah, the reason this model I'm willing to use is because it's all published, the literature is published here. And it's like, yeah, you read that paper, it's useless, it's rubbish, it's all mistakes. And the supervisor could come in and describe like why the model was a good model to use. Because I used a literature model. But I don't know if that's actually true or whether it's some lovely hyper model to scare PhD students.
It's okay, we'll have another 5 minutes.
Sure.
Let's want to put it somewhere. Yes. No, not too close. I mean, that's good.
Okay.
Good. It's very crazy in the room. It's a break. Either you can have the coffee, snacks, or you can ask questions. Is it? Too quiet. Or everybody is sleeping in the afternoon because of the lunch. Shall we cancel a lunch for future IACC events? No, you don't, is it? Ah, that makes sense. Thanks, Paula.
a bit less than 30 minutes.
Okay. So we need the Haribo for the future IACC events rather than the cakes. All right, I will take the notes.
Yeah, of course. Yeah, I know. We can put that in the awards.
We could do it.
Like that's
I think that's a good idea. Actually, for the events I'm organizing in Aberdeen, I do provide the Haribo.
Really, you do?
Yeah, I do.
You're a fan?
Yes, 2 weeks before.
No, are you a fan of this?
Yes, personally, I'm a fan of the Haribo.
Exactly.
Yes.
I vote for that as well.
Is it?
Yeah, I vote for
Everybody,
that.
is it?
Yeah, I don't know anyone who.
So we should really make sure, Haribo is something essential for the IACC events.
Yeah, I think
Everybody love it.
Maybe they can sponsor. We can ask them if they can sponsor the meeting.
That's the best idea, is it?
If this is plastic, we can recycle it.
Yes.
Get some carbon.
You can get some carbon. We don't know. Maybe we can get that.
Well, I need to find out a way to reach to the Haribo. Is it?
You can all email them. Just bomb them with emails. They have to reply.
I'm going to email Haribo tomorrow.
Thank you.
I think they should be happy.
Yeah, why not? Is it?
On the website.
Yes. And we can help Haribo to promote as well. Carbon neutral Haribo company.
And the companies, the factories, the plants, the carbonizer plants.
That's going to be very fun.
I would like to collaborate in that project and visit the plants myself with a bag.
We could do.
I was digging into recruitment.
I was always thinking to collaborate with Volvic because personally I drink Volvic water all the time. And even my students, doing the experiment, we were using the Volvic bottle.
Yeah.
I was always thinking I need to find out a way to ask the Volvic to sponsor my
I did my
research.
PhD around the area where Volvic is, where they capture
Is
the
it?
water. Yeah.
You have any contacts?
No, unfortunately not. I can try to get by some people that I know there, but I worked in the area, beautiful area. Yeah, I love the water as well.
Now when we start talking, time flies, is it? 1 minute to
Yeah,
go.
that's true.
Yes, I think I'll just make a very brief introduction. Okay. Well, hello everyone. This is the last session of this IACC event, and okay, that's an echo. Yeah, I'm Yishi from the University of Aberdeen. You all know me now, is it? Well, the first keynote speaker for the last session will be Dr. Leila Mora from Queen's University of Belfast. Dr. Mora is a lecturer in physical chemistry in the School of Chemistry and Chemical Engineering at the QUB. She was a Royal Academy of Engineering Research Fellow between 2019 to 2024 and founded a research group focused in developing liquid engineering for gas separations. Oh, really? That's good. I want to meet all of your group members. All right, I won't spend too much of the time for the introduction because I would assume Leila has a lot of interesting work to share with everyone. It's over to you now.
Thank you so much for the kind introduction. So, full disclosure, although I was able to convince a few people at the Royal Academy of Engineering that I could do some engineering work, I don't have a degree in engineering. Okay, I'm a chemist by trade and I'm trained in physical chemistry. So my approach would be more fundamental than the majority of you. So I learned a lot from being here, and I thank the organizers for letting me present my work here. So don't kick me out. I'm not an engineer. Don't kick me out. I'm willing to collaborate and learn from all of you, and I have learned a lot. So today I've decided to talk to you about a short project on CO2 capture, so developing liquid materials. We didn't hear that much so far in the conference about liquid materials, so it's a bit different. But how I steer the discovery of these liquid materials for CO2 capture in biogas streams. Okay, so first of all, I wanted to also show you a bit of the university. This is the main university building of Queen's University Belfast. Now it's mostly an admin building, and UC Belfast is quite special because we are in the UK, but we are also in the island of Ireland, and although some people tend to pick me up from the Heathrow international arrivals, we arrive at the domestic arrivals because we are part of the UK. Although there seems to be still some confusion about that, so I just wanted to clarify. And also, I promise you, the weather in Belfast is always like this. Always.
The team is sharing this one.
Promise. This is the reality.
So the online audience will see this as right, rather than those ones.
So, we've got something really important, but I'll make it work. So, for my research group, as I mentioned,
no,
I
it's
tend to
still the
develop
notes
different
one.
technologies for
the
gas separation, also for volatile organic compound capture and water purification systems. So some of the things that I tend to do are upgrading of biogas to biomethane, are also, I tend to try to understand specific interactions between gas and the liquid materials that I develop, in order to design optimized materials for the separations. I also work with water desalination materials for osmosis. Light hydrocarbon separation has been a long-standing interest of mine, so the separation of ethane and ethylene and propylene, which is an incredibly difficult gas separation, and I should give up on it, but I won't. And I also started using, because I have some training in making fancy polymers, so I've started using functionalized polymers for gas and water pollutant capture. And another tool that I use, and I'm going to tell you a bit about the tools that I generally use for my research, but I determine the thermodynamic properties of solvation, so the enthalpy and the entropy of solvation, and this helps me understand what is happening between the materials and the gases at the molecular level, again to design optimized materials. Sometimes this works, sometimes it doesn't. Okay, some of the materials that I use, and I am part of Queen's University Ionic Liquid Laboratory, so if you ever heard about these materials, I'll tell you a bit more about it. They look kind of like this, so quite viscous materials generally. But we have a lot of expertise in designing these materials, and we believe that it's easier for liquid materials because they are a bit disordered, so there are advantages and disadvantages to that. But we can build in the chemical, the interactions and the selectivity and the interactions at the chemical and atomic scale a bit more easily, or we have a lot of expertise in designing these liquid materials. So ionic liquids are molten salts that have a melting temperature below 100 degrees, so they are liquid, so imagine your kitchen salt, but being a liquid at room temperature, because the cations and anions that generally compose these liquids are quite large, so the charge is quite dispersed, and we have a wide variety of cations and anions, and we can functionalize these materials to try to build in these interactions, specific interactions with the gases. They also have negligible vapor pressure, as you can imagine, because they are ions, so they are not volatile, and so they are very interesting for gas separations. Another class of materials that I work with a lot and that I'm going to focus on this presentation is the hypothetic solvents. So these, they are in the same family of ionic liquids. Let's say they're not exactly the same, but there's a lot of overlap. But these are much more simple to make. They are quite cheap and easy to make. and I'm a physical chemist. I couldn't, I couldn't restrain myself. I had to put a phase diagram. So just to help you understand that we have basically a mixture of two salts. You can see here, for example, giving origin to a liquid. So if you are given the phase diagram, you have one material A, material B with high melting points. At certain compositions, they become one stable liquid, and this is the hypothetic point. Now, people work outside of this hypothetic point. Some people like to have very precise determinations on what is the hypothetic point, but the majority of the community, and these are more recent materials that are being popularized in the last 20 years, let's say, and they work outside of the hypothetic point. Now, my approach is to move from energy separation, so for example, for ethane and ethylene separation, moving from an energy-based separation agent to a mass separating agent, because this has the potential to reduce the energy consumption and the associated CO2 emissions. And depending on the application, depending on the gas separation, I move around this scale from chemisorbents to simple physisorbents. And the most difficult approach is to find the sweet spot between the two for certain separation. So, for example, for ethane ethylene separation, this is the case. Try to find the sweet spot of absorption, heat of absorption, to make the recovery of the gas not too expensive. But in the case of the biogas, I focused on a physisorbent material, and I will explain. So these are some of the tools that I use in my group, and I'm happy to collaborate with you guys on this. I want to understand gas-liquid and liquid-liquid behavior, so interactions with gases, interactions with water to make better materials. And I use a screening method that I'm going to tell you about. I use thermodynamics. Surprisingly, even if we use liquid materials, mostly we can use single crystal XRD, that's for another story. We use a lot of neutron diffraction, so we were at the origin of using neutron diffraction for disordered materials, the researchers in Queen, so we use that a lot to understand the structure and the interactions in the liquid phase. We use the solid and liquid NMR, infrared, and also I have colleagues that help me with molecular dynamics simulation. So all of this helps me to design optimized materials for a variety of separations. In this case, I'm going to focus on biogas upgrading. So we heard about biogas before during this conference, so you know that there's a variety of gases and other materials that are in this gas stream. So it's a complex gas stream, and particularly in Northern Ireland, because we have a lot of farming for the population that we have, and so we have lots of farmers that are actively using the biogas directly to produce electricity, but biogas is quite dirty. So I wanted to try to make a material that could promote the cleaning, a bit of cleaning of the biogas into biomethane, but in a simple step that has to be very low cost, because for farmers and anaerobic digester, people that use an anaerobic digester to use it, it has to be very simple to use, it has to be very, very cheap. So this was the goal of this project. And so we used hypothetic solvents for this, because they are really, really easy to produce. Basically, you mix two components, okay? You mix them together and you make a liquid. And that is all you have to do. So very easy to make. And so these are our hydrogen bond acceptors and our hydrogen bond donors, which are generally considered the materials that form hypothetic solvents, either by interactions or by entropic benefits, let's say, and they have the possibility. Some of these have very low viscosity. We'll look at that in a second. There's good chemical stability. So this was my criteria. You've also heard that there's the possibility of forming sulfuric acid, because we have H2S, we have salts, we have water in the gas stream. And we wanted to understand the role of the phosphine group there. And we wanted to capture a really wide variety of impurities, because you saw how complex the gas stream is. So we want a one-step purification with just one material.
Again?
Yes. I think every time. So, as you've seen, there's really a wide variety of materials based on that are called hypothetic solvents. You can really have, you just need to do a mixture, and certain materials will form this liquid spontaneously. So the bottleneck is not the making of the material, the bottleneck is the testing of it. And as many of you know, doing gas solubility or gas uptake measurements take a long time. They are quite difficult to make to obtain good and reliable results. So the first thing that I wanted to do for a long time since my PhD is to develop a screening method that would allow me to test the solubility or the uptake of gases very, very quickly. So how to put measurement. Do it very simply with equipment that exists in the lab already, and that we could use both for the permanent gases, for VOCs, for the liquids, for the microporous solids, for volatile and non-volatile materials. So I wanted something of this, and I had an idea. Unfortunately, my student Mark was agreed to test this, and this is all his work. Okay, for the method and for the results that I'm going to show is all his work. He is going to submit his thesis hopefully very soon. And so the basic idea was very simple, I think. We have a glass vial that takes pressure up to 10 bar, 10, 12 bar. And the right combination of stopper and cap allows it to close it and to make it really sealed to gas. So gases don't come out up to 5 bar. You can use up to 5 bar without gases coming out. And this allows the multi-piercing of certain needles, certain types of needles, allows the multi-piercing without the gas escaping. This is very important because we put the empty vial, ignore the glass beads for now, we put the empty vial under vacuum in the gas line, and then we, in the same line, we add the gas or the mixture of gases inside the vial, and we measure the exact pressure. So we know the volume, we know the pressure, maybe you know where this is going, and then we can do the same with our sample. Our sample can be liquid, solid, it can be whatever you want. So we inject this gas, pure gas, or our gas mixture, and since we know the initial pressure, and here after equilibration we know the remainder of the pressure. In this case, with empty vials or with the glass beads that occupy the same space that our material would take, we form a calibration curve. So this calibration curve that we put in the headspace gas chromatograph will tell us what is the correspondence between the pressure that we measure and the peak area obtained via the GC. Okay? And by comparison with the peak area that we obtain here from the gas that is still free, that it didn't go to our material, we can, from this difference, we know what is the amount of gas and which gases actually. So we have the selectivity and the gas capture obtained at the same time. And so as I mentioned, the headspace GC takes a sample from the headspace, so the gases that have not been absorbed or adsorbed in our material, it separates them in a column, it detects them, and then we have peak areas that correspond to each one of the gases. So we have real-time selectivity and capacity at the same time. And this is sort of what we obtain, and the most difficult materials to test are, of course, physisorbent materials. Chemisorbents, you have high solubility, but we wanted to test the limits of the method. So here we tested CO2 uptake. You have the peak area from the GC, and you have here the initial pressure of the gas. And we have the calibration curve for CO2 here in black, so the correspondence between the pressure and the peak area. And here you have a bunch of organic solvents because, of course, they don't uptake CO2 that much. And so this is the limit of the technique. And so you see that we can differentiate between the materials here, and the peak area for the same pressure is smaller as expected for the solvent in comparison with the calibration curve. Because that's what we were expecting. We're expecting less gas to be present in the headspace after we add the solvent. We tested it, so each point that you see here, each pressure was tested in triplicate. We can pressurize 3 samples at a time. Okay, so you obtain very consistent results for each measurement. But this is only a screening method, so we don't want high precision. That would defeat the purpose. I have methods for high precision solubility. And we tested this for a variety of gases: CO2, methane, ethane, ethylene, and hydrogen. Conceptually, hydrogen, of course, it's very hard to get materials that absorb at room temperature a lot of hydrogen, so we just tested for the conceptual part. And for gas mixtures, the gases behave in the same way as for the pure gases, and we have linearity in this calibration curve up to 2.5 bars. So that is the limitation of the pressures that we can test, which are the ones that are interesting and relevant to me. We then compared with the literature. You can see here the full bars are for our results, and the hollow bars for the literature results, and all of these organic solvents and an ionic liquid. And we have really they compared well with the literature within our uncertainty. Our uncertainty is associated with the dispersion of the data, okay? Because we have poor temperature control, and that is important. Have good temperature control for the gases. But this is okay for screening. We then compared with highly sorbent materials, so we tested microporous solids like zeolite rho and 4 angstrom molecular sieves. We also tested the porous liquid because the creator of porous liquids is our neighbor, Professor Stuart James, and these are basically the mixture between liquids that stay outside of microporous materials that are mixed into this liquid. And we also tested MEA, so a chemisorbent, a known chemisorbent for CO2, and quite volatile as well. And as you can see, our results in the full bars compared very well with the striped bars, the results from the literature. So we have proved the concept. We can use this method to screen very quickly, up to 264 samples per day after equilibration. So we can screen a lot of materials in a short amount of time for a variety of gases and gas mixtures. Then to perform proper gas solubility measurements or gas uptake measurements, I use I designed the equipment to perform this, and I use an isochronic saturation method, which consists of a gas chamber where I put the gas or the mixture of gases. I evacuate the equilibration chamber where I have my sample, and then I put the two in contact. I know the volume of the rig very, very well. And so, of course, after I add the gas that is in here and I put it in contact with my sample, I see the pressure increase because of the increase of volume. But then we see slowly the gas going into our material. And from comparison of the initial amount of gas with the final amount of gas given by the temperature and volume measurements, then I can, by subtraction, I can determine the amount of gas that went into our liquid. And this allows me to perform very precise measurements and have access to the thermodynamic properties of solvation. So the first thing for our hypothetic solvents that we wanted to test was the viscosity, because as you know, this has an impact on the absorption and desorption kinetics and the ability to move around the liquids, to pump the solvents around. And so as you can see here, we're comparing our materials to Genosorb 1753, which is a physisorbent mixture for CO2. We wanted a fair comparison, not a comparison with the chemisorbent. That doesn't make sense to compare. And the typical ionic liquid that has been popularized for this separation. And you see we have actually quite viscous materials like this topo-oxalic acid, but we also have very low viscosity materials, much lower than typically we have for ionic liquids. And so these are good competitors for fast absorption and desorption kinetics. One of the issues with the hypothetic solvents is the thermal stability. So not the chemical thermal stability, well, a bit of that, not for the ones that we created, but the physical thermal stability, meaning they are a bit volatile, or they can be a bit volatile. So as you can see here, these are thermal stability measurements at around 50 degrees, and you see our mixture, this mixture, for example, here is quite volatile, and so we see the evaporation of the material. Of course, these are at high flux of gas, so it's not representative of industrial conditions, but at least it gives us a comparison between all of these hypothetic solvents. And so the most promising ones were the TBPO, so the two phosphines with levulinic acid. We then use the screening method to determine the CO2 capacity for these materials. And the most promising one, so in terms of CO2 capacity, here's in milligram per gram, or this with the higher bars. which is this one that was quite volatile. We still took it forward for comparison, but all of these, the topo-gluconate and the with glufosinate mixtures and the TBPO for further testing. So we then obtained the gas solubility measurements for these materials that I just told you about, and what we see here is the mole fraction of the gas in the diputetic solvent over a range of temperatures, and in the full symbols you have CO2, and in the hollow symbols you have methane, and you see that CO2 is always more soluble than methane. That is completely expected, as it is always generally for CO2. We have selectivities of around 7 or 8, which are not terribly high, but not too bad for this material and compare well with the Genosort, for example. We see that the gas solubility decreases with temperature, which is typical for exothermic solvation processes, and this is a typical behavior that you see here for physisorb, so very weakly attracting materials for CO2. And in here we have a comparison with the literature. We don't have milligrams per gram, but we have a typical physisorbent unit, which is Henry's constant. The larger the bar is, the lower the solubility is. So our materials are down here, so the full bars for CO2 and the striped bars for CH4. And if you compare, for example, with Genosort, you see that we are at the range of being quite competitive with the commercial material. We wanted, of course, to see if these would also be useful for a volatile organic compound capture. As I said, I wanted something that would be a one-step process to purify biogas. So we tested with 3 types of volatile organic compounds: toluene, siloxane, and limonene, and all the diprothetic solvents remove over 99.99% of VOC. I actually have a patent on this from earlier work that I did in my postdoc. So these are quite good for capturing volatile organic compounds. So I hope I have shown you that the screening method is a useful tool that we can use to screen materials at a wide range, a short range of pressures, a wide range of temperatures, but it's quite useful for a wide variety of materials. I hope it will be useful for your research. We studied the solubility in topo-based tests of CO2, CH4, and VOCs. These materials are surely capable of removing H2S as well. They remove the 99.99% of all the VOCs that we tested, and the topo levulinic acid 1 to 2 show the highest CO2 capacity of them all, with around selectivity 7 to 8, which is better than Genosort. And these materials are also very stable to the presence of sulfuric acid. Okay, up to a year, we tested the stability up to a year, and it's completely stable, and they're not bothered by the presence of water at all because they're slightly hydrophobic materials. I wanted to show you the Quill Research Center group, which I'm very pleased to work with. We have lots of industrial partners. We have partners from Shell, from Chevron, from all around the world. So it's great to have to be in this research group. And of course, I have to thank my 2 PhD students that did a lot of work for this, Mark and Sam, and collaborators Sophie, John, and Panagiotis, and of course the Royal Academy of Engineering, and all the sponsors, and all of you for listening to me. Thank you.
Thank you, Leila. Do you have any questions for Leila? Please.
Thank you very much for the presentation. Actually, my question around any enhancements over sorbents, liquid or solid. Aside from the optic, have you considered the regeneration energy as another figure of knowledge in your comparison?
You mean the comparison between this technology and others, or do you mean between?
In developing new materials or actually offering new material, have you considered the regeneration energy? So I think based on what I've understood here, you just merely focus on the uptake rather than the regeneration. So the good sorbent in the industry, if it's going to be used, it not only should have a good uptake, but only have to possess lower energy in order to dissolve, for example,
I understand. Thank you. Thank you for your question. So the energy for regeneration is very much associated with the heat absorption. So when we have physisorbent material, this energy will be quite low for the regeneration. So we have we can associate it with that, and also with the heat of vaporization, we can add on to that, and we can add on the heat capacities that are needed. So the summary of all of this is what's going to give us the information for the regeneration energy, right? But typically for physisorbent material, these energies are quite low because they are based on van der Waals interactions. Okay, so the regeneration, it's not the problem. The problem is more the capacity and the selectivity because of these non-specific interactions between the gas and liquid. So, but it is possible, of course, from the thermodynamics, and it's possible to have this, association, the heat absorption. We can calculate from our solubility, then add the latent heat of vaporization from calorimetry, and also we can add the heat capacities for our materials. So these would all compound into the regeneration energy.
Please. Okay.
Yeah, please. Okay. Thank you. Nice presentation. Just curious, if have you used also in silico tools, for example, Cosmo RS, because with that tool you can do like theoretical screening. How the results correlate to your screening? So have you used these tools as well?
I have not used. I have colleagues that use, or we didn't compare any modeling tools or any Cosmo RS tools, because we feel that for the materials that we use, the interactions and the cohesion of the liquid, they have a large impact, because we are not talking about just interactions at the in vacuum. We are talking about empty space between molecules for physisorbent. So having that space between the molecules, okay, this free volume that exists in liquids is very important in the determination of the capacity of these materials. So I don't know exactly how these would correlate, but having this experimental tool has been more useful to us because it takes that into account, and not just an ion pair or a few molecules interacting. So there can be some correlation with the interactions, but for the free volume, it's not the most useful tool to predict the behavior of these materials. Maybe for more chemisorbent and for more interactive, so at the sweet spot or chemisorbent, Cosmo RS I think would be a more useful technique for that.
Please.
Just a couple of questions. Thank you very much, by the way. That was very interesting. So when you were showing, the screening experiments that you were doing, so in the wild, when you do the sampling, obviously it pretty much depends on the volume of the sample, but I think you're going to be disturbing the equilibrium, right? How do you manage to, take that into account?
So we don't take that into account. We do disturb the sample, but the sample is not reused.
Right.
Okay, so there is some disturbance, and this is why we wanted. I have 55 pages of SI, of supplementary information in this paper, because we tested it with so many materials. We wanted to make sure that this equilibrium that was being disrupted was not interfering too much with the solubility results, with the uptake results. So you're absolutely right, it disrupts the equilibrium for within the uncertainty that we were expecting. These are okay.
Fantastic. Thank you. The last question that I had was, when you're injecting the sample into the vial, you're going to be using basically the pressure and the volume of the system to...
The sample will be in the sample vial before it's closed.
Right.
So first we put the sample, we seal the vial, and then we put it in the gas rig. We put it in the gas line.
You put the sample after?
Before. Yeah.
So because you have to take volume into account,
yes.
You have to know, I guess, the exact volume of the particles.
We do.
Right.
Yes.
Can I ask how you measure these particles?
Density measurements.
Right.
So we have the density of the materials at the variety of temperatures, and so then we measure the mass very well, and then we can assess the volume. And from this volume, it also determines the volume of glass beads that we put in for the calibration curve. Although we don't need the exact, we just need to have at a certain range for the calibration curve. So we have 2 or 3 calibration curves for different volumes.
Fantastic, thank you.
Thank you.
Thank you. Yes, we have time for last question.
How do you vacuum it out if there's a liquid in the bottom, or is it just so stable that you won't get any evaporation, or like sucking up any of the liquid through your vacuum pump?
We do not. So the needles are quite thin, so the evacuation just takes about 4 or 5 minutes, okay, to get a good vacuum and to just remove it. The liquid does bubble. And for volatile materials, so the MEA solution, which is a bit volatile, so ionic liquids and they don't evaporate, so we can just perform vacuum all day, it doesn't change anything. For MEA, we had to use a little trick, so we kind of freeze our sample, we perform vacuum, we let it heat up a little bit, we take some of the gas out, and then we close it immediately. Okay, so it's a little trick to remove most of it, but we've seen that, I mean, the results that we found in the literature for MEA, they are so different from each other, but we were right at the middle between the two. So we think it doesn't interfere too much. Again, for the uncertainties that we want for the screening method, these are okay. It's not precise measurements. The temperature is not very well controlled. We have to take the samples from the gas rig into the GC room, and then the temperature is controlled there. So there's some uncertainty in this, but for what we want, just for screening, these are okay. Thank you.
Thank you very much again, Lila. That was really insightful of the talk. Very useful message, is it? That's yours? Yes. All right, we're living in a dynamic world, so we are facing this dynamic change for our IACC event as well. We have to change the schedule, talks a little bit. Our next speaker is going to be a second keynote speaker. Is Dr. Paula Sanchisi from the Austin University. Actually, we were in the same of the research group for PhD in University of Leeds. Paula is a senior lecturer in chemical engineering at Austin University and taking her research at the Energy and Bioproducts Research Institute. In 2014, she completed her PhD at the University of Leeds. Our supervisor was Professor Paul Williams. And she was working on hydrogen production from the pyrolysis gasification of municipal solid waste using nickel-based catalyst. Paula joined in Austin University since 2017 as a lecturer, and then later on in 2022 she was promoted to senior lecturer. So it's over to you now, Paula. You remind me about my age. Sorry.
Thank you very much, thanks a lot for to the organizers for the invitation. It's really nice being here today and in some faces, 2 names I've read around. And thanks as well for the other speaker for accommodating and helping me on some presentations. So my presentation is going to be slightly different to what we have seen so far. I wanted to bring you a little bit of flavor of what we do at Austin University. Yesterday, when talking with a few of you, I realized not everyone knows where Austin University is, so I decided to add a map. Aston is located in Birmingham in the region of West Midlands in the UK. So this is an aerial view of the city. And we are very lucky to have a dedicated research center on bioenergy, which is where I undertake my research. And just a little bit of show off, They published the latest Guardian results, and the subject of chemical engineering, as you can see, Aston is in the top 3. So that possibly gives you a little bit of an overview of where we are, and that is the second year where we have maintained this 3rd place, just under Cambridge and Bath, which is quite proud to be part of a very successful department. And going into research, this is a photo of the Research Institute where I undertake my research. On the right-hand side, you can see a diagram of all the different areas that we cover, and possibly not all of them you might think are not related with carbon capture. However, nowadays we are looking at optimizing processes, doing integration, how we can make things more efficient, and one of those is around hydrogen production. We are lucky to have a wide range of analytic equipment to analyze solid, gaseous, and liquid samples. And this is good for me and quite convenient because my research is mostly experimental research. However, as you can see in there, we have also colleagues who are experts on undertaking techno-economic analysis, socio-economic analysis, environmental assessment, using different modeling tools. And from the previous talk, the presenter mentioned making processes more economically feasible. So these sort of approaches as well can help us to verify that processes are running in the way that we will expect. Today I'm wearing 2 different hats. One is, well, as a researcher and as a university, how my research is linked with today's, the topic of the conference. But I'm also a co-investigator of the Supergen Bioenergy Impact Hub, and another co-investigator is here with us. The Supergen Bioenergy Hub brings in experts from industry, academia, policymakers in order to promote and to support the deployment and implementation of bioenergy in general. But also we do a lot of work with different international bodies, and one of those is the International Energy Agency. Some of you might have come across this particular body. On the right-hand side, you can see an example of the work they do. So they are looking at analysis, creating data, bringing in policy recommendations and solutions to ensure energy security, and basically helping the world transition to a clean energy. And if you haven't been able to do it, and if you are interested on the deployment and implementation of carbon capture, utilization, and storage, you can go on the website, and then you can have flexibility on the different case studies for different countries. And this graph is particularly for the UK. So it's telling us where we are at the moment. You can see operational 2023 in carbon capture capacity, no? What we need by 2030. We are not far off, and we will require a lot from different sectors, hydrogen or ammonia, biofuels, and so on. So we can compare as well, can give us an overview on how we are comparing in terms of progress in this area with other countries. What is the link between Supergen and the International Energy Agency? Well, we are acting in Supergen as the focal point for informing EAA members on the progress in research and development and technology deployment at different technology readiness levels. In which topic, which is the task 33, looking at gasification of biomass and waste. So basically we need to collect information, we report on the progress of these technologies, and we inform as well what is the driven in terms of different government funding approaches, such as the Department of Energy Security and Net Zero, the recent innovation, Net Zero innovation programs, and so on. So what is happening in the UK, we go, in terms of gasification, biomass and waste, we go and inform the members. And we are looking at promoting the commercialization. How can we support the efficient commercialization, something that is economically, in terms of biomass and gasification processes. But also we provide input to other intertasks, such as the bioenergy with carbon capture, utilization, and storage. And I will give you today one example of what we are working on. As a message is not directly my work. I'm not expert in life cycle analysis, but I think it's important to support some of the ways that we want this technology to move forward. So earlier there was a presentation talking about gasification, but maybe not all of you are quite familiar with this particular conversion process. Gasification is looking at using high temperatures between 700 up to 1000 degrees Celsius to convert a solid biomass. We can have different types of biomass, it's not limited to one. I will give you one example in the life cycle analysis, but there is flexibility. One of the beauties of gasification is precisely that we can use different solid biomass feedstocks to obtain high value products. In this case, we are looking at using gasification to obtain a high hydrogen syngas or gas stream. But as you can see, the syngas produced is also containing other components. We have seen, including carbon dioxide, and we have seen some of those can act as impurities or can act as unwanted products in the gas stream, and therefore there is still some work to do in this area. Why hydrogen? Well, I think we all agree that hydrogen is going to be quite important. Mainly looking in the UK deployment and to achieve these net zero goals by 2050 in all the hard to decarbonize sectors such as the steel, the long haul transportation, and so on. In the diagram, you can see where gasification sits in. So we have all the biomass in this case is represented with trees. Trees are acting as a natural absorbers of CO2 emissions in the atmosphere. And then we are using gasification to transform that. As natural process of the gasification, there is some CO2 that is emitted, and then in there we can use some of the really interesting work you have presented in between yesterday and today to look at CO2 capture and then the different options, either on-site utilization, transport, storage, or further applications for industry, heating, transportation, so on. So we are looking at what is the theoretical potential of biomass energy with carbon capture and storage. Can we really achieve negative emissions? So we are talking about low carbon or negative emissions. Is that possible? Is that realistic? When we are looking at the integration of gasification and carbon capture, we know that we can use different technologies downstream for carbon capture, and this can play a major role in the overall economics, optimization, performance, and so on. And then we can have the capturing CO2 from different sources or points in the process, or as I show you, at different stages, which can be from the atmosphere. If the CO2 is not used on site or as captured, we know that we have options such as the utilization, if it is CO2 compressed and transported, pipe, and so on, or stored, to be stored, which I think there is going to be a talk as well about this particular approach later. So going back to these negative emissions, this is more or less how the whole process looks like. And as you can see in there, we have flows of work, heat, CO2 emissions at different points. In gray color, you can see the CO2, how it's moving. The arrows is showing you how is absorbed or how it's produced at different stages. As mentioned before, we can have a wide range of biomass feedstocks that can be utilized. Then we need to account for all the individual stages where CO2 can be potentially produced in the conversion pathway. Transportation, collection, transportation will create emissions, CO2 emissions. Pelleting process will create CO2 emissions, transport, CO2 emissions. So when we are assessing how effective or if we are actually delivering negative emissions, all these intermediate points in the supply chain or logistics need also to be addressed. Then we have the different conversion technologies, including, for example, power plants, combined heat and power, and the gasification with combined approaches such as the water gas shift reactors. for hydrogen production or for increasing the hydrogen content in the syngas. And as mentioned before, you can also see at the bottom there is another option, not looking at the conventional biomass resources that you might have in mind. So we are looking at municipal solid waste, and then towards the end you can see the approach for carbon capture. So I'm going to show you some results that we are presenting or working with the International Energy Agency for the Intertask on Bioenergy with Carbon Capture, and also some 2 examples of other bioenergy with carbon capture studies. So these results, if you are interested in knowing a little bit more, there is a publication in there from my colleagues at the Energy and Bioproducts Research Institute, and it divides the process, the overall process, into 3 different main sections. We have the pretreatment of the biomass, then we have the conversion, and then the carbon capture, utilization, and storage. We have talked in the past couple of days about the relevance on using experimental data to do the validation of different models. So my colleagues, they work on approaches that they are existing and very well known. And particularly when looking at the gasification stage, they use data from a pilot plant that we have on site at the Energy and Bioproduct Research Institute. So you can see it's a 1 megawatt bubbling fluidized bed reactor working at 800 degrees Celsius with oxygen. For this particular paper, they were looking on different scenarios. One it was with oxygen and one it was with air. And the main goal it was looking at the overall carbon dioxide reduction potential. They also used another scenario with pre-combustion, post-combustion, and so on. But this is the one that I think is more aligned to what we are discussing in here. The energy efficiency as well was looked into, and the emissions were mainly regarded from the process as 181 kilograms of CO2 per megawatt hour produced. As I said, I won't go into high level of detail, but on the left-hand side, I just wanted to put the main highlights of the publication, what was achieved, and what were the main findings of the process. In this case, bioenergy with carbon capture and storage using a pre-combustion carbon capture approach shows a 27% biomass to energy conversion efficiency. The table on the right-hand side is giving you all the different aspects, and also it's quite important to look into the key performance indicators of the whole process. So which are the main parameters that will tell us if the process is performing in the way that we will expect. In this case, 99% pure CO2, which was suitable for both storage and various industrial utilization pathways, was obtained. I mentioned before that for the validation of the gasification or conversion step or stage, real experimental data was used to validate that particular model. However, for the downstream carbon capture approach and looking at the hydrogen production and so on, real existing technologies were used or were looked into. However, there is no experimental data that allow the direct validation of that particular section of the whole process. In this case, they obtained 98% CO2 capture, making the system efficient for negative emissions. And that was mainly the main message we're looking at. The question is, can we use gasification as a means of having conversion, obtaining a high value product such as hydrogen, but having the whole process delivering negative emissions? And this was demonstrated in here, and in here you can see the net emissions as minus 859 kilograms of CO2 equivalent per megawatt of energy produced, meaning that is actively removing more CO2 than the one that is emitting. But there are still some challenges in the gasification technology and implementation. Someone asked in one of the previous presentations about tar formation and other contaminants that might be present in the syngas. When in reality, or from the modeling point of view, we can have a process that delivers negative emissions, there are still ways required to optimize the process and to ensure that we are reducing the amount of contaminants present in the gas stream to actually have a high hydrogen stream and to be able to capture the CO2 emissions. Due to the flexibility of the gasification process, we can use different inputs or solid feedstocks in the process itself. However, this also might pose a challenge in terms of the heterogeneity nature of them. If we are looking at municipal solid waste, for example, you can imagine all the different stuff that can be found in there. We need to pre-treat that, and that also needs to be accounted in the overall CO2 assessment of the process. The design of the gasifier as well can vary from most of the examples we have seen today in terms of approaches for reactors can be fixed bed, but we can have varieties. We can have circulating fluidized bed reactors, dual approaches for fluidized bed, and so on. So this adds another level of complexity as well. The operational conditions, including temperature, pressure, gasifying agents. I work a lot in catalyst development, so as well we can have a huge variety of in situ applications that can help us, for example, to reduce the tar via catalytic cracking, but also to increase the hydrogen produced. And can we also do some in situ CO2, as we have seen in the presentation for the integrated carbon capture approach. And finally, the process integration. Most of the research done to date in the scope of gasification is done individually from the experimental point of view. We look at the gasification as a unique unit that is not talking to what's happening upstream to what's happening downstream, including application of carbon capture. So really the integration can be extremely challenging when we are talking about hands-on real application. Gasification can also take place at not only high temperatures, but also high pressure, which can add another complexity into the integration point of view. So all these small, tiny barriers need to be addressed before we can look into the deployment of the gasification. So what we are doing at Aston University, so hopefully now you know where Aston University is. We are about to launch the Wilson Center for Low Carbon Hydrogen Production, and this is directly linked with the Supergen Bioenergy Impact Hub. So I'm leading the technology development role on gasification for low carbon hydrogen, and I'm also co-investigator in the Hydrogen Development and Knowledge Exchange Program. This center will allow us to precisely cover what I just mentioned, one of the challenges I mentioned before, that is integration. We will bring in together expertise in gasification, membranes. We talk a little bit, someone talk about development of materials that will help separation of gases. So we have one of my colleagues who is expert in membrane development, we'll have a reactor that will allow us to look into efficiencies for separation, and another colleague that will help us on assessing and looking into the efficiency of utilizing the high hydrogen stream that is produced from biomass gasification in the form of solid oxide fuel cells. But the center, as will bring in all this experimental expertise, will look into going beyond analyzing single units from experimentally. We look at the development of novel catalysts, as I said, for optimizing the gasification, hydrogen separation using membranes and upgrading. How can we utilize the syngas? Yes, solid oxide fuel cells can pose a nice, straightforward way to do it, but it's not the only one, it's not the only utilization route, so what else can we do? And look at the process integration, and mostly using digital approaches. So on the right-hand side, you see an example of what we want to do with this center. So if we are able to develop a connection between what we have in the physical plant and from the digital twin approaches, then we can reduce as well the energy and time needed for optimizing, like doing all these iterations that we are all familiar with and very challenging when doing from the experimental point of view, but also how can we increase the performance of the process. And that photograph is the reactor for the gasification unit, which has been delivered and co-funded by the Wolfson Foundation and Aston University. And the last project I wanted to cover is one that was funded by the Industrial Decarbonization Research Center, which was looking at CO2 measurement guidelines. In here we had some industrial partners and the Energy Institute, which we wanted to address one of the main challenges that is still ongoing in the CO2 scope from different industrial processes, which is how can we effectively measure CO2 streams containing different impurities, different type of impurities and at different concentrations. And there is no really out there in the literature anything that can help us or provide the actual operators on how to undertake this sort of measurements. On the right-hand side, you have the triple point diagram for CO2. We know how pure CO2 behaves very well. We know the conditions. We know what happens when we change temperature, when we change pressure, and so on. And we know where the triple point occurs and also the critical points when these are happening. However, as you know, and some of the presentations address as well, what happens when we have moisture, when we have water, when we have other impurities? How can we achieve an accuracy level in terms of CO2 concentrations? So really we submitted a first draft and we are hoping that this is going to be released or published as an addition of the Energy Institute library soon. To understand how can we overcome barriers such as the equation of state not working no more for conventional measurement methods. What is the impact on liquid vapor phase boundaries? What is expansion regimes and so on, and why we can have these accuracy levels when we have impurities present. So yeah, keep an eye on, if you are on LinkedIn, keep an eye on that. Hopefully that will be published soon. So just as a sort of conclusions in terms of what can be the pathways then for implementation and cost. I covered 3 projects that have shown, yes, we can have bioenergy via gasification as a negative emission. We can have also a high hydrogen as a result of the process. But there are still barriers to be overcome. The cost of the hydrogen production will depend on the technology, as we know, on the cost of the energy source that is used, which is also very significant according to the region where we are implementing the process. And this is something that is a key message as well from the first project I show you. There are a lot of leverages that need to be addressed in terms of regional differences. And really the production cost will be only a fraction of the final cost consumers need to pay, because we need to include the conversion, reconversion costs. If there is any purification needed, that also needs to be addressed as part of the overall costs, transportation costs and so on. And this can even be greater than the production itself. So that is something as well to be taken into account. And other factors, such as the technology's advancement level, we talk about the TRLs, availability of existing infrastructure, and the feedstock price. So it is more cost-effective from what we have seen to really look at deploying these technologies in combination. For example, as I said, biomass combined with heat and power, with carbon capture and storage, and so on. And the cost-optimal combination of these technologies will be ultimately a function of the hydrogen, in this case, electricity and heat prices. So hopefully that gave you a good overview of what we do at Aston. If you're interested in working in any of these projects, I talked to someone about biochar upgrading as part of the gasification process, even looking at as a potential material for CO2 absorption and so on. By all means, reach out. So thank you for your attention.
Thank you very much, Paula. Do we have any questions for Paula? Please.
Yeah, thank you. I had a question about BECCS. So currently the main feedstock is from trees, right? But trees grow slowly. Are there any case studies where there's something more available?
Well, that is why I emphasize about the regional factor. One of the things to make sure that the overall BECCS is efficient is to look at what we have available in the area where BECCS is to be deployed and implemented. For example, maybe wood waste might be good for an area where they are using wood to produce, I don't know, kitchen, furniture, or whatever it is, whilst maybe for another region that might not be suitable, that maybe is a region that is isolated, and maybe they have a lot of, I don't know, forest waste, and maybe forest waste that be a more suitable application for another region. So really the way that BECCS can move forward in terms of implementation in the short and medium term is looking at it not as an individual technology that can be just utilized, but also that needs to be adapted according to the region or place where it's going to be implemented. Another option, as you saw in there, it was municipal solid waste, and we know that is available everywhere. So really that can also provide a different level of flexibility in terms of where it can be implemented. And also you have heard about approaches like drugs. Maybe they need to bring in extra, like if you require wood with certain degree of purity, maybe they are bringing it from Canada or other countries. And by doing that as well, there is CO2 emissions associated with the sample collection, transportation, and so on. So if you want the process to be efficient, all these logistics and potential additional CO2 emissions in transportation, conversion, preparation need to be taken into account.
Thank you.
Any more questions, please?
Yeah, by the way, Vlad, also anaerobic digestion as well is a BECCS technology, right? If you remove the CO2 from that, and that's like energy crops like maize and stuff.
Which also can be more suitable when you think about food waste.
Yeah.
Food waste, it has a lot of moisture, and again, that is why it's quite important to think about the region and the location where the technology is to be implemented. Maybe gasification is not suitable if you have a lot of food waste because of the high moisture content.
That wasn't my question, but I just wanted to add. I was quite interested because, I know gasification has been around a really long time for biomass, but what is the TRL level currently, and what's like the biggest site that you know exists that actually commercially operates?
The TRL is high, it's operational, it's industrial, is well known, but in the same way as gasification has flexibility to process different types of feedstocks, it has flexibility to deliver different types of outputs, and the syngas can be used for combined heat and power, can be used for high hydrogen, can be used for different things.
But do you know of any big commercial sites that really, because I know, I'm just interested because I don't actually know of any biomass.
Waste to energy facilities also rely on biomass, and we have very good examples in the Nordic countries, which are extremely successful in the way that they were using municipal solid waste, and they actually need to import it from other countries because of the need of high capacity and also the continuous process. We also have for Supergen as partners Q Technologies, who are actually in the way of moving into industrial scale. Now they have pilot plans for hydrogen production from municipal solid waste, and now they are in the process of moving. I have been in contact with other companies such as Leilac, who are already implementing that. ABSL is a very good example. They work on gasification. They are in Swindon. Those are here in the UK, and Evero Technology, who are developers of gasification. So yes, it's well known, but again, there are some points that could be refined to optimize the process for them.
Any more questions for Paula? No? Okay, let's thank again for Paula for sharing all these interesting projects. Paula is the last keynote speaker. I just did a quick mess, you know. We have 8
it was my fault, so I want to take
we have 8 of the keynote speakers for this event. When anyone realize 4 of us are female. That's a very important event.
I need to go to equality, diversity, and inclusion.
Yeah, that's what I want to bring out. So that's a very strong, solid of the proof. IACC we are trying our best to promote the EDI. That's a milestone for us. Okay, I'll just. All right. Our next speaker is Farzani. Sorry, I'm really bad at pronunciation names. So, Farzani Asfahani from Brunel University, London. All right, over to you now.
Okay. Good afternoon, everyone. I'm going to present our research work about multi-phase flow modeling for CO2 sequestration in deformable porous media. In these 2 days, you heard about carbon capture technologies and processes. But once CO2 is captured and isolated, it is pressurized into a supercritical state, so it can be transported through by using pipelines or ships to a storage site, and it is injected into the storage. There are various geological storage options, but among those, deep saline aquifers offer the largest potential capacity. These permeable rocks saturated with brine can be found worldwide and could be a key for our CO2 mitigation efforts. So there are various processes involved during injection of CO2 into the storage, like thermal effects, chemical effects, mechanical effects. In our research, we focus on 2 phenomena. First, the deformation of the storage due to hydromechanical coupling when you inject CO2 into the storage, and how the pore pressure changes into the storage and how it affects the subsidence and uplift of the cap rock in the storage. And the second, we focus on the effect of cracks and faults during the injection of CO2 into the storage. So if there is a fault in the storage site, when we inject CO2, it can outflow to the atmosphere or into the seawater and could be hazardous. So we define a model that simulates this saline aquifer, how this injection of CO2 propagates inside the storage. In our model, we consider a 3-phase porous medium for the saline aquifer, including the solid phase, fluid phase, and the CO2 phase. So we simplify the model by using this assumption. For example, we assume that the temperature is constant, there is no chemical reaction between different phases, and also there is no mutual dissolution between CO2 and water, and the viscosity of CO2 is constant, and also the mechanical properties of the solid skeleton is not affected due to CO2 sequestration. So we simplified the model because we are in the preliminary stage of our research. And to define the model, we wrote the balance equation. These balance equations include the momentum balance equations, which is written for the whole porous medium. So in the momentum balance equation, we have considered the effective density of the porous medium as a combination of the density of the solid phase, the density of the water phase, and the density of the CO2 phase. And also we use the effective stress concept, in which the total stress is a combination of the effective stress and pore pressure. And pore pressure is defined as a combination of water, pore pressure, and the CO2 pressure. And for the solid skeleton, we use the elastic behavior. And so the effective stress is related to the strain by Hooke's law. Then we wrote the mass balance for the fluid phase and the CO2 phase. I don't want to go through these details of the mass balance equations, but I want to draw your attention to the unknowns of these three equations. So we have 5 unknowns in 3 different equations. The unknowns are degree of water saturation, SW, the pore water pressure, PW, the degree of CO2 saturation, SG, and the pressure of the CO2, PG, and also the strain. Oh, sorry. Fortunately, these unknowns are related. For example, the degree of water saturation plus the degree of CO2 saturation is equal to 1. Also, the subtraction of the gas pressure from the pore water pressure gives us the capillary pressure, which is related to the degree of water saturation. So, with using these relations, we can decrease the number of unknowns to 3. So, we have 3 equations and 3 unknowns. For solving these equations, we use finite element method. So, it is a mathematical method to solve the partial differential equations. So, we multiply the 3 equations by the field variables of displacement, CO2 pressure, and the degree of water saturation. And we can find the weak form of the equations. So for solving this equation, we proposed a 2-dimensional element in which we have 8 nodes. In the corner nodes, we have 4 degrees of freedom, including the horizontal and vertical displacement, CO2 pressure, and degree of water saturation. While in the middle nodes, we have the displacement along horizontal and vertical axis. We define this element in user-defined subroutine of Abacus. So we develop the code for this element and use Abacus for input file and so on. So to validate our model, we tested for 2 different examples. First, for a saturated porous medium. So in this test, you can see the boundary condition in the left. So we have a column with 1 meter depth. In the bottom, we constrain the displacement, while the horizontal displacement of all nodes are constrained. So, and the pore pressure is set equal to 0 at the top. So the water can go outside of this column. And we apply 100 kilopascal of physical load on the top of the column. And with this application of this load, we can see the consolidation of this column. So during the consolidation, we monitor how the pore pressure changes inside the column. So in this figure, you can see that during the consolidation time, this is the pore water pressure. The pore water pressure decreases to the hydrostatic pressure because we have considered also the gravity. And also here you can see the contour of the pore pressure changing with time. We have monitored also the displacement of this column. So during this consolidation, as we apply the load, so the water goes out and the column shrinks. So we have the increase of displacement by time of consolidation. We test our model also for an unsaturated porous medium. In this test, we have considered a column with 1 meter depth, and the displacement of the vertical displacement of the column is constrained at the bottom. The horizontal displacement are constrained for all the nodes. And for the initial condition, we have considered a pore water pressure equal to minus 280 kilopascal, and initial degree of water saturation is equal to 0.52, and the gas pressure is atmospheric pressure. And we applied a physical load of 1 kilopascal at the top of the surface. So for the loading, we decrease the pore water pressure at the top of the sample to minus 420. And we see how the degree of water saturation, pore water pressure, and displacement changes with consolidation time. In this figure, you can see the change of degree of water saturation for 4 different depths of the column. So you can see by increase of time, we have decrease of degree of water saturation to almost 0.45. And you can see that this degree of water saturation decreases gradually. And as we go to the surface, so for example 0.05 meter, it is this consolidation change of degree of water saturation is faster than in the depth. Also, the displacement of these 4 nodes are monitored during the consolidation time. Again, the displacement of the upper surface is larger than the lower surface, and also there is gradual increase of displacement for all the depths. Also, we have monitored how the pore water pressure changes during this consolidation time. So as you can see, by decrease of pore water pressure to minus 420 in the surface, you can see that this pore water pressure decreases along the column for all the nodes until it reaches to the hydrostatic pressure at the end of the consolidation time. So for the conclusion, I have presented the modeling of CO2 sequestration in a deformable porous media. So it is completely different from all the presentations that have done. It is more mathematical. And for this model, we considered the balance equation, including momentum balance equation, mass balance of CO2, and mass balance of water. And we proposed a 2-dimensional finite element to solve these balance equations. And finally, we verified and validated our model with testing it with 2 different examples, the consolidation of a saturated and unsaturated soil. Thank you for your attention.
Thank you very much. Do we have any questions for Fazani? Please.
Thank you very much. That was very interesting. So with the porous diameter, can I ask what sort of diameter you consider for porous structure?
No, for the in our model, we assume that they are superposed on each other. So we have a solid structure, and we have also the CO2 phase and also the fluid phase. They are superposed on each other, so we don't consider the holes and these things.
Right. Okay. Thank you.
Any more questions? Please go ahead.
Thank you for your presentation. Very interesting. So, as I understood, you are simulating a control volume of 1 column, right?
Yes.
But in real application, we have land or something
Yes.
that is not 1 column.
Yes.
So I was wondering if you have tried to integrate like your simulation for more columns, or to simulate something bigger, because I guess you will also have some interactions, right?
Yes, but for now, I just validated my model with the previous models that we have. But the next step is, for example, to test our model how this CO2 injection happens and how this CO2 propagates inside the real problem.
Yeah.
So I just validated my model up to now.
For the column?
Yeah.
Yeah, all right. And how long does it take you to simulate the control volume?
For this one, the time of the simulation, you mean? With a super fast computer, it is 5 minutes.
Ah, nice. Yeah.
That was quick.
Yeah.
Respect to experiment. Yeah.
Any more questions?
Just one, maybe sounds silly, but is it possible to apply your model to a porous structure and see how liquid phase of a matter, let's say CO2 for example, would move along a porous network? Is it possible
You
to
mean
apply that
you
or
consider
modify
the
that?
holes in
Yes.
the there are some models that I've considered also in this way,
Right.
but this is different because we are considering that they are superposed. These phases are superposed on each other.
Right.
Yeah.
But it is possible to kind of upgrade this model to suit that, right?
Yeah, but it is more complex
Right.
and it takes more time to simulate.
Sure.
Yeah.
Sure, thank you.
You're welcome.
Thank you. Any more questions? No, let's just thank you again. Thank you. All right.
then we need to consider time as well, because I think she's doing all this spatial
Okay. Well, our last speaker is Dr. Song He from Guangdong University of Technology. I'll leave the time for yourself to introduce yourself. I know you have more about yourself to talk with us.
Okay, hello everyone. Okay, welcome to my presentation. It's about a thermoeconomic assessment of the calcium looping process and it integrated with chemical looping hydrogen production, which can be applied for cement flue gas decomposition. Currently, the CO2 emission in the cement production sector accounts for over 7% of the total greenhouse gas emission. And according to the prediction of IEA, the global cement production will grow by 12 to 23% above the 2014 level by 2015. At that time, about 4.4 billion tons of CO2 will be emitted. Then in a typical cement production process, the fuel combustion and the limestone decomposition contribute to over 70% of CO2 emissions. Besides, the electricity consumption during the cement production will also bring indirect CO2 emissions. Then some measures are proposed to reduce the CO2 emission in the cement product, including CO2 capture and storage, and reduce the clinker to cement ratio, and the low carbon switch, and improve the thermal energy efficiency and the utilization of green power to reduce the electricity intensity. The CCS and the zero carbon fuel switch will be crucial to achieve the significant emission reduction in the cement production process. Generally, in cement products, we consider the two kinds of CO2 capture technologies, including calcium looping and solvent scribing. For a typical calcium looping process, we need an air separation unit to supply high purity oxygen to supply heat for the calcination process and avoid the CO2 dilution. But in this process, the air separation unit accounts for about 50% of the overall plant expenses, and it consumes more than 50% of the total electricity demand. Besides, in the solvent scribing process, we need steam to supply heat for solvent regeneration. But there are no efficient with heat to generate the steam to supply the solvent regeneration. If we don't have sufficient steam, then we want to capture the CO2 capture, we need to build a new combined power and heat plant to supply heat and power for the CO2 capture and the compression. So to avoid this energy intensive air separation and the CHP plant, we consider the integration of calcium looping and the chemical looping hydrogen process. It can avoid the power consumption of air separation units, and the hydrogen generated can be used for the fuel switching, and or it can be used as a byproduct for sale. Here is a typical reference of which cement plant which use the calcium looping, and it use the oxy-fuel combustion to supply heat for the calcination. In this process, the CO2 in the cement flue gas is absorbed in the carbonator, and the carbonated solids are then sent to the calciner, and the oxygen fuel combustion occurs in the calciner. After the combination and calciner cycle, the high grade thermal energy is recovered through a heat recovery steam generator to generate high pressure steam, and the high pressure steam is sent to steam turbines for power generation. In our system integration scheme, we consider to replace the oxygen fuel combustion with the air oxidation in the chemical looping hydrogen process. And besides, we recovered the waste heat from the cement production process, and the steam is decomposed to hydrogen, and it depends on the mixing ratio. We can use it in the cement production process, mixing with the natural gas in the cement production process. Besides, except for it avoids the power consumption of air separation, it also offers another advantage. In this process, the chemical energy of natural gas is cascaded, converted to hydrogen, and then converted to high-grade thermal energy. It will be beneficial to improve the thermodynamic performance. Here we introduce some of the system evaluation criteria, including the equivalent CO2 emission and the equivalent energy consumption. Since in this novel schemes, we product power, we product hydrogen. So here we calculate the equivalent CO2 emission. Considers the indirect emission associated with power and hydrogen generation, and we takes the typical natural gas combined power plant and a natural gas to hydrogen plant to calculate this equivalent CO2 emission and energy consumption. And then according to the CO2 emission and its energy consumption, we can calculate the specific primary energy consumption for CO2 avoided, and the cost of clinker, and the cost of avoided. Here is some the assumptions of feedstock we modeled in Aspen. And firstly, we modeled a base cement plant. It is based on 4,200 ton per day plant in Canada. And here are some the operating parameters of this cement plant. And here we listed some operating parameters of the calcium looping units. We compared our simulated results, the simulation results of our model, and some results in literature, and some are the base cement plant. It demonstrates the reliability of our model. Here comes the results of our model. We can find that we achieved a native 107.8 kilometer CO2 per ton clinker in our scheme, and which is much lower than the traditional calcium looping process, and we can get and compare the specific energy consumption of CO2 avoided, we achieve a decline from 4.03 GJ per ton CO2 and 2.556 GJ per ton CO2 in our scheme. Then we discussed about the influence of hydrogen blending ratio. In our cases, we discussed the hydrogen blending ratio from 5% to 20%. Since at this range, it will not it can be stable combustion and not much refrigeration for the industrial furnace. And we find that increasing the hydrogen blending ratio reduces the avoided emissions from hydrogen, and with the hydrogen blending ratio increase, with the specific energy efficiency, the specific energy consumption of CO2 avoided also increased from 2.56 GJ to 2.68. Except for the thermodynamic performance comparison, we also consider economic analysis. Here is some the calculation assumptions of our economic frameworks. And firstly, we compared the cost of equipment. Even though we don't need the air separation unit, but we introduce chemical looping hydrogen generation. It cost our scheme need more equipment, and it brings about 30 million US dollars higher than the traditional scheme. But in our scheme, we have more power and the hydrogen outputs which can be sold. So in our scheme, we can get a lower cost of CO2 avoided. In our case, it can be compared with the traditional calcium looping scheme. We can reduce the CCA from 56.6 US dollar per ton CO2 into a range from 24.1 US dollar to 30.5 US dollar. So here we come to the conclusion. In this work, we propose a concept of integrating the calcium looping process and the chemical looping hydrogen generation process to decarbonize the cement plants, and through avoiding the energy required for air separation and recovering waste heat for hydrogen production, we can realize a 36.8% reduction of the FBCCA, and the cost of the CO2 avoided can be reduced from about $56.6 to about 24.1 to 30.5 US dollar. Yeah. Future, except the current scheme works, we will further consider some more different integration schemes, including if we can have a refrigeration of the pre-climber, such as indirect heating for pre-climber to avoid the CO2 dilution during the cement production process. And also we are designing the indirect heating reactors, and we will conduct the experiments to further evaluate the process. And And also we will consider, since we have CO2 captured and we have hydrogen as byproduct, we also will consider whether it will be economically feasible to utilize CO2, including different technologies, including CO2 hydrogenation to methanol or dry reforming to methanol. So that's all my presentations. Thank you, everyone.
Thank you very much. Do you have any questions for Song? Yes? No? No one? Okay, I do have one question. I can see the emerging need of this project because China is one of the largest cement manufacturing countries. So, do you mind if I could ask if the project is funded by the government, which was the founder? I'm sure the Chinese government has put a lot of efforts and investment to promote this kind of research projects.
Yeah, it is funded by some project of some China fundings, include some.
Is it IACC?
Yeah, IACC and some science funding from my school is located in Guangdong province. Yeah.
Oh, is it from the?
Yeah.
Okay.
Yeah,
the local.
But it's different that in China most of the cement it use coal as the feedstock, not nature. But in our model, we model this based on the cement plant uses the natural gas in Canada. So we actually we will next consider using coal as the feedstock. That would be provide more detailed guideline for China.
Mm-hmm.
Yeah.
Okay, great. Thank you. Do you have any more questions? Please? No? Okay. Well, I wasn't really introduce you properly because I don't really have your biography. So you're visiting research at Cranfield University.
Yeah, currently I'm a visiting fellow in Cranfield University.
Okay, 2 affiliations. All right, that's the end of the session. It's over to Michael to close the event. Thank you very much again.
I think we might need just a couple minutes to confer about the awards, and then we'll close. So if you don't mind giving like 5 minutes of break before we close up.
我觉得这个茶他们不是说泡个3分钟就得拿出来？
啊，那会儿拿了就进来了，我觉得。但没事，就喝点那个带子的味道而已。那等一下还得颁个奖。
我知道。不给您颁一个。
不是 best oral presentation。
你不是有
？Keynote 都不算的，一般这种老师都不应该算进去的。那你要做的。
来。
So let's say you were this like one single. So I have to take that specific training. So advancing words is only that. You have an off, yes, so you can take anyone.
I don't have a seat on the 65. I have a seat on the 125. 1645 is the earliest time. It gives you the code to look up. If there's anything else, it's 1645, that's the first one. I'm going to get
But then I can get on any train from Guildford. It's just the train like Houston to Piccadilly, the specific one. I have to get on there.
Is not better. There's a 16:30.
What time is the rise to?
I'm not sure it's it's London Waterloo then, and then it's we're on the underground. This is the very last train we get, any train I feel more bad about leaving Brad in London. I booked his train ticket and I didn't book my red one.
So we should take this.
If we can get that one, it would be better.
Little awards. Have we shut down sharing stuff here? We are still. Okay. Right. Thanks for those of you that have stayed right till the bitter end. I appreciate your stamina. Without further ado, I'll just go on to presenting the prizes. So, by the way, this was really, really difficult. It was, to be honest, all the talks were really high quality. So I think there's no order here. This is just kind of the four people that kind of stood out amongst the others. There was a tiebreaker that happened outside, so that's what but we've got 4 prizes, and the first prize will go to Yuan Wang from Queen's University Belfast. She's not here, so I think this will be just reserved for her. Whoever's going to Belfast next. The next prize goes to Vladislav Zurba from University of Manchester.
You can take a photo. Am I able to have a photo with it? Right now.
Yeah.
With the host.
There you go.
The next winner is Billy Davis from Brunel University.
Well done.
Good one. And final winner is Mariam Schroeder from Brunel. And with that is the end of the conference. Thank you guys very much. I think it was mostly a success. I think most of you will probably agree. I think really it's nice to have everybody in person, and hopefully, I know that some of the students that I spoke to from Surrey were really, really appreciative of meeting everybody, and I think that there will definitely be some new collaborations between people. So I think that's a success. Hopefully you've enjoyed your time in Surrey, and looking forward to keeping in contact. I think everyone knows my email address, so if anybody wants to follow up with me, you're welcome to. And I think that's it. Cheers, guys.
Thank you. Yes.
Are you going to see anybody from Queens anytime soon?
I will take it.
Okay, cool. Yeah.
Thank you, Michael.
Yeah, thanks for all the
Oh,
help,
thanks
honestly.
for organizing. Really well organized. I can see
Great,
that
I'm
it's
glad to,
really
to be
time
honest with
consuming.
you, I was on holiday for a good part of it, and I think Chunfei did a lot.
But still, thank you very much. Let's keep in touch. So if you have any plan to visit our building,
I would
please
love
let
to.
me know,
I would
and
really love
I'm sure I want to come back again.
Great.
It's great to
You're
meet
welcome
you.
back at Surrey anytime.
Thank you, thank you.
放我这儿。
放你这儿吧，王媛媛呢？你这不给你个机会去见他？
我哪有机会啊我？
哦对，
我给你带着吧。
行，那我放办公室吧，我先替他用了。
他姓汪。
对，他姓汪，三点水的汪。
那源是哪个源？
三点水的源，他命里缺水呢。
你来微信看没那啥呢？就是有没有报名这个？三点水的源啊，源头的源。
源头的源咋写？
就是根源的源。
嗯。
啊。哇，哎，这名字好呀。
先看上人，又看上人家名字。
我就夸两句，怎么就看？
这么长还，我还不是天天我就看着肖战呢，真是。
是吧？
人性，你干嘛跟人性抗争？
都可以。
我要干嘛来着？发消息。哎呦，一心呐，我两用我都不行。
忙啥呀？
这不是直播也要看着主持那个啥那边在回这信息，我就。
有一个复旦的做水资源处理的，是跟他同名的，那没加入，但找不见。
直播。